All right, people. I believe everybody is doing great, nice, and absolutely fine. So, welcome to Unacademy NEET English. What's up, people? What's up? What's up? So, light up the chats with the fire emojis. I just want to see. Everyone means everyone. Everyone means everyone. Guys, so we have the day 2 today, okay? And we are going to smash this particular chapter, that is electrostatics. We have to kill this particular chapter, that is electrostatics, okay? Every single thing will be from the scratch. Every single thing will be from the scratch, okay? If you haven't studied before electrostatics, okay, no matter what, I'll be taking you from the scratch, from the basics, and will take you to the level which you actually need, so that you would be able to solve every single question in the NEET examination, okay? That's my guarantee. That's my guarantee. So before that, I would want you guys to hit the like button, smash the like button, because liking this session is extremely mandatory. Liking the session is extremely mandatory, okay? Yo. Great. A lot of you might be having the question, sir, why do I look something different today? It is because I have taken down all of my hair. The reason is the hair loss, okay? So I have taken it down for some time. That's the reason I'm wearing the cap today. So chill scenes, we'll have to sort everything out. Every single thing will be basically talking about in this particular chapter. And guys, if we talk over here, guys, I would want you guys to smash the like button as soon as possible, because liking this session is extremely mandatory. Liking this session is extremely mandatory. Everyone means everyone. Everyone means everyone. Okay? And light up the chats with the fire emojis. I just want to see over here fire only, fire only. If you want the killer level content, if you want the next level content, okay? If you want every single problem pattern, so that tomorrow if you open up every single module out there, so you should be able to solve every single question from that particular chapter, okay? So guys, great. Okay, now guys, let me show you one thing over here. Let me show you one thing. That is, I would say last year, we say streamed 8 months ago. This electrostatics, okay, I was done with this particular one shot. Electrostatics game of NEET 1.0, it has already crossed 1.2 lakh views. And this year, I have added so many more questions. This year, I have improvised so many things out there. And I have made this a beautiful one, okay? I have made this a concise one so that you should be able to solve every single question in the upcoming time in your NEET examination, okay? So this has already crossed so many views. So today we'll have to basically go with Game of NEET 2.0, Electrostatics, that is a day 2. That is day 2. Okay? Okay, great. So we are already done with the day 1. I guess we should start, okay? Let everybody come, let everybody join, and we will start this session over here. We will start this session over here. Okay, guys. Great. So let's start this particular session over here from the basics, and I would want you guys to take the notes, okay? Make a proper notebook and take the note of every single thing, whatever I tell you in this particular session. Okay? Now guys, let's take a look over here. Let me close this and let's basically move on to this chapter over here. So the first thing that I will show you is we will be completing every single topic, whatever is in the electrostatics, okay? Electric charges and fields, potential energy, okay? Without capacitors I'm talking about, because capacitors is the next chapter. Every single thing we will be covering in this chapter only. Next. we will be talking about, we'll be solving all the problem patterns in every single topic, whatever you have. Okay? So that in the upcoming time in the NEET 2025, you should be able to kill every single problem out there. Okay? That is the next thing. Now, guys, when it comes to the electrostatics chapter, the first topic, the very first topic that we study over here is, we say, electric charge. What this charge is all about. This is the very first topic that we talk about over here, that is electric charge. That is electric charge. Okay? Yes. Yes. Great. Now guys see. Duration of the class will be 10 to 12 hours because I have added so many problem patterns, okay, as compared to the last year. So that's the reason duration will go up. Last year I have taken, it was about 9 hours. So this time it will go 10 to 12 hours. Now, my dear friends, listen to me very carefully. When it comes to the electric charge, let's suppose I'll take a comb over here. I'll take a comb. That basic example, okay, I start every single time with the same example. I'll take a comb over here. Okay. And what I'm doing is that I'll take this comb. Let's suppose this is the comb. And I'm rubbing this comb with my hair. Okay. Unfortunately, I don't have as of now. So I'm rubbing this comb with my hair. Okay. So when I rub this comb with my hair, and then I'll basically take a small piece of papers over here. These are the small piece of papers. I'll write piece of papers. You might have done this experiment previously. I'm rubbing this comb with my hair, okay? And then I'll place the small piece of papers over here. And then I'll take this comb close to these piece of papers. What is going to happen? Sir, we have done this experiment. These piece of papers will be attracted towards the comb. They will be attracted towards the comb. They will stick to the comb. If I say, without rubbing this comb with your hair, do you think that this comb will attract these piece of papers? We say, sir, no. We say, after rubbing, when you rub this with your hair, after rubbing, we say it will attract these piece of papers. So, can I say that when you rub this comb with your hair, something gets occupied onto this comb. Something gets occupied onto this comb. And because of that something, these piece of papers are getting attracted over here. If I do not rub this comb with my hair, we say, and nothing gets occupied over here, so it will not attract. And that something is what we call the electric charge. That something is what we call the electric charge. So we say, because of this charge, this attraction took place. Because of this charge, this attraction took place. These piece of papers were attracted. It is because of the charge. Okay? When you rub the comb with your hair, charge gets occupied on this. And because of that charge, this attraction took place. These electrical and magnetic effects took place. Okay? So I can say over here, in simple words, I can say, charge is something. Charge is something due to which a body shows electrical and magnetic effects. Okay, electrical effects we'll talk about later on in the current electricity. But as of now, so we say this attraction is because of the electric charge. Okay, yes sir. Now guys, when it comes to the charge, guys, the sequence in this chapter will be next level. You guys will love it. Make sure you make the notes like I do over here. Okay, note down every single thing, whatever I tell you. You guys will love it, that is for sure. The content will be unmatchable. Now, so we say charge is something due to which these electrical and magnetic effects come into play. Now guys, listen to me very carefully. I say, sir, what is the symbol of this charge? We say, what is the symbol of this charge? Guys, when it comes to the symbol of the charge, like I say, sir, I have got a mass over here, I have got a block over here. I say its mass m is equal to 2 kgs, so symbol of mass is m. Similarly, we say symbol of charge is, I can simply say it is q. We say we have got a body over here. On this body, we say q is equal to 2 Coulomb charge. We do not say m is equal to 2 Coulomb charge, just the simple thing over here. Okay, yes. Next, I say, what is the SI unit? SI unit. Sir, SI unit of charges, we say, sir, Coulomb. Okay. I say, like, we say, how do we measure the mass? Sir, mass is 2 kgs, 3 kgs. This kg is the unit over here. When it comes to the charge, we say charge Q is equal to 2 Coulomb. Q is equal to 3 Coulomb. This Coulomb is over here, the unit. Okay, yes. Now, my dear friends, as of now, I told you what is charge. Charge is something due to which a body shows electrical and magnetic effects. Okay, like over here, this is getting attracted over here, so it shows magnetic effects. This is getting attracted, so attraction is because of the charge over here. So symbol of charge is Q. SI unit of charge is, we say, Coulomb. And then when it comes to the types of charge, guys, we have got 2 types of charge. Which one? We say positive charge, and we say negative charge. We have got positive charge and we say negative charge. As simple as that. Now guys, you might have heard this particular point also. Let's suppose if I have a positive charge over here, and if I place one more positive charge over here, can I not say, sir, this positive will repel this positive charge and this positive will repel this positive charge? Because we know positive repels, like charges repel, and unlike charges attract. And if I say I have got negative charge over here, we say these 2 charges will definitely repel. And if I say I have got over here a positive charge and I have got over here a negative charge, these 2 charges will attract each other. So the point I'll write over here, we say like charges repel. Okay. And we say unlike charges attract. Like charges repel and unlike charges attract. As simple as that. Is this clear till over here, guys? Is this clear till over here? Let me know in the chats. And guys, if you have not liked the session as of now, please do like the session as soon as possible, because liking the session is extremely mandatory. Okay, that is marking the attendance. Marking the attendance means liking the session. Okay. So this is the detail about the charge as of now. Let's now talk about the neutral body. Let's now talk about the positively charged body. And let's now talk about the negatively charged body. Now guys, understand one thing. Let's suppose I'll take a rod over here. This is the rod I have got. Okay. And in this rod, on this rod, I am saying the amount of positive charge present on the rod is exactly same as the amount of negative charge present on the rod. We say positive, negative, positive, negative, positive, negative, positive, negative. So, if the amount of positive charge is equal to the amount of negative charge, I can say the body is said to be neutral. We say this body is neutral body. So we say here, number of positive charges is equal to, we say, number of negative charges. Okay. If positive charge on a body is equal to the negative charge, the body is neutral. Okay. Now guys, if I say I have got a positively charged body, what does that mean? We say if this body is having positive charge more than the negative charge, then I call this as positively charged body. So here I say number of positive charges is greater than number of negative charges. Okay, I can make some negative also over here, but make the positive more. And then if I say negatively charged body in which negative charge is more. Okay, we say here negative charge is greater than number of positive charge. As simple as that. Just the basic 3 points. Okay. Now guys, we will move on to the properties of charge. The first property that we have over here, that is charge is conserved. Let me show you guys over here. See. What does conservation of charge actually mean? Let's suppose I am taking a box or a bag over here, okay? And inside this bag, this is a bag, let's suppose. Inside this bag, you have got 3 balls, okay? 3 metallic balls. This ball is having the 2 Coulomb charge in it. This ball is having the 3 Coulomb charge in it. This ball is having the 4 Coulomb charge in it. Can you tell me what is the net charge inside the ball? You say, sir, net charge inside the ball is 4 plus 3 is 7. 7 plus 2 is 9. So we say, sir, that is 9 Coulomb. 9 Coulomb is the net charge in the ball, in the bag. Now, I am taking this bag, okay, I'll take it to some place, okay, I'll shake it, I'll throw it up, it comes back, okay, it goes here and there, and then I'll place the same bag over here, okay, after shaking. I'll place the same bag over here. I saw that. In the first ball, right now it is 3 Coulomb charge. Previously, how much charge was in the first ball? We say, sir, 2 Coulomb. Right now it is 3 Coulomb. And I saw in the second ball, it is having 1 Coulomb charge. How much was the charge previously, sir? 3 Coulomb. Right now it is 1 Coulomb. Sir, in the third ball, here it is having 4 Coulomb and here it is having 5 Coulomb. So I can say they have transferred the charges in between, okay? They have shared the charges with each other. Could you please tell me what is the net charge over here? Sir, net charge over here is 5 plus 3 is 8. 8 plus 1 is, we say, sir, 9 Coulomb. So previously, initially, charge is 9 Coulomb. Finally, charge is 9 Coulomb. So means I can say charge remains, net charge of the system remains conserved. We say net charge of the system remains conserved. Net charge of the system remains conserved. No doubt, we say in this particular case, the balls will share the charge between each other. But when it comes to net charge of this bag of the system, that remains the same. Okay, charge can be transferred from one body to another body, but the net charge of the system remains conserved. We say Q initial is equal to, we say Q final. Net charge initially is equal to the net charge finally. This is what we call the conservation of the charge. Is that clear? Please tell me in the chats. Everyone means everyone. Is that clear, boys and girls? Yes, great. Crystal clear. Great. Now. Next. Okay, let's talk about this particular example. Here, I am saying that we have got this block, this box over here. This is a box. Inside this box, I am having this ball. It has plus 5 Coulomb charge. And there is one more ball, it has 2 Coulomb charge. Let's suppose I'm transferring the plus 2 Coulomb charge from this ball to this ball. And afterwards, I saw that on this ball, we say it is 3 Coulomb charge. Because see, 5 minus 2 is, we say how much? 3. So 3. And here, it was minus 2. When you give it to the plus 2, minus 2 plus 2, it will become 0. You see, here net charge initially is equal to net charge finally. Net charge remains conserved. Net charge remains conserved. Next, charge is quantized. Charge is quantized. Maximum number of students out there are having problem in understanding this concept. But let me give you the feel of this particular concept for once and all. See guys, let's suppose I have got over here a shop 1, okay? And this shop basically sells balls, cricket balls or something like that. And I went to the shop and I asked this shopkeeper, could you please give me the smallest ball which is available in your shop, or which is made by the company, the smallest ball in the entire world? He said, I'll give you this ball, this is the smallest. I said, no, smaller than this. He said, then take this one. I said, no, smaller than this one. He said, take this one. I said, no, smaller than this one. He said, take this one. This, very small. I asked him, give me the smallest ball than this one. He said, this is the smallest ball possible. We say, smaller than this one is not available anywhere in the world. So can I say this is the smallest ball possible, or smallest ball available? I can say it something like that. Yes. Now, I went to another shop. We say shop 2. And let's assume that this shop is basically selling. It sells, we say charge. Let's assume that it is selling charge. Okay. Now guys, if it is selling charge, I can say in this particular case, I asked this shopkeeper, could you please give me the smallest charge possible? He said, take this charge. I said, no, smaller than this one. He said, take this one. No, smaller than this one. Take this one. Smaller than this one. Sir, this one. Give me smaller than this one. He said, no, this is the smallest charge that is available in the entire world. Smaller than this one, you can't get anywhere in the world. So we say, can I write this as, this is the smallest charge possible. This is the smallest charge possible. Now guys, how much? I asked him, sir, what is the value of the smallest charge? He said, the value of this smallest charge is, we say, sir, charge on 1 electron. So we say it is charge on 1 electron. Okay. So charge on 1 electron is the smallest charge in the entire world. And how much is that? 1 electron is having the charge of 1.6 into 10 raised power minus 19 Coulomb. 1.6 into 10 raised power minus 19 Coulomb. Okay. So I asked him, can you give me the smaller than, guys, now tell me, if I am saying that 1 electron is the smallest charge possible in the world, sir, can I get E by 2? No. Why? Because smallest charge possible is 1 electron. Smallest charge possible is 1 electron, that is 1.6 into 10 raised power minus 19. It is not possible. Now guys, so I can say, listen to me very carefully. We say, I'll write over here, charges possible. Charges possible. Can I say 1 electron? Is this 1 electron possible? Is this 1 electron possible? Yes, you can get 1 electron. Sir, is 2 electrons possible? Yes, 1 and 1 means 2 electrons. Now guys, if I ask you, charge is not possible. Charge is not possible. If I ask you, give me E by 2, that is 0.5 electron, is that possible? No. Why? Because smallest is E. Sir, can you give me 2.5 electron? No. 2 electrons you can get, but 0.5 you cannot get. Can you get 3.75 electron? No. We said these are the charges which are not possible. which are not available in the world. What is available? 2 electrons. We say 3 electrons, 4 electrons, and so on. I can say n electrons. I can say n electrons where n is an integer. So charge possible is Q is equal to plus minus, it can be positive, it can be negative, plus minus n times of E. This is what we call the quantization of charge. Quantization of charge means charge is available in fixed amounts. It is not available in random amounts. Like if you go to the market, if you go to the shopkeeper and you ask him, give me 1 pen, he'll give you 1 pen. Give me 2 pens, he'll give you 2 pens. Give me 2.5 pens, he'll say, I cannot give you 2.5 pens. I can give you 2.5. How can I give you 0.5? So pens are available in fixed amounts. Now go to another shop. Get me rice. Give me rice. 1 kg, 0.5 kg, 3.5 kg. Rice is available in random amounts. We say pens are available in fixed amounts. Similarly, charge is available in fixed amounts. So charge is quantized. I'll write the same statement over here. We say, so charge is available in fixed amounts. Like 1 electron, 2 electron, 3 electron, 4 electron. So that is, we say Q is equal to plus minus n times of E. Plus minus n times of E. Okay? Where n is an integer, And so we say charge is quantized. Charge is quantized itself means charge is available in the fixed amounts. That's what I'm trying to say. Okay? So I can say charge is available in fixed amounts, charge is quantized, charge is available in, we say Q is equal to plus minus n times of E. Whatever you say, one and the same thing. Is this clear? Please let me know in the chats. Everyone means everyone with the fire emojis. Everyone means everyone with the fire emojis. All the people out there, guys. And if you have not liked the session yet, I would want you guys to hit the like button as soon as possible, ladies and gentlemen. Great. Now we have got a question over here. How many electrons are in 1 coulomb of negative charge? You guys are supposed to tell me how many electrons are present in 1 coulomb of negative charge over here. See guys, I'll simply solve this particular question with this equation. We say as we know, we say Q is equal to n times of E. Okay? Now here I can say n means number, n is number, n is equal to, we say Q divided by E. Yes. So I can say in this particular case, what is charge? See. It is saying how many electrons are present in 1 coulomb of charge, means charge is given as 1 coulomb. Charge is given as 1 coulomb. And E means charge on an electron. E is charge on an electron. E is charge on an electron. And how much is that? 1.6 into 10 raised power minus 19. So I can say in this particular case, guys, so this is 1 upon 1.6 into 10 raised power minus 19 coulomb. So 1 upon 1.6 is how much? We say 0.625. So it becomes, I'll write over here 0.625 into 10 raised power minus, and it goes in the numerator. 0.625 into 10 raised power 19. So I can write 6.25 into 10 raised power, we say, sir, 18. So these many number of electrons are present in what? We say 1 coulomb of charge. Let's take a look at the next question over here. Let's take, these are the basic questions. Yes. See guys, can a charge of 8 into 10 raised power minus 18. 8 into 10 raised power minus 18. 8 into 10 raised power minus 18. Coulomb be given to a body. Be given to a body. Guys, this is an integer. Don't get confused over here. Okay. This entire number, this is an integer. Now, we say can a charge of 8 into 10 raised power minus 18 be given to a body? Guys, see. I can say as. We say Q is equal to N times of E. If this N comes out to be an integer, then we can say yes, this much of charge we can give to a body. Because we know, sir, how much is the charge possible? That is Q is equal to N times of E, where N is an integer, So if N comes out to be integer in this case, means yes, we can give this much. Now guys, I can say in this particular case, N is equal to Q divided by E. So I can say, what is the value of Q in this particular case? That is 8 into 10 raised power minus 18 divided by, we say charge on an electron is 1.6 into 10 raised power minus 19, because charge here is given as this. Can we give this much of charge to a body? It is like, is this charge possible in the world? I can rewrite the question. Is this much charge possible in the world? How can we check? N is equal to Q by E. So if N comes out to be an integer, then we say yes. So in this particular case, this is minus 19, this is minus 18. So this will come out to be 5. 8 divided by 1.6 is 5. And 10 raised power minus 18, it goes over there. 10 raised power minus 18 into, we say 10 raised power 19. That is 10. So I can say 5 into 10 is, we say, sir, 50. So N is coming out to be 50, which is an integer. So I can say yes. I can say yes. Is this clear? Please tell me in the chats. Is this clear? Please tell me in the chats. Everyone means everyone. Give me the signal in the chats. Great. Great. Now guys, let's move on to the next topic. That is what we call the charging a body. That's what we call the charging a body. Okay. What are the different ways to charging a body? Video is buffering in between. I have another screen over here in front of me, which is definitely not buffering at all. You guys have, if you guys have, I guess, internet problem. So please refresh and it'll be fine. Okay. Now guys see. We have over here next topic, that is charging by friction. The first example in this particular chapter, with we started, is when I rub the comb with my hair, we say the comb gets charged. That is what we call the charging a body. Charging a body means occupying the charge on the body. Now, the first one is charging by friction. What was this? I was creating the friction over here. Okay. Now guys, listen to me very carefully. In this particular case, we say it is to charge a body. By a rubbing. It is to charge a body by rubbing. So basically, when you rub the two bodies and it gets charges is what we call the charging by friction. Now guys, see, listen to me very carefully. I have taken the example over here. Let's suppose I'll take a glass rod over here. This is the glass rod made of glass. Okay. And this glass rod is, we say, neutral. This glass rod is, we say, sir, neutral. Neutral means the amount of positive charge is equal to the amount of negative charge on the body. Positive, negative, positive. And I'm rubbing this glass rod with a silk cloth. Okay? So I'm rubbing this glass rod with a silk cloth, and this silk cloth is also neutral. Okay? This silk cloth is also neutral. So when you rub the glass rod with the silk cloth, you observe that negative charge is transferred from the rod to the silk cloth. This negative charge gets transferred from the rod to the silk cloth. Okay? And afterwards, finally, after rubbing, I'll write over here, after rubbing, I saw that if negative charge is transferred onto the silk cloth, we say now more negative charge is present onto the silk cloth. You see over here? And on this glass rod, what remains? We say, sir, positive charge. On the silk cloth, what is more? Negative charge. Can I say in this particular case, this became positively charged, and this becomes negatively charged? Because here only positive charge remains. Here, negative charge becomes more. So we say this becomes negatively charged and this becomes positively charged. Okay? Okay? Why rod is transferring the charge? Because it is the case of electron affinity. I say this has got more. This has the more tendency to retain its electrons, retain its negative charge. That's the reason. So that's why negative charge of this rod gets transferred to the silk cloth. So we say this becomes positively charged and this becomes negatively charged. This is basically, I can say in this particular case, charging by rubbing or charging by friction. Let's talk about the next one. Guys, is the volume perfect? Is volume perfectly fine? Okay. Now guys, next we have charging by conduction. I can say it is to charge a body. It is to charge a body by touching. Now I'm saying that you don't have to rub two bodies to charge them. But you have to just touch them. Now, what you are doing is that you are taking a positively charged sphere. Okay? This is a positively charged sphere. And this is an uncharged sphere or neutral. Net charge in this case is 0. When it comes to the neutral means net charge is 0. The amount of positive is equal to the amount of negative means. Let me just tell you over here. In this particular case. See guys. I say here, net charge I can say in this particular case is 0 if it is neutral. Here I can say net charge is positive, and in this particular case net charge is negative because this is negatively charged. Now let me show you over here. We said this is positively charged sphere and this is a metallic sphere I am taking over here. This is a metallic sphere. Okay, and you are bringing another uncharged sphere, and when you touch them, just touch them, don't rub them, just touch them, and when you touch them, you saw that charge gets transferred from this sphere to this sphere. Now we say some charge remains over here and this also becomes positively charged. We say this becomes positively charged. Okay, and guys, see, I'll write a point over here. If the spheres are identical, okay, means if the two spheres are made of same material, same size, identical, okay, then charge is shared equally. Okay, If I am saying this is having the 10 coulomb of charge, it will give 5 coulomb to this and 5 coulomb will remain over here. This is when we say when charges, when spheres are identical. Identical means same size and same material. It is made of same size and same material. Now see guys, let's suppose we have got a sphere over here. It is having 4 coulomb charge and this is another sphere. It is having 2 coulomb charge. When you touch them with each other, what will be the finally charge on this sphere? What will be finally charge on this sphere? Because we know when two metallic spheres are touched with each other, conduction will take place. Conduction means sharing of this charge. So in this particular case, guys, see, I will tell you. We say, what is the net charge initially? Net charge means 4 plus 2 is, we say, sir, 6 coulomb. Don't you think that charge of the system remains conserved? Yes, sir. So I can say finally also net charge should be, we say 6 coulomb plus 6 coulomb. Since the two spheres are identical, okay, this is the case of identical spheres. I'll write over here. Identical spheres. Since the two spheres are identical, I can say in this particular case, half of the charge it will take, half of the charge it will take. So we say plus 3 coulomb and this will be also, we say, plus 3 coulomb. 3. Yes. Now the question is, I will be showing you the questions on this one also. Guys, see, if the two spheres are not identical, what if the two spheres are not identical? They are not made of the same size. They are not made of the same material. In that case, see guys, important one. This is important. If you have got a sphere over here, charge on this sphere is, let's suppose, Q1. Radius of this sphere is, let's suppose, R1. Okay. And I am saying this is another sphere over here. It has radius R2. Okay. It has radius R2. Different radius they have got. They are not identical. And charge on this sphere is, let's suppose, Q2. Here, both are having the same radius and they are identical. And in this particular case, we say different radius. And if you touch them or if you connect them by means of wire, that is one and the same thing. In this case, let's suppose how much will be the charge on first, how much will be the charge on second. So we say, let's suppose this is Q1, we have to find out Q1 and we have to find out, we say, sir, Q2. I will show you the questions on this one also, but later on. Please, as of now, you just remember. Now see. We say in this particular case, the value of this Q1 will be Q1 dash. It will be R1 upon R1 plus R2. R1 is the radius of first sphere. R2 is the radius of second sphere. Then we say multiplied by Q1 plus Q2, charge on first, charge on second. Similarly, you have to find this Q2. Similarly, this Q2 dash will be R2. Here it is R1. Here it is R2. Then we say R1 plus R2. Rest is same. We say Q1 plus Q2. So this is the charge on these two spheres when they are not identical. If they are identical, then they will share equal charges. Please tell me in the chats if this is crystalline clear. Everyone means everyone. Everyone means everyone. And guys, if you have not liked the session yet, I would want you guys to hit the like button. Make it 1000 right now. I'll count to 10 seconds. Make it 1000 right now. Great. Can JEE students watch this? Yes, everybody can watch this. Okay. So, I am saying that if you have got the two spheres which are not identical at all, in that particular case, that they will share the charges with each other, okay? But these charges are not equal. Oh, so what is the value of Q1 over here? This is the value of Q1 and this is the Q1 dash, and this is the value of Q2 dash. Okay? Great. Now guys, next we have over here the third method. Wasim sir in the chats from Unacademy NEET English. How bilya? Now guys, let's take a look at the third one. That's what we call the charging by induction. First, we rub the two bodies, okay? Then we touch the two bodies. First one was charging by friction. Then we have charging by conduction. Third one is, we say, charging by induction. Third one is charging by induction. Now guys, in this particular case, we say it is to charge a body by bringing them close to each other. It is to charge a body by bringing them close to each other. Like I have taken the example over here. Guys, I would want you to focus. Let's suppose you have got a rod over here which is positively charged rod. This rod over here that I have taken is positively charged. I can say this is positively charged. Okay? And I'm bringing this positively charged rod. Close to the sphere. Okay? And this sphere over here is neutral. Neutral means the amount of positive charge is equal to the amount of negative charge present over here. What do you think? What is going to happen? Sir, this positive charge will repel the positive charge of the sphere, because we know positive repels. Okay? So we say, I don't want to reply him. Please tell him to go. Tell him not to disturb over here. He's already done with his lecture. Okay, now he is disturbing me. Go. So we say, when you bring this positively charged rod near to the sphere, we say this positive charge of the rod will repel the positive charge of the sphere. So we say on this sphere, positive charge gets occupied on this side, another side. Negative charge will be attracted towards the rod, so it will be occupied from this side. Okay? Now, my dear friends, in this particular case, you'll do this earthing over here. Okay? This is earthing. What does this actually mean? We say earthing means connecting a wire with the ground. We say Earth is considered to be the ocean of electrons. So we say now this Earth will send the electrons over here. We say this Earth will now send the electrons over here. Electrons have got negative charge. Okay? And if this Earth sends the electrons negative charge, so we say now it will neutralize this part. Guys, see. Don't get confused over here. We say this side of the sphere will get neutralized. If this is having positive charge over here, Earth is sending the electrons, means negative charge. We say this portion gets neutralized. Okay? So from this portion, net charge is 0. So what remains onto this sphere? We say, sir, positive charge. What remains? Sorry, negative charge. So now if I'm taking this sphere over here, it will become negatively charged. What I'm trying to say is that we are taking a positively charged rod and I am taking this close to this particular sphere, and we say positive charge gets repelled and it will be occupied on this side. Negative charge gets, we say, attracted and it will get occupied on this side. Then we'll do the earthing over here, connect it with the ground. Earth is considered to be the ocean of electrons. So it will send the electrons, and those electrons, that negative charge will neutralize this part. What remains onto the sphere is, we say, sir, negative charge. So it will become negatively charged. So this is the charging by induction method. Guys, is this clear till over here? Please let me know in the chats. Everyone means everyone. Okay. Now we are starting the Coulomb's law. I would want you guys to tell me in the chats if everything is crystal clear and sorted. Great. Now guys, let's move on to the Coulomb's law. Guys, see, what does the Coulomb's law actually say? Listen to me very carefully. We say, let's suppose if we have got over here a charge that is Q1, and let's suppose if we have got another charge over here that is Q2, and I'm saying that this charge Q1 is positive, this charge Q2 is also positive. We have got the two positive charges. Guys, tell me, don't you think that, sir, positive charge repels positive charge? Yes. This positive charge will repel this positive charge with a force F. If I'm saying they are repelling each other, repelling with what? Repelling with the force. They are applying the force. Now this positive charge will repel this positive charge with what? We say, sir, force. Now I'll write since the two charges are repelling each other, since the two charges are repelling each other with a force called Coulomb's force. So means they are applying the force on each other with what force? We say, sir, Coulomb's force. That force is given by the Coulomb. And how much is that force? Guys, see. If I say I'll place the bigger charges over here, bigger are the charges, we say big will be the force. They are applying more force. Smaller charges will apply less force. Bigger charges will apply the large force. So can I not say this force between the two charges is directly proportional to the magnitude of the charges? Yes. So more is the magnitude, more will be the force. Less is the magnitude, less will be the force. And if we place these two charges very far from each other, so we say force will decrease, they will apply less force. If you bring them close, we say force will increase. So can I say this force is inversely proportional to, we say, R square? Yes. If you increase the distance, we say force will decrease. If you decrease the distance, force will increase. Now if we combine the two equations, we say combining the two equations, I can simply say in this particular case, so F is directly proportional to Q1, Q2 divided by R square. Now, I would want you guys to replace this proportionality with a constant. We say replace the proportionality with a constant. Replace the proportionality with a constant, that is K. So can I write this particular equation now? That is F is equal to, that is K. Q1 Q2 divided by R square. So from now onwards, you'll remember that if you have got the two charges, they are applying the force on each other. And how do we find that force? We say K Q1 Q2 by R square, where R is the distance between the two charges. And what is the value of this K? I can say value of this K is 1 by 4 pi epsilon naught. Sir, what is this epsilon naught? This is what we call the permittivity of free space. Please wait for some time. After some time, I'll explain this. Okay. And this epsilon naught is called permittivity of free space. Okay. And value of this epsilon naught is 8.85 into 10 raised power minus 12. So we say it is 8.85 into 10 raised power minus 12. And then we say Coulomb square upon Newton meter square. This is the value of epsilon naught. Now guys, now see. If you put this epsilon naught over here, if you put its value over here, then solo 1 by 4 pi, pi is 3.14. Epsilon naught is 8.85 into 10 raised power minus 12. Then solo, we say K will come out to be 9 into 10 raised power 9. We say Newton meter square upon Coulomb square. This is the value of K, okay, in general. And in particular, if we talk about the epsilon naught, this is the value of epsilon naught. So is this crystalline clear? So from now onwards, you'll say that if we have got the two charges, the force between the two charges is K Q1 Q2 by R square. As simple as that. As simple as that. As simple as that. Okay. Okay. And if someone asks you to plot the graph between force versus R, F versus R, so we say force versus R. So since force is inversely proportional to R square, so I can say the graph will be something like this. Okay, the graph will be something like this. This is graph between F versus R. Now guys, next. I would want you guys to focus over here, okay? I would want you guys to focus exactly over here. Everyone means everyone. See guys. This is basics. I'm taking you to the class 11th. Everyone over here. Let's suppose, my dear friends, I am saying that I have got a block over here. This is a block that I have over here. And on this block, we say two forces are acting. We say, sir, this is F force. Let's suppose it's 10 Newton. This is F force, that is 10 Newton. Same two forces. If you have got these two forces and angle between these two, total angle, this is given as 90 degrees. This is given as 90 degrees. Remember, my dear friends, if this is 90 degrees, we say net force in this case is, we say, sir, F net in this case is root 2 of F. Guys, please directly remember this. If I tell you at some point of time, remember this, remember that, you'll have to remember that. Okay, you'll have to agree with me. Okay. Now guys, see, we say, sir, how do we calculate it? This is the formula. F net is equal to under root of F1 square plus F2 square plus 2 times of F1, F2 cos of theta. Here, I am saying if you have got the two vectors, then angle between the two vectors is 90. Resultant will be root 2 of that vector, root 2 of F. If this is X, resultant will be root 2X. Now, if you have got the two forces acting on the block, okay, and angle between the two forces 60 degrees, remember its resultant will be, I say a root 3F, This is when angle is 60. If you have got the two forces F, and angle between these two forces is 120 degrees. Remember, in this particular case, resultant will be F only. Net force in this case will be what? That is F only. And one more thing. If you have got a block over here, on this block, two forces are acting, F and F, in the same direction. In the same direction means here theta is equal to 0 degrees. They are parallel. Here you will directly say F plus F is 2F. Resultant will be 2F. If you have got the two forces, okay, acting on this block, which are in the opposite direction, here theta is equal to 180 degrees. Remember guys, net force in this case will be 0. You have to remember this slide directly. If angle between the two vectors is 90 degrees, resultant will be root 2f. If angle between two vectors is 60 degrees, resultant will be root 3f. If angle is 120, resultant will be f. If angle is 0, resultant is 2f. If angle is 180, resultant will be net will be 0, because this will cancel with this one. Yes. Next, what if F1 and F2 are unequal? Means here I am saying F and F are equal, then you are saying this is the resultant. If F1 and F2 means this force and this force are not equal, in that particular case, what will you do? You will directly use this general formula. That is, if I say this is F1, this is F2, angle is 60, under root of F1 square plus F2 square plus 2 times of F1, F2 cos of 60. This is the actual formula which you need to in that case. Okay, please don't get confused. Listen to me. Whatever I say over here, just follow that blindly. Okay. One more pattern of questions that we have over here on the screen. Guys, see. Let's suppose I have got a square over here. I have got a square over here. Is this clear till over here? Yes, basic formula can be used anytime. You can use this formula. With the help of this formula, you will get this answer, this answer, this answer, this answer, and this answer. Give me the signal in the chats if everything is crystal clear and sorted. Everyone means everyone. Everyone means everyone. Now guys see. Let's suppose we have got a square over here. At this corner I have placed plus q, here it is plus q, here it is plus q, here it is plus q. These are the 4 charges at the corners. What is the net force at this charge which is placed at the center? You guys are supposed to tell me the net force placed at the center charge. Guys, see, this plus q will repel this plus q, something like this, with a force F. Okay. This plus q will repel this plus q with a force F in the opposite direction, because positive repel. This plus q will repel this plus q in this direction with a force F. This plus q will repel this plus q in this direction. Don't you think that this gets cancelled with this one? This gets cancelled with this one. So we say in this particular case, net force comes out to be equal to 0. Okay. Let's talk about this one. Sir, this positive charge will repel this positive charge in this direction with a force F. This positive will repel this positive in this direction with a force F. This positive will repel this positive in this direction with a force F. Let me make it over here. One force is something like this, another is something like this, another is something like this. Sir, are these 3 forces equal? Yes, because distance between these two is equal to between these two is equal to between these two, and charges are also similar. Now, always remember this is angle is 120. This angle over here will be, in case of this triangle, will be 120. If this is F, this is F, and this is F. Now, could you please tell me what will be the resultant of this force and this force? So resultant of this force and this force would be something like this. That will be F only. Why F only? Because I told you, if the angle between the two vectors is 120 degrees, resultant in that case is F only. So I can say here, in this case, resultant will be F only. Now, You have basically mentioned the resultant of this one and this one. So that is F in the upward direction, and you have got F in the downward direction. Now this F gets cancelled with this one. So I can say net force will be 0. Okay. Similarly, net force on this charge will be also 0, okay, using the same logic. Similarly, net force on this charge will be equal to 0 over here. Means. Let me write over here. If identical charges are present at every single corner, guys, first thing is, if you have got the symmetrical figures, triangle, square, pentagon, hexagon, okay, so if identical charges are present at every corner. Identical means similar. Plus Q, here also plus Q. Here also plus Q. Here also plus Q. Then, whatever be the charge at the center, net force on that charge will be 0. Okay? Net force on that charge will be 0. Okay? You say, sir, if I want to do this over here, we say in case of pentagon, we use this logic. Okay? We use this logic. Okay, it has some rules which are a bit complicated. We don't have that in our syllabus. That's why we say directly net force in case of a symmetrical figure at the center charge will be 0 if identical charges are present at every single corner. Like here, plus Q, plus Q, plus Q, plus Q, plus Q, plus Q. At the center charge, net will be 0. Okay, okay. And one more thing, sir, if I place minus Q over here, then I cannot say net force will be 0 over here. So we can simply say net force on the center charge will be 0. What is the condition? If identical charges are present at every corner, then net force will be 0. Let's talk about this one. Let's suppose we have got a square, plus Q, minus Q, minus Q. And you have to tell me what is the net force on this plus Q at the center. See guys, this minus Q will attract this towards itself with a force F. This minus Q will attract it towards itself with a force F. This plus Q will repel. This plus Q will repel this with a force F. Okay. Plus Q will repel plus Q. And this plus Q will repel this plus Q with a force F. Now guys, tell me one thing. These two forces F and F are in the same direction. Can I say in this direction F plus F will be 2F? Because I told you, if the two vectors are in the same direction, it will be 2F. So this F and F will be also over here, that is 2F. So here it is 2F. Here also it is 2F. And angle in case of square over here is, we say 90 degrees. Whenever you have the angle 90 degrees between the two similar vectors, so could you please tell me what is the resultant? Resultant is, we say root 2 of. Guys. If this is F, it will be root 2F. If this is X, it will be root 2X. If this is 2F, resultant will be root 2 of 2F. So I can say that will be 2 root 2 into F. 2 root 2 into F. Because when the angle between the two vectors is 90 degrees, resultant in that case is root 2F. Now what is this F? F is the force between the two charges, any two, between these. How can we find the force between the two charges? Guys, let's suppose if I say this side is A. Always remember, this is half of the diagonal. Half of the diagonal will be A divided by root 2. Half of the diagonal is A by root 2. And full diagonal, remember this, if this is a square, side is A, we say diagonal will be A root 2. Half of the diagonal will be A divided by root 2. Keep that thing in your mind. Now guys, see, I'll make you understand this. So I can say, we can write this further as 2 root 2. Force between these two charges, or these are one and the same thing. So that will be, sir, K Q1 Q2, that is K Q square divided by distance between them. Sir, K Q1 Q2 by R square. So I can say R in this particular case is A by root 2, we say whole square. So further I can write over here, this will be a square by 2. So 2 into 2 becomes 4. 4 root 2. Then we say k q square divided by a square. Okay. Okay. Is this clear? Please tell me in the chats everyone means everyone. Please let me know in the chats if everything is crystalline clear and sorted. Next question we have on the screen. Next question we have on the screen. It says that 3-point charges plus q minus q are placed at the corners of an equilateral triangle. We say plus q, and we say minus q. Of side A, another charge plus q, capital Q, is placed at the centroid. Find the net force on this center charge. We have to find the net force on the center charge. Guys, see. We say this minus q will attract this plus q towards itself with a force F. This plus q will repel this plus q. We say with a force, we say, sir, F. Okay. And we say this plus q will repel this plus q with a force, sir, F. As I told you, in case of the triangle, this angle is 120 degrees. Now, could you please tell me, sir, this resultant of this one and this one, angle between these two is 120. Don't you think resultant of this one and this one will be F only? Yes. So here, in this direction, it is F. And resultant of this one and this one will be also F in this direction. So that is also F. Now this F and F are in the same direction. So can I say net force in this case will come out to be, that is 2F. Because F and F, 2F. Guys, resultant of this one and this one is F. So already here is one F. Another F is because of this one and this one, that is 2F. Now I can say this is 2. Now this F, how can we write this F? See guys, F means force between either be these two charges, between these two charges. Okay. How to find the force between these two charges, sir? K, I'll write, sir, K. Q1, that is this charge. Q2, that is this charge. Capital Q, small q. Divided by distance between them. Guys, in case of equilateral triangle, if this is A, always remember, from centroid to corner, this distance will be A by root 3. Always remember, this distance will be A by root 3. So I can say this is A divided by a root 3 and this is whole square. Okay. And further, I can say this is 2 and then I'll write over here, this is KQ, this Q upon, and this will be A square. And guys, A square by 3. Now that 3 will go into the numerator and 3 into 2 will become 6. Okay. So 6KQQ by A square. Okay. Next, could you please tell me what is the resultant, what is the answer of this particular question you have? You have got in this particular case over here hexagon. Guys, tell me in the chats, is this clear? Everyone means everyone. Is this clear? We'll have more questions. Chill. I'll explain it once again. Guys, see. See, what I'm trying to say in this particular case is, see. You have got this charge over here, and there is the center charge plus Q. We said this positive charge will repel this positive charge in this direction with the force F. This negative charge will attract this positive charge with the force F. This positive charge will repel this positive charge with the force F. Because negative attracts positive, positive repels positive. Now, these are the three forces over here. I'll make these three forces over here. Sir, this is F. This downward, sir, F. And this we say, sir, this is also F. Okay, yes. Now guys, we say if this is F and this is F, can I not say in this particular case, sir, in case of this triangle, this angle will be 120. Now, if angle between this force and this force is 120, what will be the resultant of this force and this force? See, resultant of this force and this force will be, sir, what? That will be F. Now, already from this side you have got this F and this is the resultant. Now, this F plus this F is how much? Now, you have got in this direction two forces, F and F. So, that is 2F. That is what I mentioned over here. And what is this F? F is the force between either this and this is F, between this and this is F, between this and this is F. And how do we write that? This distance is A by root 3. Sir, F will be K Q1 Q2 by R square. That is what I mentioned over here. Is this clear? Let me increase the volume over here. Just a second. Okay. Guys, if you have not liked this session yet, I would want you guys to hit the like button as soon as possible. Everyone. Now guys, let's move on to the next question. Yes, this one. Guys, see. In this particular question, you have got, we say minus 2 Coulomb charge on this corner, 4 Coulomb charge, minus 2 Coulomb charge, and you have got 2 Coulomb charge. Okay. You are supposed to find the net force on this 2 Coulomb charge. You are supposed to find the net force on this 2 Coulomb charge. Guys, see. Net force on this 2 Coulomb charge because of the rest of the charges. This side is given as 2 meters. If this is 2, how much will be the diagonal? That is 2 root 2. Okay. You have to find the force on this charge. See guys, we say on this charge, this negative charge will attract this positive charge towards itself with the force F1. This is the force F1 between this and this. Let's find this force F1 over here. We say F1 is equal to, that is K Q1 Q2 by R square. Sir, K means K, Q1. This charge, Q2, this charge, 2 Coulomb. Coulomb is a unit. So how much is the value magnitude? That is 2. Another one is also 2. Guys, if it is mentioning minus 2, when you are finding the magnitude of the force, consider negative charge also as positive. So 2 into 2 is, we say, sir, 4 divided by. Distance between these two is, we say, sir, 2 meters, so 2 square. So we say 2 2s are 4, 4 will cancel, so this is K. So this force F1 is coming out to be K. Now guys, we say this negative charge will attract this positive charge towards itself with a force F2. Let's find the value of F2. I can say F2 is K, we say Q1, Q2 divided by R square. And then I'll write over here, this is K. Value of Q1 over here is 2, value of Q2 over here is 2. So this is 2, another one is also 2 divided by. Distance between these two is how much? That is 2 square, because it is square. So 2 2s are 4, 2 2s are 4, and this is also K. So means this F2 is also K. Now this 4 Coulomb will repel this 4 Coulomb because both are positive with the force F3. Let's find this F3. F3 is K, Q1. Q1 is 2, Q1 is 2, Q2 is 4, Q2 is 4. Force between this and this. Divided by, what is the distance between these two? That is 2 root 2. This is the diagonal. So I can say 2 root 2 whole square. So I can say, guys, see. 2 into 4 is 8. So we say K into 8 upon 2 square is 4. And this root and square will cancel. So 4 into 2 will again be 8. So this 8 and 8 will cancel. This is also K. Now. We say all the three forces are K. So first let me draw this F1 over here. Sir, F1 is in this direction. And its value is K. And this F2 is in the downward direction. It is also, sir, K. And this F3 is in this direction. I can say this is also K. This is also K. Guys, between this and this angle is 90 degrees. Between this and this angle is 90 degrees. When you have the angle between the two vectors as 90 degrees, understand one thing. When you have the angle between the two vectors as 90 degrees, always remember that I have told you the resultant of this and this will be root 2K. If this is K, this is K, this will be root 2K. Now you have got this vector and this vector. In this direction you have got K, and in the downward direction you have got root 2K. Could you please tell me what is the resultant of this one and this and this? You say, sir, root 2K is bigger than this one. So you always say bigger minus smaller. So here net force is, we say root 2K minus K. So here K will come out. So this is a root 2 minus 1. This is root 2 minus 1. Okay. So this is the net force. This is the net force on this plus 2 Coulomb charge. Is this crystalline clear? Please tell me in the chats. Everyone means everyone. Let's move on to the next question. Let's move on to the next question. Great. Now guys, take a look over here. We have to find the net force on this charge. See guys, these charges at the corners are not identical or similar. So we cannot say the net force at the center charge will be 0 because the charges are not similar. Okay. Now, I would want you guys to focus over here. Sir, this negative charge will attract this positive charge. This negative charge will attract this positive charge. Force F, this is force F. This negative charge will attract this positive charge with the force F. This positive will repel this positive with the force F. This positive will repel this positive with the force F. This positive will repel this positive with the force F. Okay. Now, in this particular case, can I say this F and F is 2F in this direction? Yes. Can I say this F and F is 2F in this direction? Yes. Can I say this F and F is 2F in this direction? Yes. Guys, always remember in case of this hexagon, this angle will be 120 degrees. This angle will be 120 degrees. If angle between this vector and this vector is 120, don't you think that, sir, resultant of this one and this one will be along this and that will be also 2F? Because if you have F and angle is 120, resultant is F only. Now, this 2F and 2F are in the same direction. Okay? This 2F and this 2F. Now, this 2F plus 2F is how much? We say, sir, net in this case will be 4F. This is the answer. And F you can write as K Q1 Q2 by A square. Because here, this is A. 4F is the answer over here. Next, let's talk about this question. This is important also. Guys, see, I would want you guys to focus over here. A certain charge Q is divided into two parts, small q and q minus q. It says that we have got a charge over here. It is divided into two parts. We say q and we say capital Q minus q. Okay, this is one charge and this is another charge. Okay, how should q and q be divided so that q and q minus q are placed at certain distance, experience the maximum electrostatic repulsion? It says that basically, how should we divide these two charges? Means, how should we divide this charge? What should be the value of this q? So that repulsion, electrostatic repulsion, force between this charge and this charge should be maximum. What should be the value of q so that force between the two should be so that force between them should be maximum. Guys, see. Please keep your mind 100% over here. I would want you guys to focus. What should be the value of this small q, or how should we divide this charge so that maximum force should be between these two? Now guys, we know if this charge and this charge are placed at the distance, let's suppose r, they will apply the force on each other. Let's suppose this is F force and on this it is F force. Okay. Now, could you please tell me the force between the two? We say, sir, force between the two is F is equal to, that is K, Q1, Q2, that is Q1, and Q2 is this charge, that is Q minus Q, divided by distance between them, that is R square. First, let's find the force. Now guys, always remember that, please, if I say at some point you have to remember it. Okay? If I say this force should be maximum, guys, if I say this force should be maximum, then if directly remember this is the concept of maxima and minima, which we study in the differentiation integration. I'll show you over here. If the force is maximum, then we say the value of df divided by dq should be equal to 0. Directly remember it. If I say I have got any quantity y, okay, if I say I have got any quantity y, and I want you guys to basically make the value of y as maximum, I want the maximum value of y. Sir, maximum value of y is when dy by dx is equal to 0, when differentiation of this y with respect to x will be 0. Similarly, if you want this force to be maximum, then df by dq should be equal to 0. Okay? If there is any student who is not able to understand this question, he can skip it. Skip it. Not a problem. Okay? So now I can say df by dq should be 0. What is df by dq? Differentiation. Let's do the differentiation of this one. Guys. First I can write this as, this will be k divided by r square, k by r square. And q into q is q minus q into this q is q square. Now let's do the differentiation of this one. So I can say df divided by dq means a differentiation of this force with respect to the charge. Will be, guys, k by r square is constant, so take them out, k by r square. And now differentiation of small q minus this. If I am saying it is like we say 2x minus x square. Here it is 2 is q, x is x. You have to do the differentiation with respect to x. What will you say? Differentiation of this term will be 2 minus differentiation of x square will be 2x. Similarly, differentiation of q and this capital Q and small q, it will be q, because we are differentiating with respect to this over here. Okay, and then we say minus differentiation of q square will be 2q. And if we have to find the maximum value of force, we make it equal to 0. Because if you want the force to be maximum, then directly remember dF by dQ should be 0. This is the value. Okay. Now guys, let me write it on the next slide. So I can say this, guys, k by r square. I'll write over here k divided by r square into we say q minus 2q, capital Q minus 2q is equal to 0. Multiply it over there, it will become 0. So q minus 2q is equal to 0, and take it over there. So q is equal to minus 2q. So q will be minus q divided by 2. Okay, sorry, it goes over there, it becomes plus. So q is equal to 2q and q is equal to q by 2. Is this clear? Yes, plus. Is this clear? If there are students who are not able to understand this, please skip it. Is this clear? If you want any quantity to be maximum, then its differentiation should be equal to 0. Remember it directly. Yes. Now guys, let's move on to the next concept. That is what we call the vector form of Coulomb's law. Guys. Previous one. That if you have got the two charges over here, Q1 and Q2. If you have got the two charges over here, Q1 and Q2. We know, sir, these two charges apply the force on each other. Okay, that is F and this is F. Okay. My dear friends, if I ask you how much is the force between the two, you say, sir, F is equal to K. We say Q1, Q2 divided by R square. Sir, this is what we call the scalar form, which gives you the magnitude only, how much the force is acting. But when it comes to the vector form, this is the vector form. Guys, see, F is equal to K, Q1, Q2. Then we say R vector divided by, we say, sir, R cube, divided by magnitude of R cubed. Sir, when do we have to use this and when do we have to use this? If I say, guys, please. If I say I have got a charge over here 2 Coulomb. I have got another charge over here 2 Coulomb. Distance between them is 2 meters. I am asking you, please tell me the force between the two. What will you say? F is equal to K, Q1 is 2, Q2 is 2, divided by R square, it is 2. So it will be simply, that will come out to be K. You use the scalar form directly. What if I give you the question, something like this? You have got over here a charge minus 2 Coulomb, plus 2 Coulomb, and distance between them is given in the vector form. So here, we say in these types of questions, we say here, we use the vector form of Coulomb's law. Here we use the vector form of Coulomb's law. Guys, see, what is the vector form? We say as. When it comes to the vector form is K, Q1, Q2 divided by R cube into R vector. This is the vector form. Now guys, tell me one thing, everyone over here. Can I say in this particular case, you have got one charge, this is Q1, you have got Q2, and R is the vector between these two, and this is given in the vector form. Here, this R is given as, I can say 3I cap plus we say 4J cap. 3I cap plus we say 4J cap. Can I not say, guys, this is the R vector. And always remember, if you are given a vector, let's suppose I am saying I have given a vector over here, A is equal to 3I cap plus 4J cap. Sir, how do I find its magnitude? We say magnitude of A will be, guys, simply, we say under root of whatever is mentioned over here with the I, that is 3 square, plus whatever is mentioned with the J, that is 4 square. It's this coefficient. So this will be simply 3 square is how much? 9. 4 square is 16. So root 25. So similarly, if I ask you to find the magnitude of R, what will you say? Under root of this 3 square plus we say, sir, 4 square. And that will be under root of 3 is 9 plus 4 is 9 plus 16 is 25. This is 25 and this will come out to be 5. Now, what will I write over here? I can say, so force will come out to be, that is K. What is the value of Q1 over here? That is -2. Sir, when you have the vector form, in that particular case, you will have to mention this Q1 or Q2 along with the sign. When you have got the scalar form, you ignore the sign, you mention all positive. But here, I can say, what is the value of Q1? That is -2. I'll write -2. What is the value of Q2? That is +2. So I'll write +2. And then R vector. What is R vector over here? That is given as 3I cap, we say plus 4J cap. And then we say whole divided by R cube. This is magnitude of R. So I can say this will be 5 cube. Now, this force will come out to be 2 into 2 is 4. Okay. Now, guys, this 4 into 3 is 12. 4 into 4 is 16. So it will be, take this minus out, minus K. 4 into 3 is 12 I cap. Then we say plus 4 into 4 is 16 J cap. Okay. Then we say divided by 5 cube is 125. This will be the answer. See, I cap, J cap, this is the vector form. This is the force over here you got in the vector form. Is this clear? Now, if there is a student who is confused, what is this I cap and J cap? Guys, see. This is we study in the vectors. If I say I have got a block over here, I am applying the force on this block and this force is in the X direction, positive X. So I can write over here Fi cap. Because this I cap tells us that force is in the X direction. Force is acting along X axis. Because we say this is X axis, this is Y axis. This is positive X, this is minus X, this is minus Y. If I say force is acting in this direction, you can say minus Fi cap. So it means force is acting in the negative direction. If I say force is acting something like this, means this vector is along J direction, along Y direction. So J is the unit vector which is along Y axis. IJK tells us the direction of the vectors. Everyone means everyone. Please tell me in the chats if everything is crystal clear and sorted. Okay. Relative permittivity. Now guys, see. What does a relative permittivity actually mean? Listen to me very carefully. Let's suppose I have got the two charges over here, Q1 and Q2. Okay. And distance between these two charges is R. And these two are kept in a box in which only air is present. Okay. These two are kept inside a box in which only air is present. Okay. Now, could you please tell me what is the force between the two? Could you please tell me what is the force between the two? You say, sir, force between these two charges is F is equal to K Q1 Q2 by R square. Sir, what is K? We write K as 1 by 4 pi epsilon naught. Guys, when you have air, when you have vacuum, at that point of time, you take this epsilon naught. That's why we call it the permittivity of free space. So this basically tells you the force between the two charges in air. And then you write Q1, then you write Q2 divided by distance between these two is R square. Cool? Yes. And what is the value of this epsilon naught? Sir, epsilon naught is 8.85 into 10 raised power minus 12. We know its value. Now, let's take the same two charges and we say, place these two charges in a medium. Let's suppose this is water over here, okay? Water or any other medium. And I'm asking you, tell me the force between these two charges. You say, sir, force between these two charges in a medium is 1 by 4 pi. Shall I take epsilon naught or something else? Sir, we take epsilon naught in case of air. But when it comes to the medium, here, we take, we say, I'll write epsilon of this medium. Sir, what is the value of this? I don't know. Sir, what is the value of epsilon naught? I know it. I don't know this. Okay, nobody knows. So then we write, sir, we say Q1, Q2 by R square. Let's call this as equation second. And let's call this as equation first. Okay. This is force in air. Now, I would want you guys to divide equation first and second. I would want you guys to divide equation first and second. Now, how can you divide this equation first and second? I'll write over here. That is force in air divided by force in a medium. That will be. Here I'll write 1 by 4 pi epsilon naught. And then I say Q1, Q2 by R square. And divided by 1 by 4 pi epsilon m. Then we say Q1, Q2 by R square. Now, in this particular case, don't you think that this and this will cancel? And this 4 pi will cancel. So, force in air divided by force in medium is equal to, I can say 1 by epsilon m, 1 by epsilon naught upon 1 by epsilon m. So, it will be 1 by epsilon naught upon 1 by epsilon m. Take it over there. So, it will be epsilon of m divided by epsilon naught. I'll write over here. Force in air divided by force in a medium is equal to, we say epsilon of m divided by epsilon naught. Guys, see. Now focus over here. We said this epsilon m by epsilon naught, this is what we call the ER. This is what we call the relative permittivity. When you basically divide epsilon naught with epsilon m, it is what we call the ER. Now, can I say, so I can write over here, this is force in air divided by force in a medium will be equal to ER. Yes. Now, I'll write the same equation over here. Take this ER over here, take this FM over here. So, can I say this FM will be, take the ER over here, this will be force in air divided by ER. I can say where ER is called relative permittivity, where ER is called relative permittivity. Now guys, I would want you guys to focus over here. If I say, if you have to find the force in a medium and you know the value of relative permittivity, then you find the force in air divided with the relative permittivity, you will get the force in medium. See. Can I say, so ER helps us to find the force in any medium. Sir, how? Because if you have to find the force in any medium, you divide the relative permittivity over here, you will get the force in a medium. Now, sir, why do I need the help of ER to find the force in a medium? I'll directly use this formula, 1 by 4 pi epsilon Q1 Q2 by R square. I am asking you, do you know the value of EM? Sir, no. If you don't know the value of EM, how can you find the force in this medium? Sir, can you find the force in free space? Yes. Why? Because do you know the value of epsilon naught? Yes, I know the value of epsilon naught. That is the reason we introduced the concept of relative permittivity. Now, if I say, relative permittivity of this water ER is 81. For every medium it is given. It is 81. Can you tell me how much is the force in water? I'll say force in water. Guys, can I say that will be force in water is equal to, force in medium is equal to force in air divided by relative permittivity of water, that is 81. So I say force in water has been decreased by 81 times as compared to the force in free space. So relative permittivity tells you the force in any medium if you know the relative permittivity of that medium. Please tell me in the chats this is crystal and clear. Guys, everyone, I need the signal from every single student. Everyone means everyone. Great. So I can say ER, relative permittivity, is something which helps you to find the force in any medium, provided if you know the relative permittivity of that medium. Like for water, relative permittivity is 81. You can say force in air divided by 81. Next. Also. Guys, see. Also, can I say in this particular case, guys, this EM by E naught is ER, as EM divided by E naught is equal to ER. So here I can write this EM will be simply, take it over there, that will be E naught into ER. Means, if you know the permittivity of, relative permittivity of water, that is 81, and you know the permittivity of free space, yes, multiply these two, you will get the permittivity of water. So relative permittivity also helps us to find the permittivity of a medium. I am saying like for water it is 81. So 81 multiplied by epsilon naught gives you the permittivity of water. So I can say it also helps us to find, the permittivity of any medium. I hope this point is also clear. I hope this point is also crystal and clear. This was the question which was asked in NEET 2020 on the relative permittivity. It says that when air is replaced by a dielectric medium, guys, dielectric relative permittivity has one more name. That's what we call the dielectric constant. Okay. So dielectric medium of force constant K. Then the maximum force of attraction between the two charges separated by a distance is. It says that if we have got the two charges, that is Q1 and Q2, they are placed in air at r distance. Okay. Now, okay. Now, if we replace this air with a medium, and place these two charges, Q1, Q2, if we replace this air with a medium which has the relative permittivity value as K, which has the dielectric constant as K, you are supposed to tell me what will be the force between the two charges. Guys, tell me. Can I say force between the two charges in any medium is force between the two charges in air, that is F divided by relative permittivity. So I say that is F divided by, what is the value of relative permittivity over here? That is K. So it is F by K. Decreases by K times, increases by K times, wrong, remains unchanged, becomes 1 by K square, decreases by K times. If the value of ER is 81, decreases by 81 times. Guys, tell me in the chats, is this clear and crystal and clear? Everyone means everyone. I would want you guys to tell me in the chats if this is crystal clear to each and every single student. Okay. Oh. Now guys, let's take a look over here. Equilibrium position. One more important topic that you guys need to understand over here. Equilibrium position. Guys, see. I'm saying that, let's suppose we have got, let me rub these two. Let's suppose we have got a charge over here that is let's suppose Q. See guys. Let's suppose we have got a charge over here that is Q, plus Q. And we have got a charge over here that is plus n times of Q, These are the two charges that we have. I am asking you the simple question over here. That is, where should I place the third charge? So that net force on that third charge is 0. Sir, let's place that third charge Q0 over here. Let's check if the net force here is 0. Guys, this positive charge will repel this positive charge in this direction. We say with a force, let's suppose F. This positive charge will also repel this positive charge in this direction with a force F. Guys, do you think that these two forces will cancel out and the resultant will come out to be 0? No. So we say here, net force is not equal to 0. We have to find that position where net force is 0. Let's check over here. If we place Q0 over here, this positive will repel Q0 with a force F. This positive will also repel Q0 with a force F. Here also we can say net force is not equal to 0. Here also we can say net force is not equal to 0. Okay. Let's now do one thing. Let's place the Q0 over here. Guys, see, this will repel this charge in this direction with a force F. This charge will also repel because positive repels with the force F. Here, I can say the net force will be 0 and it is towards the smaller charge. Okay, distance between the two charges is R. Okay, we say here I can say net force will be equal to 0. Now guys, I say this is at x distance from the smaller charge. We say so at x distance from the smaller charge, at x distance from the smaller charge, we say net force is equal to 0. Now, if I ask you what is the value of this x, guys, directly remember, the value of this x will be simply, that is r. R is the distance between the two upon under root of n plus 1. R upon under root of n plus 1. Directly remember this, okay? N is this, how many times this is bigger than this one? Plus 1. Let me show you the question. The question in this particular case is, find the position where net force is 0. I'm saying I'll place that charge over here Q naught at what distance? We say, sir, x distance. And what is the value of x? X is equal to R upon, we say, under root of n plus 1. And I can say, what is the value of R? R is the distance between the two, that is 10 upon under root of n plus 1. N is what? Guys, let me show you how do we find the n. N is this bigger charge, that is 9q, divided by smaller charge, that is q. This and this will cancel, that is 9. So this will be under root of 9 plus 1. So this will be 10 divided by root 9 is 3 plus 1 is 4. So that will come out to be 2.5. So at 2.5 meter distance, we say net force will be 0. What if I ask you to tell me in this particular case what should be the value of x? Here also, guys, let's place the third charge Q naught here. At what distance? We say, sir, x distance. And I can say this x will be R upon, we say, under root of n plus 1. And I can say over here, what is the value of R? R is the distance between the two charges, that is 11 upon under root of n. Under root of n will be, guys, how do we find the n? N in this case will be simply bigger charge divided by smaller charge, that is 36q divided by, we say, 25q. Q will cancel, so 36 divided by 25. So I can place it over here, that is 36 divided by 25, and then we say plus 1. So over here I'll write, so this is 11 upon root 36 is 6. 6 divided by root 25 is 5, plus we say, sir, 1. And I can say over here, this is 11 upon 5 into 1 is 5. 6 plus 5 is 11 divided by 5. Okay, this and this will go. So it goes in the numerator. So it will be 5 meters. Yes, 5 is the answer. Now guys, tell me one thing. In this particular case, you are taking this charge as positive. You are taking this charge also as positive. So this formula is valid. If both the charges are of same nature, similar nature. If this is positive, this is positive, this is negative, then also valid. Now. I say, if Q1 and Q2, if the two charges are unlike, okay, opposite in nature, in that particular case, okay, let me show. In that particular case, you guys are supposed to tell me what will be the equilibrium position. See guys. Let's suppose I say I have got a charge over here that is plus q, and I have got minus n times of q. Okay, and I am asking you, where am I supposed to place the third charge so that net force on that third charge is 0? So that net force on that third charge is 0. Guys, see. When it comes to the similar charges, we say we place it in between, near to the smaller charge. When it comes to the opposite charges, guys, directly remember now, I'll place it over here, okay? Near to the smaller charge, but from the outside, Sir, at what distance? I say at x distance, And this x over here will be, sir, x is equal to r. R is the distance between the two. R upon under root of n minus 1. If the two charges are similar, then you say r is equal to under root of n plus 1. If the two charges are not similar, then you say r is equal to under root of n minus 1. Okay, just a second, guys. So we say this is q. Okay, this is minus n times of q. And this is r. And here we place q naught at x distance. And this x is equal r upon under root of n minus 1. Okay? Okay? Yes. Now, let me show you the question on this particular case. Now, see this, see, guys, look at the question. I'll give you the break exactly after 3 hours, okay? It is right now 7:06, we'll have 1 more hour. Because we have the 12 hours long session. You are right now asking for the break. What will you do in the upcoming time? Wait, guys. We have to see the proper content. We have to learn each and every single thing. If you want to learn maximum in this particular session, then you have to, okay, bear it. You have to be with me for, we say, next 12 hours. Now, guys, see. If I say this is minus q, this is plus 9q. The charges are opposite. Find the distance from 9q. Find the distance from 9q. Where q naught is placed, so that net force on it is 0. I'll say I'll place the q naught over here. Sir, at what distance? At x distance. Now, see, guys. I'll say, sir, this x will be simply r upon under root of n minus 1. Why? Because if the charges are opposite, then I can say root n minus 1. So can I say in this particular case x is equal to r? What is the value of r? That is 18 over here upon under root of n. We say, sir, this is under root of n will be, sir, 9. Then we say minus 1. And I'll write over here x is equal to, this is 18. So we say this is 18 upon, or root 9 is 3 minus 1 is, we say, sir, 2. So I say this is, we say, 9 meters over here. So this distance is 9 meters. This came out to be 9 meters. But we have to check the distance from 9q. So from 9q, the distance is 18 plus 9. So I say from 9q, I can simply say, distance is, we say that is 9 meters plus, we say, sir, 18 meters. Okay, that is 27 meters. Is that clear? Guys? Give me the signal in the chats. Everyone means everyone. Next one is, we say, that is magnitude of q naught. Guys, till now, I was asking you, okay, tell me in the chats if everything is crystalline clear. Tell me in the chats if everything is crystalline clear. Okay. Great, 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 great. You will get the PDF in the Telegram channel, okay? And let me show you the Telegram channel over here. You can join this Telegram channel, that is t.me/Yawar Manzoor. t.me/YAWARMANZOOR. Okay, you'll get the PDF over here in this Telegram channel. t.me/YAWARMANZOOR. Now guys, take a look over here. Take a look over here. See. Till now, I was asking you, where am I supposed to place the third charge? Means distance. Tell me the distance. Sir, in case of two positive, in case of similar charges, under root of r upon under root of n plus 1. In case of two negative opposite charges, r upon under root of n minus 1. But now I am asking you, what is the value of this Q naught? Magnitude of Q naught. What should be? The question is, guys, see. What? This is the condition. Should be the value of third charge Q naught. What should be the value of this third charge? Its value. So that the system remains in the equilibrium. So that the system remains in the equilibrium. What should be the value of the third charge so that the entire system is in the equilibrium? Guys, directly see. Value of this third charge. Sir, so that the entire system is in the equilibrium, what does that mean? So that all net force on all the three charges are equal to 0. This is the condition. So we say this Q naught will be, that is minus n times of Q upon n times of Q upon under root of n plus 1, we say whole square. Under root of n plus 1, we say whole square. This will be the value of Q naught. This will be the value of Q naught. Now guys, I would want you to focus. Let's suppose this was the question asked in NEET 2013. See. We have got over here a charge Q. We have got over here a charge Q. Okay. Distance between these two charges is, let's suppose, whatever it is, R. Okay. We are supposed to find what should be the value of the third charge Q, which is placed over here. What should be the value of the third charge Q? So that all the three charges are in the equilibrium. We have to find the value of this Q. Guys, see. Let's first find the n in this question. How do we find n? N is equal to this charge by this charge. That will be Q divided by Q, that is 1. So I can say this third charge, its value is, we say minus n times of Q upon under root of n plus 1, we say whole square. And this will be minus n. What is the value of n? That is 1. And Q means this Q. Yes, sir. Upon n plus root n plus 1 whole square. Root n means a root 1 plus we say 1, and it is whole square because n is 1. So I can write over here, this will be minus Q in the numerator upon root 1 is 1. 1 plus 1 is 2. And then we say this is 2 square. So it will be minus Q divided by 4. So the value of third charge is minus Q by 4. Please tell me in the charts if this is crystal and clear. Guys, tell me in the charts if this is crystal and clear. I have told you three things over here. The distance and we say the magnitude of the charge itself. Magnitude of the charge itself. Great. Guys, if you have not liked the session yet, hit the like button as soon as possible. Smash the like button. Like this. Now, a particle of mass m carrying the charge minus q is moving around a charge plus 2q in a circular path. Guys, look at this question. It's a good question actually. Okay. It's a good question actually. Okay. We say we have a particle of mass m carrying a charge minus q is moving around plus 2q. There is a charge plus 2q which is placed over here. And another charge, we say minus q1, is basically moving around this charge, and its mass is m. Okay. In a circular path. This is q2, this is q1. It is revolving around it in a circular path. Okay. Now, find its time period. We have to find its time period. Sir, what does time period mean? Time period means in how much time this will complete one cycle. In how much time it will complete one circle. Okay. Now guys, in order to find the time period over here, similar type of question is asked in the gravitation also. Guys, see, we say here, whenever guys particle moves in a circle, one force acts on it, that is what we call the centripetal force. So we say here due to the circular motion. I say centripetal force will act, Fc will act. And could you please tell me what is the value of that centripetal force? The value of that centripetal force is mv square divided by r, or you can also say this is mr omega square. Okay? Mr omega square. Either you say mv square by r, or you can say mr omega square. Okay? Omega is the angular velocity. Now guys, I can say in this particular case, What is that? Sir, since these two charges are at r distance, so they apply the electrostatic force between each other. Also, if electrostatic will act. So on this charge, we say electrostatic force will act. Sir, that electrostatic force will be Fe is equal to, we say that is K Q1 Q2 by R square. And always remember that this centripetal force is a fake force actually. Okay, it is not a real. This centripetal force is actually created by electrostatic force. Directly remember, let's suppose if you have got stone over here, you connect a string with the stone and then you rotate it. Here the stone is rotating in circle. Here also centripetal force will act on the stone. But here the centripetal force will be created. Here centripetal force will be created because of the tension, because in the string you have tension. Here centripetal force will be created because of the electrostatic force. So both will be equal. So here I can say Fe is equal to, we say sir, Fc. So Fc is equal to, we say sir, Fe. So this is mr omega square is equal, because we say V is equal to R omega, okay, then you get this relation. So this is K Q1 Q2 divided by R square. Now take it over there. So I can say this will be simply, that is omega square is equal to K Q1 Q2 divided by, and this will be mr cube, because here it is r square into r becomes r cube. Now this omega, we can write this omega as 2 pi divided by t also, and take the square over here, it becomes a root, that is k q1 q2 divided by mr cube. This becomes root. Now do the reciprocal, so you can say t divided by 2 pi will be simply under root of mr cube divided by k q1 q2, and this t will come out to be time period, so this will come out to be 2 pi under root of mr cube divided by k q1 q2. Is this clear? This is the time period. Is this clear? Is this clear? Please tell me in the chats. Everyone means everyone. Now guys, this is also important. I would want you guys to focus completely over here. For the next 20 minutes, we'll solve this particular topic. For the next 20 minutes, we'll have to finish this topic. Okay? Now guys, take a look. This is what we call the, guys, I'm not leaving a single topic over here, okay? This is what we call the equilibrium of the suspended charges. This is what we call the equilibrium of the two suspended charges. What does suspended charge mean? Let's suppose you have got a ceiling over here. You attach a rope or a string, okay? Then you connect a charge to this one, or a sphere on which charge is present. Guys, what I'm trying to say is, let's suppose you have got a block over here attached with this string. This is what we call the suspended block. This is what we call the suspended block. Okay. Similarly, I'm saying you have got a string over here, rope, and you have a sphere. On this sphere, it has got plus q charge. You have got another rope. On this sphere, you have got plus q charge. Now, what happens over here? Guys, I would want you guys to understand. Pendulum, yes, pendulum. What happens over here? Sir, initially, let's suppose they are over here. When you place the charge plus q on this one, plus q on this one. Now, it will go something like this. It will go something like this. They'll go away from each other. When they goes away from each other, and then they will stop at some distance, okay? They'll remain in the equilibrium at some distance, okay? They remain in the equilibrium at some distance. So we say, let's suppose they remain in the equilibrium at x distance. This is the x distance between the two. Okay, yes. And charge is q over here, and this angle is given as theta. Now, what they are asked is that find the value of q, find the value of theta, this angle theta. Tension T, if there is a rope, there is a tension in the string, okay? Always remember, if this is a rope, this is a block, there will be tension force in this string. You have to find the value of tension, theta, and distance between the two charges, this x, and the value of q also, the value of q also. And let me just tell you, my dear friends, this value of q and x, this was asked in the JEE Mains 2021. This was asked in the JEE Mains 2021. Now guys, I would want you guys to focus over here. We say if the two charges are in the equilibrium. In order to solve this problem, what is the step 1 you guys are supposed to do? We say step 1. Step 1. The first step that you guys are supposed to do is, guys, understand very carefully. We say draw the forces acting on the charge. Draw the forces acting on the charge. In order to solve this problem, you have to draw the forces acting on the charge. Guys, this is charge. Don't you think that in the downward direction there is a force which acts, that is mg, mass into acceleration due to gravity? Yes. And this charge will repel this charge in this direction with what force? That is electrostatic force. And here you have got tension in this direction. This is the tension force. Okay. And if this is theta, don't you think that, sir, this will be also theta and this will be t cos of theta, this component. And I can say this will be t sine of theta, this component. Now, how many forces are acting? T cos theta, mg, t sine theta, F electrostatic. Now, can I say in this particular case, the charge is in the equilibrium? If the charge is in the equilibrium, if anybody is in the equilibrium, we say net force is 0. Means this force, right side force is equal to left side force. Upward force is equal to downward force. So I can say balance the forces. Balance the forces. You have to balance the forces. Now guys, if you balance the forces, what will you say? T sine theta is equal to F electrostatic, and we can write this F electrostatic as K Q1 Q2 by X square, K Q square by X square. This will be the electrostatic force. Now guys, can I say this force is equal to this force because the body is in the equilibrium? So I can say over here T sine theta will be equal to K Q square divided by X square. And T cos theta will be equal to mg. T cos of theta will be equal to mg. Now I would want you guys to divide these two equations, okay? Divide the two. I say divide the two. If you divide the two, don't you think that it will become tan of theta is equal to T sine theta by cos theta. Sine by cos is tan, T will cancel tan theta. And here it will be K Q square divided by X square into mg. So call this as, this will be the value of theta. This is the value of theta. So first we got as theta. This is the value of theta. Theta is equal to tan inverse of K Q square X square into mg. Okay. Next. From this equation, guys, see, I'll write over here as we got the value of tan of theta is equal to K Q square upon X square mg. Now let's basically find the value of x. Let's find x, the distance between the two charges. Guys, take this x over here. So this will be x square is equal to, from this side it will be kq square upon, and then it will be mg, and then we say tan of theta. Now take the square over here, it will be root, so x will be under root of, this is k q square upon, we say mg, and then I say tan of theta. This is the value of x. This is the value of x. Now let's find the value of q. Let's find q. Let's find the value of q. And how are we supposed to find the value of q, guys? Take this x square mg, multiply over there. So we say from this equation, from the equation first, we say from equation first. So I can say multiply this over there. So we say k q square is equal to, kq square is equal to, I can write that is x square mg, and then we say tan theta. I multiply these two terms with this one. And I can say in this particular case, this q square will be, that is x square mg, and then we say tan theta divided by, we say, sir, k. And now q will be equal to under root of, that is x square mg tan theta divided by k. Guys, at one time in a question, they can either ask you to find the value of q, and if they ask you to find the value of q, then x will be given in the question itself. If they ask you to find the value of x, then q will be given in the question itself. Don't get confused. This is the combination of 4 questions I have made. Okay? 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 Guys, always remember, if this is theta, we say this angle will be theta. And if this is theta, so this component will be t cos theta, another one is t sin theta. From that side, from where it is theta, we consider that as cos component, and another one is, we say, sin component. Okay, so we got done with this theta q and x. Let's find the tension now. So I'll say, let's find the tension. Guys, let's suppose I'll take this charge over here. I'll take this charge over here. This is Q charge. Could you please tell me, if I'm taking this charge, what are the forces acting in reality? Sir, this tension. Then we divide this tension in t cos theta and t sin theta. Okay. Then we resolve this in t cos theta and t sin theta. But in reality, this tension, electrostatic force, and mg. So I can say, on this charge, we say in this direction tension is acting, in this direction electrostatic force is acting, in this direction we say mg is acting. Tell me, guys, could you please tell me what is the resultant of this one and this one? They are at 90 degrees. So the resultant of this one and this one will be simply, that is given as r. And this r resultant will be simply under root of this fe square plus, we say, sir, mg square, fe square plus mg square, fe square plus mg square. And guys, it is like under root of f1 square plus f2 square plus 2 times of f1 f2 cos of 90. Cos 90 is 0. That's why it will remain fe square plus mg square. Directly remember, resultant of this one and this one will be, if this is at 90 degree, fe square plus mg square. Now see, guys, this is Q charge. On this charge, from the upper side tension is T, from the lower side it is resultant R. If the charge is in the equilibrium, don't you think that this tension will be equal to this resultant? Yes. So here I can say tension is equal to this resultant because the charge is in the equilibrium. So tension is equal to this resultant, that is under root of, we say, electrostatic force square plus mg square. Is this clear? Is this clear? Please tell me in the chats. Yes, this is 100% useful for JEE. I was about to say JCB. 100% useful for JCB. For JEE, yes. Is this clear, guys? Please tell me in the chats. Everyone means everyone. I need the signal in the chats. Great. Next. Guys, tell me the answer of this question in the chats. Tell me the answer of this question in the chats. I would want you guys to tell me the answer in the chats. Everyone means everyone. Guys, smash the like button if you have not liked the session yet. Two small spheres, each having a charge plus q, are suspended by an insulating threads of length L from a hook. Okay? So we say two small spheres. We have got two small spheres. This is the first one. It has got the plus q charge. Are suspended by an insulating thread. Are suspended by means of a thread of length L. From a hook. So we have got one more. This is also plus q. This is also length L. This arrangement is taken to a gravity-free space, okay, where there is no gravitational effect. Guys, I am taking this arrangement and I am placing this in a gravity-free space. Okay, there is no gravitational force over here. If there is no gravitational force over here, don't you think that, guys, here, we say this is applying the electrostatic force on this one. This is also applying the electrostatic force on this one, Fe. Okay, and we say in the downward direction mg is acting. Now I am saying that there is no gravitational pull over here, so we say mg becomes 0. If this force becomes 0, if gravitational effect is 0, mg is 0, because of this Fe and Fe, we say the angle, it will go something like this. Don't you think it will become, these two charges will become something like this? Yes, on this electrostatic force is acting, on this electrostatic force is acting. Because gravitational force is 0. Because of the gravitational force, it will remain something like this. If gravity is 0, so it will go something like this. How much is now the angle between the two threads over here? Theta will be 180 degrees. Yes. So you guys are supposed to find then the angle between the two threads. Theta is equal to 180 degrees. And the tension in the string, guys, this will be the value of tension. This will be the value of tension. Guys, don't you think that the body, this charge will be in the equilibrium? So this tension will be equal to electrostatic force. We say this force is equal to this force. Here, we say tension is equal to electrostatic force. And electrostatic force will be, sir, K, Q1, Q2, electrostatic force between this and this, K, Q1, Q2, and it is given as charges Q and Q. This is plus Q. This is Q and Q. Okay, so it is K, Q square divided by, what is the distance between the two, guys? This distance is L, this distance is L, that is 2L. So we say distance over here is, we say 2L. So I can say this is 2L whole square. So this will be K Q square upon 2 square is 4L square. This will be the value of tension. Is this question clear? Please tell me in the chats. Is this question clear? Please tell me in the chats. Everyone means everyone. This is my Telegram channel, guys. Join this Telegram channel. t.me/YAWARMANZOOR. I'll be sharing the notes and every single detail in this Telegram channel only. Now comes the next topic, that is what we call the electric field. I guess I have shown you the enough questions in Coulomb's law in case of the forces, okay? Now let's basically move on to the electric field. Let's basically move on to the electric field. Okay. Guys, don't ask me for the break. Please. Okay? I'll give you the break, but you'll have to wait for that. We'll have to finish because I have the content, enough content, and I'll have to finish it within the 12 hours only. So for that, I'll give you the break, okay, whenever I feel that I should give the break now. So you will have to wait for some time and I'll give you it. What is electric field? Guys, see. Electric field is Let's suppose I'll give you a simple example over here. I'll give you a simple example over here. Let's suppose I have got a magnet over here. Let's suppose I have got a magnet over here. This is a magnet. I would want you to focus over here. I say, you place a coin over here near to the magnet. What will happen? This will be attracted towards the magnet. I say you place the coin over here. What will happen? It will be attracted towards the magnet. I say you place the coin over here. It will be attracted towards the magnet. I say you place the coin over here. It will be attracted towards the magnet. I say here also it will be attracted. Here also it will be attracted. Now, my dear friends, in this particular case, don't you think that this magnet is creating some sort of field around it? And if in that field, we say a coin, if we place any coin in that field, it will be attracted. Now, outside of this field, if we place this coin, it will not be attracted. No force will act on it. And this field is what we call the magnetic field. As of now, you call it the magnetic field. Similarly, guys, if you have, let's suppose, a charge over here. If you have got a charge over here, plus Q. And you place another charge over here, that is Q naught. Okay? You place Q naught here. We say this will repel this Q naught in this direction. Positive, positive repels. If you place this Q naught over here, here also it will be repelled. If you place this Q naught over here, here also it will be repelled. If you place this Q naught over here, here also it will be repelled. So don't you think that this charge Q is also creating some sort of field around it? And if in that field any other charge comes, it experiences force. If in that field any other charge comes, it experiences force. And this field is what we call the electric field. Charge creates electric field, magnet creates magnetic field. So I say it is a space around a charge. It is a space around a charge in which if any test charge comes, test charge means which has the zero field. We consider its field as zero. In which if any other charge comes, it experiences force. If you keep this out of this field, we say it will not experience the force. From now onwards, you will say, sir, if there is a charge, it will create electric field. If there is a charge, it will create electric field. As simple as that. Okay. Now guys, if let's suppose you have got a positive charge over here. Okay. And we will place a test charge over here. Let's suppose this is Q naught. Test charge is always positive. Tell me, will this Q naught be repelled or attracted? Sir, obviously it will be repelled. If it is repelled, I can say the electric field of the positive charge is away from the charge. Its direction is away from the charge. How do you find it? You place the test charge over here. If it is repelled, so electric field of the positive charge is away from the charge. It is away from the charge. And if you have negative charge, if you place over here a test charge, we know, sir, it will be attracted. So I can say electric field of negative charges towards the charge. We say electric field, the direction of electric field in case of negative charge is always towards the charge. In case of positive charge, we say it is away from the charge. In case of negative charge, it is towards the charge. Okay. So from now onwards, electric field of positive charge is away from the charge. Electric field of negative charge is towards the charge. Okay. Next. 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 Electric field, guys, see. Sir, since you are saying this is a charge, okay, it creates the field around it, okay. Sir, please tell me at let's suppose r distance, how much will be the field around the charge, okay. We say to find the electric field due to a charge, point charge, at we say r distance, we have to find the electric field due to a point charge at what distance? At r distance. Guys, always remember, if this is a charge, it will create electric field at r distance. What is the value? What is the intensity? What is the magnitude? So I can say, as if you have got a charge over here, we say at r distance, you have to find the value of electric field. We say at r distance, electric field will be simply, guys, directly remember, that is K. K is Coulomb's constant. Q, this is the charge, Q, divided by this r square, KQ divided by r square. This is the value of electric field at r distance, KQ divided by r square. And clearly I can see in this particular case, electric field is inversely proportional to r square. As you go away from the charge, electric field will decrease. As you move away from the charge, electric field will decrease. As you move away from the charge, electric field will decrease. Now guys, if you plot the graph between E versus R, we say that will be also a rectangular hyperbola. Why? Because we say E is inversely proportional to R square. Okay? E is, the more you are closer to the charge, electric field is large. You move away from the charge, electric field will be small. Graph between E versus R. Now guys, let's take a look at some graph tricks. First, I'll be showing you the graph tricks. Is this clear till over here? Please tell me in the chats. Is this clear till over here? Please tell me in the chats. Sir, when will you start the electrostatics? Tomorrow, day after tomorrow. I'll start electrostatics. Okay. Now guys, take a look over here. Some graph tricks. Guys, understand very carefully. I will show you how do we draw the graphs. See, let's suppose, my dear friends, always remember the sign conventions. We say these are the sign conventions. Guys, let's suppose we have got a positive charge over here. Okay? And I have told you, positive, in case of positive charge, electric field is away from the charge. I'll make it something like this. Guys, remember, if the direction of electric field is towards right, understand, this is towards right. The direction of electric field is towards right. Consider this electric field as positive. We say it is towards right. Consider this as positive. If the direction of electric field is towards left, okay, we consider this electric field as negative. So it is towards left. It is towards left. Guys, if the direction of electric field is towards right, take it positive. If the direction of electric field is towards left, consider it negative. Take it negative. Okay. Now, if you have got a positive charge, let's suppose if you have got one charge over here, and you have to draw the graph between E versus R for a single charge. This is E versus R. You'll simply say, sir, we can say graph will be like this. E is inversely proportional to R square. So graph will be rectangular hyperbola. Okay. Now guys, see. If you have got over here two positive charges, this is one and this is another one. You have to draw the graph in these two cases. Guys, I'll show you one technique, the rest you will be able to understand. See, here, On this axis, this is electric field. From the lower side, it will be minus electric field. Sir, why? Because it is plus y minus y. X-axis, y-axis. From this side, it is, we say, sir, R. Similarly, from this side, it is electric field, and this will be minus electric field. If you have to draw the graph between any two charges, what will you do? You will basically draw this line, y-axis, x-axis. From the upper side, plus E, minus E. From the upper side, plus E, and from the lower side, it is minus E. Yes. Now, guys, this is a positive charge. First, draw the sign conventions. We say, sir, electric field, because of the positive charge, is away from the charge. So we say, from this side, electric field will be away from the charge. So this will be away. So instead of writing it over here, I'll write it over here. This will be electric field, and this electric field would be positive. Why? Because this is towards right. And from this side, this electric field would be negative. Why? Because this is towards left. Now, guys, similarly over here, because of this positive charge, electric field is away from the charge. This is positive. And from this side, we say electric field is negative. From this side, electric field is negative. Now, guys, let's draw the graph now. This is the positive charge. So, come on to this side of the positive charge. Is the electric field positive or negative? Sir, positive. Shall we make the graph from the upper side or lower side? Sir, upper side. Why? Because from the upper side, we make positive electric field. From lower side, we make negative electric field. So, graph will be like this only, because E is inversely proportional to R square. Why did I make it from the upper side? Because electric field is positive. Now, come on to this side of the charge. Left side. Is electric field positive or negative? Negative. Shall I make the graph from the upper side or lower side? Sir, lower side. So, I'll make it something like this. Okay. I'll make it something like this. I'll make it something like this. It'll be also something like this. Now, come on to this charge. We say on the right side of this charge, electric field is positive. Shall I make the graph from upper side or lower side? We say, sir, we'll make the graph from the upper side. Why? Because electric field is positive. So, this will be the electric field. Here it will meet. This is what we call the neutral point. Neutral point. And we say at neutral point, electric field is 0. We say at neutral point, electric field is 0. Now, guys, come on to this side of this charge. Tell me, is the electric field positive or negative? Sir, electric field is negative, so I'll have to make the graph from this side. This is what we call the graph. Now, for a single charge, if we make the graph in the 4 quadrants, I can make it something like this. From this side, I can say electric field is positive. So, graph will be from the upper side. From this side, electric field is, we say, sir, negative. Graph will be from the lower side. So, this will be the graph. Guys, please tell me in the chats if this is crystal clear to each and every single student. Tell me in the chats. Everyone means everyone. Food diya, sir. Yes. Killed it. Okay. Now, can you plot the graph? Can you plot the graph for, in case of, we say, sir, we have got positive charge and we have got a negative charge. Can you plot the graph in this particular case? What is the first thing we are supposed to do? Make the x-axis and y-axis. Make the x-axis and y-axis. Make the x-axis and y-axis. Okay. Let's make the x-axis and y-axis. This is electric field. This is minus electric field. And this is, okay. One thing I forgot to tell you. What is that? Neutral point. Let me explain this neutral point. See guys. I say if we have got a plus q charge, over here, okay? Now, and this is R, let's suppose this is R. Electric field because of this plus q charge at this point will be, sir, away from the charge, and that is E. Because of the positive charge, electric field is away. Electric field because of this positive charge is away from this charge, that is E. This and this will cancel each other, net will come out to be 0. So that's why at the center point this will be the net electric field. This will be the net electric field. Okay? Now guys, let's make the graph over here. This is E and this is minus E. Guys, tell me one thing. Can I say over here? See guys, in case of a positive charge, I can say electric field is away from the charge. So this will be positive. Why, sir? Because it is towards the right. So from this side, electric field will be away from the charge and this will be negative. Now come over here. In this particular case, we say electric field is, electric field is towards the charge. Why? Because this is negative. In case of negative charge, electric field is towards, so this will be negative electric field. Why? Because this is towards left. And from this side, this will be the electric field, which is positive. Now let's draw the graph. Guys, see. When it comes to the negative charge, from this side, electric field is negative. So shall I make the graph from the upper side or the lower side? Obviously, sir, lower side, because electric field is negative. So this will be the graph. Now come on to this side. Electric field is positive or negative? Positive. So I have to make the graph from the upper side. Now guys, this is a positive charge. Come on to this side. Sir, electric field is positive. I'll make the graph from the upper side. Sir, in this particular case, you didn't make any neutral point. Yes, we say in case of positive and negative charge, we consider neutral point will be at infinity. Here we do not make any neutral point. Now come on to this side. We say electric field is negative, so graph would be something like this. Okay. Is this clear? Please tell me in the chats. Everyone means everyone. Now guys, take a look over here. See, for positive and negative charge, we are already done with this. And for negative and negative charge, you can take a look over here. Okay. Check this out. Okay, this is your homework. Check this out. Everything is mentioned. And. This is the graph in case of, we say plus 4Q and Q. And here, the electric field of 4Q will shift towards over here. Why? Because we say, sir, this is Q and this is 4Q. This will have the bigger electric field. This will have the smaller electric field. That's why the electric field of the 4Q its graph will bit shift over here. And neutral point will shift towards smaller charge. Please do check this out. Is this clear? Please, do I have to explain this also? Please tell me in the chats. Is this crystalline clear, guys? Let me know in the chats. Is this crystalline clear? Okay, no need. Great. So please do check these graphs at your home from your end. Now guys, an important question. This was once asked in the NEET as well as in the JEE. take a look over here. See guys, in this particular case, I will show you this question over here. We say this is the charge which is at 1 meter. This is another charge. Guys, see. This is, let's suppose, the point, what we call the origin. Okay, this is the origin or any reference point. Okay, this is the reference point over here. We have got the first charge which is placed at 1 meter distance. We have got the second charge which is placed at 2 meter distance. So this distance 1 meter is from this charge. This distance plus q is from this 2 meter is from this distance, this origin. And then we have got this third charge. This is at 4 meter distance. Then we have got this is at 8 meter distance. So means this is 1 meter. From here to here it is 2 meter. Third charge is placed at 4 meter, 8 meter, and so on. It is till infinity. We are supposed to find, guys, see. We are supposed, I'll give you the break. Please wait for 5 to 10 minutes. We are supposed to find the electric field because of all of these charges. Electric field because of all of these charges at the origin. We are supposed to find the electric field because of all of these charges at the origin. Okay, yes. Now guys, understand one thing very carefully. If I say net electric field at the origin, how am I supposed to find that? Guys, see, first we say electric field because of this charge. Okay, that is k, this q divided by, sir, this distance, that is 1 square is 1. Because of the point charge, electric field as at r distance will be kq by r square. Then we say plus electric field because of this charge will be, that is kq divided by distance between this and this, that is 2 square, that is 4. Then we say plus electric field because of this will be, sir, kq divided by 4 square is, we say, sir, 16. Similarly, I can say electric field because of this will be kq divided by 8 square is 64, and so on. Now, could you please tell me in all of these, what can you take common, sir? That is kq. So then I'll write 1 plus, we say, sir, 1 by 4. Then we say plus 1 by 16. Then we say plus 1 by 64. Then we say plus so on. Okay, yes. Now, my dear friends, I would want you guys to focus exactly over here. If you add all of these, this is what we call the GP series. Okay, so basically you have to add all of these. This is till infinity. This is what we call the GP series. Now you cannot edit something like this. It will take you your whole life, still you won't be able to edit. But there is a formula. So I can say in order to add all of these, okay, I have the formula, that is what we call it, sum is equal to, we say A upon 1 minus R. Sir, what is this A? A means the first term. And what is the first term in this GP series? That is 1. And what is this R? R means the common ratio. R means the common ratio. And how to find the common ratio, guys? See. You take any term over here. Let's suppose 1 by 16. You divide it with the term which comes before it. What is the term which comes before 1 by 16? That is 1 by 4. So that is 1 by 4. 4 ones are 4, 4s are 16. So common ratio is 1 by 4. How do we find the common ratio? Sir, you take any term, divide it with the first term which comes before it. That will be the common ratio. Even 1 by 64 by 1 by 16 is also 1 by 4. Now find the sum. So I can say sum will be A upon, A means 1 upon 1 minus R. R is 1 by 4. So I can say sum is equal to 1 upon 4 into 1 is 4. 4 minus 1 is 3. So that is 3 divided by 4. Take this in the numerator. This will be 4 by 3. Now, sum of all of this came out to be how much? 4 by 3. So can I say, I can say, we say net electric field will be, that is KQ, and then we can say 4 by 3. Instead of all of this, I am writing 4 by 3. And further also you can write K means 1 by 4 pi epsilon naught. Then Q, and we have got 4 by 3. This 4 and 4 will cancel. So it is Q by 3 pi epsilon naught. Okay, yes. So guys, I think let's take a break, huh? I think we need to take a break. This is the dinner break, guys. This is the dinner break. So be back, okay? I would want all of you to come back exactly at, I'll just write over here. We say break till, we say 8:40 p.m. So guys, welcome back. Ladies and gentlemen, I got you. Come on, everybody. So, back to basics, back to work. Let everybody join, let everybody come, and we are starting the session. Yo, yo, yo. Let me show you this question also, which is on the same GP series, okay? This question is having the similar pattern. This question is having the similar pattern. Yes, I'm done with the dinner. Now, guys, listen to me very carefully. I would want you guys to focus exactly over here. See, when it comes to, we say in this particular case, you guys are supposed to find the net electric field at this origin. Okay? We have got the plus Q charge, which is at 1 meter distance from the origin. We have got the minus Q charge, which is at 2 meter distance from the origin. We have got the 4 plus Q charge at 4 meter distance. Like here we have got alternative plus Q minus Q, plus Q minus Q, plus Q minus Q. Previously, if you take a look at this particular question, here we had only positive charges. But right now in this case, we have got plus Q minus Q, plus Q minus Q. If I want to find the net electric field at the origin, we say because of the first charge, electric field will be KQ divided by 1 square. Because from here to here distance is 1, so it will be 1 square is 1. Then we say minus. Since the charge is negative, I'll write minus over here. We say KQ divided by, from here to here, distance will be how much? That is 2 square, that is 4. Then I can say plus once again, because charge is positive. So that will be KQ divided by, from here to here distance is 4, so 4 square is 16. Again, minus KQ divided by 8 square is 64. And plus so on up to infinity. Now we can clearly see in all of these, there is something which is common, and that is KQ. I'll take this KQ out. What remains in the rest of this over here, in these terms, I can say this is 1. Then we say minus, in this term it remains 1 by 4. Then we say plus 1 by 16. Then we say minus 1 by 64, 1 by 64. Then we say plus and so on. Now guys, I would want you to focus exactly over here. See, if you take a look over here, this is a GP series. And how do we find the sum in case of the GP series? If we have to add all of these, we say S is equal to A upon 1 minus R. A means the first term. So I'll write over here that is 1 upon 1 minus. And what is the value of common ratio over here? Am I audible, guys? Am I audible? Check, 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 check. Am I audible, guys? Am I not audible? Then why are these guys saying? Yes, I guess so. I'm perfectly audible. Just. What remains in the rest of this overture? It's completely fine, huh? Yes, yes. So I can say in this particular case, so this common ratio will be, take any term over here. So let's suppose I am taking 1 by 16 again. Divide it with the term which comes before it. That is minus 1 by 4. So it will be minus 1 by 4. This and this will cancel. So this will be minus 1 divided by 4. Common ratio in this case is minus 1 by 4. So I can say this will be minus 1 by 4. So this sum will come out to be, guys, see. This is minus into minus is plus. 1 upon 1 plus 1 by 4. So this will be 4 into 1 is 4. 4 plus 1 is, this will be 5 divided by 4. Take this in the numerator. This will come out to be 4 by 5. Now, instead of all of this, I'll write 4 by 5. So I can write over here, net electric field will be simply, that is KQ upon, we say 4 by 5. And here instead of K, you can write Q by 4 pi epsilon naught. And this is 4 by 5. 4 and 4 will cancel. So this is Q divided by 5 pi epsilon naught. I hope this is crystal clear to each and every single student out there. Next, let's move on to this topic that we have over here. Now, guys, take a look over here. See, here it says that electric field due to a charged ring. I would want you to focus exactly over here. Guys, see. Let's suppose we have got a ring over here, and on this ring, charge is present. How much is the charge? That is Q, plus Q. Plus Q charge is present on the ring, and that I'll show you over here. Guys, always remember, whenever there is charge, it creates electric field. Now, if I place that charge onto this pen will also create electric field. If I place that charge on the ring, this ring will also create electric field. If I place the charge on the sphere will also create the electric field. Now, here we have to find the electric field because of the ring. Okay? At what distance? At x distance. Okay? So I'll write the same statement over here. Since the ring has charge on it, so it creates the electric field. Since the ring has the charge on it, so it creates the electric field. And we are supposed to find the electric field at x distance. To find the electric field at x distance. We are supposed to find the electric field at x distance. Guys, directly remember, when it comes to the electric field at this x distance, I say it will be KQX. Sir, what is this K? K is the constant, Coulomb's constant. Q is the charge on the ring. So we say if this is a ring, we have distributed the charge on the ring. That is Q. And X is the distance from the center at which we have to find the electric field. Then we say upon. And I'll write over here R square plus we say, sir, X square whole raised power 3 by 2. This is the value of electric field because of the ring on its axis. It is something like this. This is the ring on its axis. This is the ring on its axis. We are supposed to find the electric field at this x distance. Let's suppose if somebody asks you at the center, guys, don't you think that At center, what is the value of x? We say, sir, value of x at center is 0. Because as you move away from the center, x is increasing. As you move towards the center, we say x is decreasing. There is a long derivation for this particular formula. I will not derive it over here. I am saying directly, because of this ring at this point, electric field is this much. So now at center, we say value of x is equal to 0. If you put x is equal to 0 over here, 0 multiplied by something, the whole term will come out to be 0. So this will be 0. This is the electric field at center. Okay. Now guys, one more thing I would say over here. What is that? See guys. I say case 1. What is that? That is very close to the ring. Very close to the ring. This is the case 1. Now see, let's suppose guys, I have got a ring over here. Okay. And in this particular case, if I have a ring over here, this is the ring. And the radius of the ring is given as, let's suppose, r. And I am saying I'm taking a point over here such that it is very close to the ring. This is the ring just outside of the center, means very close to the ring. And for this, I can clearly say x is much less than capital R. I am supposed to calculate the electric field at this point, which is very close to the ring. Guys, this is x distance. X is some good distance, finite distance. When it comes to the x is equal to 0, that is center electric field is 0. Now, if I am saying close to the ring, so radius is greater than the x in that particular case. Now see, what will be the value of electric field? We say electric field is, that is kqx upon, and then we say over here, this is r square, then we say plus x square. Guys, x is very small. Its square will be more small. We are adding a very small quantity to a very large quantity. Will it create any difference? No, sir. It is like adding a bucket of water to the ocean. Will it create any difference? No, sir. Ocean has got the immense water. How will it create any difference? So that is the reason, that is the same thing over here. X is very small, R is very large as compared to X. So adding very small quantity to the very large quantity will not create any difference. So we ignore it. So I'll write directly 3 by 2, R square 3 by 2. Now this 2 and 2 will go. So I can say electric field will come out to be, that is kqx upon, and then I'll write over here, that is r cube. This is the value of electric field very close to the ring. This is the value of electric field very close to the ring. Let's suppose I'll talk about the case 3. That is very far from the ring. Can I say it is something like this? This is the ring. It is something like this. This is the ring. And this is the radius of the ring. Very far distance will be this. This is r and this is x. Very far from the ring. And I can say in this particular case, I can say r is much less than x. Now. Case 2 means you are finding the electric field very far from the ring. Case 1 is you are finding the electric field very close to the ring. So I'll use the same formula. E is equal to, we say kqx upon. Now we say r square plus x square. Right now, r is very small. Adding very small quantity to the very large quantity, it will not create. Guys, 2 and 2 will cancel because now here remains r cube. That's why I'm writing r cube over here. Okay. Okay, case 2. I have one and the same thing, guys. Now I am saying, see, this is, in this particular case, r we can neglect over here. So then it is x square and this will be whole raised power 3 by 2. This and this will cancel. So what remains over here? This is kqx upon, and this will be x cube, and now this x and 1x will cancel, so electric field will come out to be kq divided by x square. Kq divided by x square. So this is the electric field because of the ring very far from the ring, very close to the ring. This is the electric field. At the center, this is the electric field. This is the electric field at finite distance. All the values I have mentioned over here. Now guys, you can clearly take a look over here. Very close to the ring, electric field is directly proportional to x. At center, electric field is 0. Let me plot the graph. Guys, see. I say graph between, we say E versus R. So if I plot the graph between E versus R, this is electric field and this is R. Guys. If I say over here, I have got a ring over here. It has radius R. Okay. And I am saying at x is equal to 0, electric field is 0 at the center. And at very small distance, electric field is directly proportional to x, means close to the ring. Guys, see? We say at R is equal to 0, okay? If it E versus X I'll make, E versus X. We say at x is equal to 0, how much is electric field? Electric field is equal to 0. So graph will start from the origin. And we say very close to the point, very close to the ring, we say electric field is directly proportional to x, so E is directly proportional to x, so graph will be straight line. Because if you make a ring, let's suppose over here, this is the point which is close, this is the point which is close, this point is far from the ring. This point is far from the ring. And when you move very far from the ring, see guys, when you move very far from the ring, electric field, you can see, is inversely proportional to x square. Electric field is inversely proportional to x square. So then I can say graph will be a rectangular hyperbola. If you go very far from the ring, okay, graph will be rectangular hyperbola. And here you can join this graph with a smooth curve. Okay, you can join this graph with a smooth curve. Smooth curve. Okay, and this is here E is inversely proportional to x square. And this is very far from the ring. This is very close to the ring. And at this point, electric field will be maximum. Okay, electric field is maximum. Are you able to understand this graph? Guys, close to the ring, electric field is directly proportional to x. Very far from the ring, electric field is inversely proportional to the r square. So here I can say, now guys, let me show you the proper graph. This is the proper graph that is over here. If this is the ring, we say at x is equal to 0, electric field is 0. Okay, it has to be a straight line. It has to be a straight line. It should be straight. It should be straight. It should be straight, something like this. Okay, and then here also, it should be the straight line over here. Sir, why did you make the graph from this side also? Because if you have got a ring, it creates the electric field from the right side also. It creates the electric field from the left side also. From the right side electric field, you consider that positive. From left side electric field, you consider that negative. That's why I made it from this side. And guys, we say this is E is directly proportional to, we say E is directly proportional to x. And here E is inversely proportional to x square. And at this point, electric field is maximum. And electric field is maximum, you guys directly remember this as x is equal to plus r by root 2, where r is the radius, and x is equal to minus r by root 2. Okay, So we say in case of a ring, I can simply say electric field is maximum at x is equal to plus minus r divided by root 2. Guys, please tell me in the chats if everything crystalline clear. Let me know in the chats, is this crystal and clear to each and every single student? Tell me, guys. Great. Now guys, let's take a look over here. Let's suppose I have got a ring over here, and on this ring we have got the charge plus Q. Okay, this is the charge on the ring, that is plus Q. And there is one more charge placed over here which is also plus Q. Let's suppose I'm holding this charge over here. And if I release this charge, what is going to happen? Sir, this ring will apply the force on this ring. This ring will apply the force on this ring. This is positive, this is positive. So positive repels. So it will repel it, okay? If it applies the force on this ring, don't you think that it moves away? Yes, sir. It moves away. Now the question is, will the speed increase or decrease? Guys, as the charge moves away, we say force on it will decrease. Like this is a ring. If charge is over here, less force will be applied on the charge because of the ring. Here more or less force, okay? If force is decreasing in this particular case, do you think that speed is decreasing in this particular case? Do you think moves away and speed decreasing? Option C or option B? Option C or option B? Tell me, guys. C or B? C or B? C or B? Hey, what are you doing? Option B is correct option. Why? Let me tell you why. If I say I have got a block over here, okay, I am applying, let's suppose it is moving with a constant velocity of 10 meter per second. You are applying the 100 Newton force over here. Okay. Now, if you are applying the force in this particular case, what will happen? What will happen to the velocity? Velocity will increase. Okay. Now, if you keep on applying the force in the same direction, no doubt the force is decreasing. But velocity will still increase. But with less rate. So I say in this particular case, option B is the correct option. Speed will increase, but with the less rate over here. Because it is applying the force on this charge in the same direction. Are you able to understand what I'm trying to say? Guys, tell me, guys. So we say option B in this particular case. See, here let's suppose 10 Newton force is acting, 5 Newton, 4 Newton, but still force is acting. Speed will increase, but with less rate. Like, let's suppose here its velocity was 10 meter per second, okay, when the force was 10 Newton. Now here, we say if the force is acting 5 Newton, we say when the block reaches over here, let's suppose here its speed is 15 meter per second. Now force is 5 Newton only, okay. Now, when block reaches over here, force becomes 2 Newton, but speed will still increase. Why? Because force is acting in the same direction. Next, let's take a look over here. Guys, see. Before this, I would want you guys to focus completely over here. What I want to say in this particular case is linear charge density. Guys, I would want you guys to focus completely over here. I would want you guys to focus completely over here. Let's suppose I have got over here a rod. Let's suppose I'm taking a rod over here. Okay, this is a rod. And I'm saying that charge on this rod is plus Q. I'm saying that charge on this rod is plus Q. Okay. And length of this rod is L. So, what if I ask you, sir, how much is the total charge on the rod? We say, sir, total charge. And we say, how much is the total length? Total length. Sir, total charge on the rod in this particular case is simply, sir, Q. And total length of the rod in this particular case is, we say, sir, L. I can also say Q charge is present on L length. Q charge is present on L length. So this is what we call the lambda. This is what we call the lambda. That is charge per unit length. So lambda basically tells us how much is the charge present on the unit length. Let's suppose if I say I have got 1, 2, 3, 4, 5 apples. And there are 5 people over here. 1, 2, 3, 4 and 5. If I say 5 people have got 5 apples, one person will have how many apples over here? You say, sir, total apples divided by total person. So you say, sir, that is 5 divided by 5, that is equal to 1. So this is the apple per person. Apple per person. Now guys. If I say in this particular case, guys, understand very carefully. The whole rod has got how much charge? Q. L length has got Q charge. If I say what is the charge present on the unit length, what will you say? Sir, that is total charge by total length. Like over here, total apple by total person. So that will be lambda. And lambda is what we call the Q divided by L. Or this lambda is what we call this lambda tells us the charge present on the unit length. Lambda tells us the charge present on the unit length. Okay. Similarly, my dear friends, listen to me very carefully, or we call it the linear charge density or charge per unit length. Now guys, let's talk about, that is what we call the surface charge density. Let's talk about the surface charge density. Let's suppose, my dear friends, I have got over here a sheet, and the area of the sheet is A, and charge present on this sheet is Q. Okay. Charge present on this sheet is Q. I'm saying the charge present on this sheet is Q. Okay. The charge present on this sheet is Q. Now, my dear friends, I am saying that what is the charge present on the unit area over here? How much is the charge present on the unit area over here? What will you say? Screen is not clear. It's clear, I guess. So we say in this particular case, charge present on the unit area will be simply, that is total charge divided by total area. And that is what we call the sigma. Can I say sigma tells us the charge present, sigma tells us the charge present on the unit area. So sigma will help us to find the charge present on the unit area. Lambda will present us to find the charge present on the unit length. So in case of a rod, we take lambda. In case of a, we say, sheet area, we take sigma, or we also call it the charge per unit area. Okay. Now then, let's suppose we have got a sphere over here. This is a spherical ball over here. Okay. This is a spherical ball. This is a spherical ball. Okay. And inside this spherical ball, it has got a charge present in its volume. So now we'll define volume, charge, density. Guys, if I say Q charge is present in V volume, in this entire ball, how much charge is present Q? And what if I ask you how much is the charge present in the unit volume? Unit volume. So how can you say, sir, that is what we call the sigma? Sorry, rho. Rho will be Q divided by V. So can I say this rho tells us how much is the charge present in the unit volume. So rho tells us how much is the charge present in the unit volume. So in case of volume, we take a rho. In case of area, we take sigma. In case of rod, we take lambda. Is this crystalline clear? Please tell me in the chat. Please tell me in the chats. So it is what we call the charge per unit volume. Great. Now, let's take a look over here. Now, my dear friends, listen to me very carefully. Let's suppose if I ask you over here, what is this? Let's suppose if I ask you over here, what is this? Is this a complete ring? Is this a semicircular ring? Or is this something else? You'll say, sir, obviously it's a complete ring. If I want you guys to cut this in two parts, we say, sir, this is one semicircular ring. This is another semicircular ring. So a complete ring has got two semicircular rings. Okay. If I want you guys to cut this in four parts, this part is what we call the chord. Okay. So a complete ring consists of four chords. Okay. This chord. Now, if I say you cut this ring from this point to this point, sir, what is this? This is what we call the segment of a ring. Segment of a ring. Sir, what does segment of ring mean? Segment of ring means some part of the ring. Or we say arc. Some people also call it the arc. Sir, arc can be anything from here to here. Some part of the ring. Now you take this arc. Guys, see. From here to here, this is the radius. From here to here, this is also the radius. Now take this arc and place it over here. This is not a half ring, semicircular ring. This is not a complete ring. This is just an arc. And place the charge on, distribute the charge Q on this arc. Okay, Q. Now, since this has the charge, so it creates the electric field. Now, if I ask you, sir, you take this point, you have to find the electric field at this point. You have to find the electric field at this point. This arc, this segment of ring will create electric field. Why? Because it has got the charge. I would want you guys to basically join this point with one end of the arc, one end of the segment of the ring. I would want you guys to join this another end. So can I not say, sir, this is the radius R and this will be the radius R? Yes. And angle between these two is what we call the theta. Now guys, understand one thing. Arc, this ring is basically a rod. This is kind of a rod only. In case of rod, we take lambda. Lambda means charge per unit length. Okay. Now, can I say electric field because of this at this is, guys, directly remember, we don't have to derive it. That is 2k lambda by r. Sir, k is constant, lambda is charge per unit length, r is the radius over here. Then we say sine of theta by 2. Sir, theta is the angle between this r and this r. So we say this is the electric field due to an arc at its center. At its center. This is the electric field due to an arc at its center. Okay? Now guys, listen to me very carefully. Let's suppose if I take a semicircular ring and I would want you guys to join this point with one end of the ring. This will be radius r. Okay? This is radius r. And I would want you guys to join this another point. This is also radius r. Now we say angle between these two is, we define this as theta. Clearly you can say in case of this semicircle, theta is how much? 180. Now, if I have to find the electric field over here, so I'll use the general formula. Electric field is equal to, we say 2k lambda by r, then we say sine of theta by 2. Then we say sine of theta by 2. For an arc, that we consider as general formula. For semicircle, theta is 180. So can I write electric field will come out to be, that is 2k lambda by r, and then I say sine of 180 by 2, that is sine 90. And sine 90 is how much? That is 1. So this will come out to be 1. So electric field will be simply, that is 2k lambda divided by r. 2k lambda by r. This is 2k lambda by r. Okay? Okay. Now guys, next thing, if I talk about in case of a chord, guys, see, chord looks something like this. This is how does a chord look. Now, this is the center. I would want you guys to join this point with one end of the chord, and this is another end of the chord. And on this chord, we have got the charge over here, that is plus q. On this chord, we have got the charge over here, that is plus q. Now, don't you think that angle between this and this is given as 90 degrees over here? Yes. So in case of a chord, we take angle as 90. So can I say electric field will be simply, that is, use this formula, that is 2k lambda by r. And then I say sine of 90 divided by 2, that is sine 45, that is 1 by root 2. So this is 2k lambda by r, sine 45 is 1 by root 2. Now, I would want you guys to rationalize it. Multiply with root 2 and divide with root 2. Once again, you can cancel it, it will remain the same. Guys, see, root 2 into root 2 is always 2. Guys, see how? Root 2 into root 2. It becomes root 2 whole square. Square and root will cancel, so it will come out to be 2. So we say, guys, see, don't get confused over here. We say this root 2 and root 2 becomes 2, and that 2 will cancel with this 2. So I can write over here, this will be root 2 in the numerator, then we say k lambda divided by r. So because of the chord, electric field at the center will be simply, that is root 2k lambda by r. Because of the semicircle, it is 2k lambda by r. Is this crystalline clear to each and every single student? Please tell me in the chats. Tell me guys, is this crystalline clear to each and every single student? Yes, great. Next, let's take a look at this particular question. We are supposed to find the net electric field at the center because of this. Now here, half of this semicircular ring contains positive charge, half of the semicircular ring contains negative charge. Whenever you have the question something like this, understand guys, whenever you have the question something like this, I would want you guys to divide this in two chords. I would want you guys to divide this in two chords. Okay? This is the first chord, this is the second chord. Now guys, take a look over here. When it comes to the electric field because of this chord, since this is a positive charge, because of the positive charge, electric field will be always away. And here, electric field because of this will be something like this. Come over here. Since this is a negatively charged chord, don't you think that electric field because of negatively charged chord will be towards the chord? Yes, sir. And electric field because of this positively charged chord will be away from the chord. Guys, see, I'll make these two over here. This is electric field due to negative chord. This is electric field due to positive chord. Guys, see, because of the negative chord, how much is the electric field because of the chord? That is root 2 k lambda by r. So this is root 2 k lambda by r. No need to mention the negative sign because you have already mentioned the direction. And I say because of this positively charged chord, it will be also root 2 k lambda by r. Why? Because of the chord, electric field is always root 2 k lambda by r. Now, this angle is always 90 degrees. Keep that thing in your mind. So this angle is 90 degrees. So this resultant will come out to be, guys, if the angle between the two vectors is 90, don't you think that resultant is root 2 of that vector? So resultant will be root 2 of this vector or this vector. If this is x, so root 2x. If this is f, root 2f. So this is root 2 k lambda by r. So this will be root 2 k lambda by r. Root 2 into root 2 will become 2 k lambda by r, and direction is towards right. Murugan sir, screen not clear. I am sorry. This is the only screen I have over here. I cannot replace it as of now, but tomorrow maybe I'll think about it. Next, we have this question over here. Take a look at this particular question. So in this particular case, we say you have got the negative charge. Okay, this is the negative charge over here. And this is the positive charge over here. This is the positive charge over here. So basically a complete ring is divided into two semicircular. Here. It is simple. Logically also you can divide this into two semicircular rings. Guys, see. This ring, because of the upper semicircular ring, electric field is away from the ring. Why? Because it is positive. And we say because of this ring, electric field will be towards the ring. Now here, this is electric field because of positive, this is electric field because of negative. Both the electric fields are in the same direction. And because of this upper semicircular ring, don't you think that, guys, see. Don't you think that electric field will be 2 k lambda by r? This electric field is also 2 k lambda by r. Sir, why? Because both are semicircular rings. Because of the semicircular ring, electric field is 2 k lambda by r. Now, these two are in the same direction. Don't you think that we can add them? So, we say net electric field will be 2 plus 2 is, we say 4 k lambda by r. 4 k lambda by r is the answer. Next, tell me the answer of this one. Okay, tell me the answer of this one. What will be find the net electric field at the center. Find the net electric field at the center. Guys, see, here you can divide this into 4 chords. We say something like this. Something like this. This is the negatively charged chord. Because of the negatively charged chord, electric field is towards the chord. Because of this negatively charged chord, electric field is towards the chord. Because of this positively charged chord, electric field is away from the chord. Because of this positively charged chord, electric field is away from the chord. This gets cancelled with this one. This gets cancelled with this one. So net electric field at the center comes out to be 0. Tell me about this one. Tell me in this case. Tell me in this case. Here also you can divide this into 4 chords. Here also you can divide this into 4 chords. Okay. Guys, see, this is positively charged chord. Because of this, electric field will be away from the chord. This is negatively charged chord. Because of this, electric field will be towards the chord. Guys, please look at the approach that I'm using in the questions. I'm dividing here. Now, because of this negatively charged chord, electric field is towards the chord. Because of this negatively charged chord, electric field is towards the chord. Why? Because of the negative charge, electric field is towards the charge. Don't you think that this electric field gets cancelled with this one? What remains over here? This one and this one. Okay. So one is because of this positively charged chord, another one is because of negatively charged chord. Now see, I'll make the same 2 vectors over here. This one and this one. So this one is because of negative chord, and that will be how much? Root 2 k lambda by r. This one is because of positively charged chord. That is root 2 k lambda by r. Now these two are in the same direction. If these two are in the same direction, what are we supposed to do? This plus this, and it is twice. So I can say net electric field is 1 plus 1 is 2. So 2 times of root 2 k lambda by r. Tell me, is this crystalline clear? I need the signal from every single student out there. Guys, if you have not liked this session yet, I would want you guys to hit the like button. Everyone means everyone. Now guys, we have got a semicircular ring in this particular, sorry, this is a chord. Find the horizontal and vertical components of the electric field. We are supposed to find the horizontal and vertical components of the electric field. Guys, see. In this case, first and the foremost thing, let me just tell you, electric field because of the chord will be something like this. That will be something like this. Electric field because of the chord will be something like this, and this is a root 2 k lambda by r. We are supposed to find horizontal and vertical components. Don't say cos and sine. Look at this. See, I am saying in this particular case, let's suppose I have got a force F over here. I have got one more force F over here. Angle between these two is 90 degrees. Could you please tell me what will be the resultant? Obviously, sir, resultant is root 2 of F. We can also say it something like this. If you have got resultant as root 2f, then one of its vectors will be f, another vector will be f. You can say it something like that. If resultant is root 2f, one vector is f, another vector is f. Similarly, here. If resultant is root 2k lambda by r, don't you think that, guys, I'll make it over here. This is root 2k lambda by r. Don't you think that it's one of its component will be k lambda by r, another component will be k lambda by r. Now, if this is k lambda by r, resultant will be root 2k lambda by r. So this is the horizontal component, this is the vertical component. So I can say, so here, horizontal and vertical vertical components are, we say, k lambda by r and k lambda by r. Is this clear? Tell me, guys. Tell me. Everyone. Is this crystalline clear? Yes, great. Okay, now let's move on to the rods. Great. Now, guys, I told you in the beginning itself, you are going to love this session. Why? Because the content will be unmatchable. Okay? You would have seen the number of questions I have put up in this particular session. Now, see, guys, let's suppose I say, in this particular case, I'll take a rod over here. Okay? And Q charge is present on the rod. Tell me one thing. If you have got a rod over here on which Q charge is present, will it create the electric field? Yes. Why? Because whenever we have anything on which charge is present, it creates electric field. So we say on this rod, we say Q charge is present. You guys are supposed to tell me the electric field at this point, which is at r distance from the rod. Okay, this is at r distance from the rod. Now, guys, I would want you guys to join this point with one end of the rod, okay? And this angle is what we call the theta 1. I would want you guys to join this point with another end of the rod. This angle is what we call the theta 2. Okay? Now, we say, due to this rod, electric field at point P, let's call this as point P, will be. Electric field at point P will be. See, guys, that is K lambda by R. K is what? K is Coulomb's constant. Lambda is what? Charge per unit length. R is what? Sir, at what distance you are finding the electric field. Then we say sine of theta 1. Then we say plus. We say cos of theta, sine of theta 2. Okay? Sine of theta 1 plus sine of theta 2. And then you say cos of theta 2 minus cos of theta 1. This will be the value of electric field at this point because of this rod. And this point is what we call the arbitrary point, general point. This is not a specific point. Let me tell you. If I say this is a rod, I am saying, sir, this point which is exactly at the center, this will be the perpendicular bisector point. This is a special point. Okay? Sir, this point will be the axial point. But when it comes to this point, this point, this point, these are what we call the arbitrary points, general points. So same in this case, I'm saying that electric field because of this rod at this point, which is an arbitrary point, will be E is equal to K lambda by R sine of theta 1 plus sine of theta 2 plus cos of theta 2 minus cos of theta 1. This is the electric field because of this rod at what distance? At small r distance. Okay, now guys, let's suppose if we talk about the equatorial position or perpendicular bisector position. This is the rod. At r distance, I'm taking this point, which is exactly center point. So from the upper side, if this is the length of the rod L by 2, this will be also L by 2. This is the middle point. Now guys, if you join this point with one end of the rod, this is theta 1. If you join this point with another end of the rod, this is theta 2. Don't you think that in this particular case, we say, sure, clearly I can say theta 1 is equal to theta 2. Let's suppose that is theta. Sure, this angle and this angle will be equal. Why? Because this is the center point. Now use the general formula. What is the general formula? Sir, this one. Use the general formula to find the electric field. So we say, so electric field will be at this point. That is K lambda by R. Then we say sine of theta 1. Here it is sine of theta 1. Instead of theta 1, I'll write theta only, because theta 1 is equal to theta 2 is equal to theta. So it is sine of theta plus sine of theta 2. Theta 2 is also theta. Okay. Then I'll write plus. So this is cos of theta 2. Cos of theta 2 is cos of theta, because theta 2 is also theta. Minus we say cos of theta. Now cos theta minus cos theta, this term will become 0. Don't you think that this electric field will come out to be, that is K lambda by R. Sin theta plus sin theta is 2 sine of theta. Take this 2 out, so this will be 2 K lambda by R. Okay. Then we say sine of theta. This will be the electric field. So this will be the electric field. Let's suppose, I'll take this one. Because of the infinitely long rod, guys, understand one thing very carefully. What is that? See. I'll make you understand. This is infinitely long, means it is going till infinity over here. Now, if you join this, if you have to find, we said to find the electric field at point P. You are supposed to find the electric field at point P. So what will you do? You will basically join this point with one end of the rod. Is this correct, sir? No. Why? Because the end of the rod is not over here. Its end is at infinity. So you will have to move something like this. So we say if you move something like this, this will meet this rod at infinity. In case of infinitely long rod, you will have to move something like this. So now how much is this angle over here? This is theta 1. Clearly we can say theta 1 in this particular case is 90 degrees. If you join this point with another end of the rod, so you'll have to move with something like this. So this will be, we say, theta 2. And clearly in this particular case, theta 2 is also how much? We say, sir, 90 degrees. Theta 2 is also how much? We say 90 degrees. So in case of infinitely long rod, theta 1 and theta 2 are 90 degrees. Now use the general formula. Electric field will be K lambda by R. So we say here theta 1 is equal to 90, theta 2 is equal to 90. So I say electric field is equal to K lambda by R. Then we say sine of 90 plus sine of 90, sine of theta 1 plus sine of theta 2. Okay, then we say plus cos of theta 1, that is cos of 90 minus cos of theta 2 minus cos of theta 1, cos 90 minus cos 90. Again, this term will become 0. Cos 90 is 0, cos 90 is 0. So sin 90 is 1 plus 1 is 2. So electric field will be k lambda by r. 1 plus 1 is, we say, sir, 2. This is r. So that is 2k lambda by r. So this is the electric field. This is the electric field because of the infinitely long rod at r distance. Guys, is this clear? Please tell me in the chats. Electric field because of the infinitely long rod at r distance. Similarly, there is semi-infinite rod. There is semi-infinite rod. Here there is a derivation of for this one. I don't want you guys to go through this, okay? Because this is not required at all. But I would want you guys to directly remember. If you have got semi-infinite rods, guys, what is semi-infinite? See. This is a rod which is going till infinity from one end only. One end only. This is infinity. Another end is finite. Another end is finite. So I can say if you have to find the electric field at this point at r distance, okay? So this is semi-infinite. Semi-infinite means which is going till infinity from one end only. Another end is finite, located over here. Here electric field will be a root 2k lambda by r. Directly you remember. In case of infinitely long rod, electric field is 2k lambda by r. Okay, in case of this rod finite where theta 1 and theta 2 are equal, this is the electric field. Guys, please tell me in the chats if this is crystalline clear. Everyone means everyone. If this is crystalline clear. Great. Let's take a look at this question. See guys, you have got the two infinite long rods. You have got the two infinite long rods. This one. Okay. And it has got negative charge on it. And you have got this another one as infinitely long rod. It has got, we say, sir, positive charge. It has got positive charge. Okay. You guys are supposed to tell me what is the net electric field at the center. Guys. See. Because of this negatively charged rod, don't you think electric field will be towards the rod? Yes. And how much will be? We say this is an infinitely long rod. Because of the infinitely long rod, electric field is 2k lambda by, and this distance is r. Tell me one thing. Because of this infinitely long rod on which positive charge is present, electric field will be away from the rod. And how much that will be? 2k lambda by r. Why, sir? Because of the infinitely long rod, it is 2k lambda by r. So because of this 2k lambda by r, Now, can you please tell me what is the net electric field? That is 2k lambda by r plus 2k lambda by r. That is 2k lambda by r. We say plus 2k lambda by r. So that will be simply 4k lambda by r. And this was the question which was asked in NEET 2019. One more question on this one. On this rod concept. See guys. See guys, in this particular case, what is given over here is that we are given an infinitely long rod. Okay, at r distance, we have got a charge over here that is minus q, its mass is m. Now, it is saying that I gave the velocity v to the charged particle at r distance. We are given the v velocity to this charged particle, which is at r distance. Okay, it will follow the circular path. It says that this will follow the circular path. Okay, this will follow the circular path. Okay, now we are supposed to find what is the value of v. How much velocity, guys, this is the rod, here is the charge. How much velocity you should give to this charge so that it follows the circular path over here. Now tell me one thing, guys. We say here, two forces will act. One is centripetal, another is electrostatic. See guys. As of now, you remember one thing. If let's suppose you have got an electric field over here. Okay. And in this electric field, you place a charge. Remember it, please. We'll have to study this after some time. If you have got an electric field and if you place a charge in this electric field, we said this charge will experience the force, okay? Force will act on it, and that force is equal to this Q multiplied by this electric field E. Please directly remember it. Now see, here. Because of this wire, electric field will be present at r distance, okay? And that electric field is 2k lambda by r. You recently studied electric field because of an infinitely long rod is 2k lambda by r. And in this electric field, don't you think this negative charge is present? Yes. So force will act on this negative charge. So force on minus q due to electric field. How much that will be? F is equal to Q times of E. So F is equal to charge is Q and electric field is 2k lambda by r. This will be the force. Okay. So we got the first force acting on the charge, that is electrostatic force. What is the next force? That is centripetal force. Also centripetal force is acting on the charge. Also centripetal force is acting on the charge. And that centripetal force, I can simply say F is equal to, we say m v square divided by r. V is the velocity, m is its mass, and r is the radius of the circle. Now, as I have told you, these two forces will be equal, electrostatic force and centripetal force, as we know. We have already studied this, as we know. Centripetal force is obviously created because of the electrostatic force over here. So I can say this Fc is equal to, we say, sir, F electrostatic. And this is mv square divided by r. It will be equal to, that is 2k q lambda divided by, we say, r. We have to find the value of velocity. In this case. So I can simply say this velocity will be, so v square it is. So m will go down, r will go over here. So it will be v is equal to 2k q lambda r divided by, so we say this is m. Okay, r and r will cancel over here. Why am I doing this? So we say m will go down. So this is 2k q lambda divided by m, and it is square, so root will go over here. Is this clear? Is this clear? Please tell me in the chats, guys, if this is crystalline clear. If this is crystalline clear. Tell me in the chats. We say. Wasim Bhatt in the chats once again. Alia Bhatt's brother. Wasim Bhatt. वारिया ज़्यादा थोकुस यार अद के चीन हैक था Okay. Oh, HSP sir. HSP Baba sir. What's up? Good to see you in the chat, sir. Now, guys, let's move on to the next topic. Let's move on to the next topic. That is what we call the electric flux. That is what we call the electric flux. Okay. What does electric flux actually mean? We simply say electric flux is the number of field lines crossing the surface perpendicularly. Guys, see. Let's suppose I am saying that I have got a surface over here. I have got a surface over here. I have got a sheet over here. I have placed a sheet. And this is the electric field which is coming from, like you have placed some charge over here. Because of that charge, electric field lines are leaving. Okay, this is the electric field. These are the field lines which are leaving from that charge. Okay. Now, you are placing one more sheet over here. You have placed two sheets. You have placed two sheets. Okay. Now, guys, these field lines are crossing both of these sheets over here. These field lines are crossing both of these sheets over here. Now, clearly in this particular case, you can see how many number of field lines are crossing the surface A and how many number of field lines are crossing the surface B. 1, 2, 3, 4, 5. So in this case, I can simply say flux is 5. In this case, I can simply say, sir, flux is 3. Why? Because flux is the number of field lines crossing the surface. Here flux I am saying 5. Here flux I am saying 3. Only 3 are crossing. Here 5 are crossing. So can I say from this, guys, see, this flux is directly proportional to electric field. More is the electric field, stronger we place the charge over, more field lines will come. If more field lines cross this surface, let's suppose this is the board over here, more field lines are crossing the board, we say more will be the flux. So more is electric field, more is flux. And also this flux is proportional to area. See here, area is bigger, more field lines are crossing, flux is more. Here area is smaller, less field lines are crossing, so flux is less. So flux is directly proportional to area. Now combining these two, I can say flux is equal to electric field, or I can say something like this, that is E dot A, E dot A. Okay, or you can directly write this is EA cos of theta. Sir, why is this theta over here cos theta? I'll tell you. We say where theta is the angle between E and A, where theta is the angle between, we say E and A, where theta is the angle between E and A. Okay, where theta is the angle between E and A. Now guys, let's suppose I have got an area over here that is something like this. This is the sheet over here that is something like this. And through this sheet, I am saying this is the electric field which is crossing the sheet. This is the sheet and electric field is crossing the sheet over here. Now, what is the direction of area over here, guys? Always remember, if this is the sheet, direction of area is a vector or scalar, area is a vector quantity. Direction of area is always perpendicular to the surface. That will be something like this. So if this is the sheet, place something like this. We say direction of the area would be something like this. This is the area. And let's suppose this is the angle over here, that is theta. E and A, angle between E and A is theta. Tell me, if this is the sheet, this is the electric field, can I say this electric field will have got two components? It will have two components over here. Sir, this component, if theta is from this side, so this will be E cos of theta. And this will be, we say, E sin of theta. Tell me, which of the two components is crossing this sheet? Which of the two components is crossing the surface? Sir, E cos theta. E sin theta is just touching the surface. So we say here E cos theta is crossing the surface. Here E cos theta is crossing the surface. So it will create or produce the flux only. We represent this flux, electric flux, with phi. Okay. So now if you have to write the electric flux over here, what is the value of flux over here? If you have to write the value of flux, you can say flux will be simply, that is E cos of theta multiplied by area. So flux here will be EA cos of theta. That's why I told you this cos theta is over here. So you have to take that component of electric field which is crossing the surface. Let me give you one more example. So what is flux now, guys? Flux is the number of field lines crossing the surface perpendicularly. So if flux is crossing through this wall, so if field lines are crossing through this wall, flux will be produced. Now, let's suppose you have got a question something like this. This is the electric field. Okay, and this is the sheet. This is the electric field crossing something like this. And here, this is the angle theta with the horizontal. Can I say in this particular case, guys, this is the electric field and this component of electric field will be E cos of theta. Why? Because theta is from this side, so we take this as E cos theta. And this component of electric field we call at E sin of theta. Now tell me, which of the two components is crossing the surface over here? Sir, obviously here it is E sin theta. Here E sin theta is crossing the surface. Here E sin theta is crossing the surface. Here E sine theta is crossing the surface. So if I have to write the flux over here, you will write E sine of theta multiplied by area. Here cos theta is just touching the surface. So I can say flux in this case is EA sine of theta. EA sine of theta. Sir, what if we use that formula, EA cos theta? Use that also. Use that also. Phi is equal to EA cos of theta. You say, sir, theta is the angle between E and A. If this is the surface, don't you think that this will be the area over here? Yes. Area is always perpendicular to the surface. Now tell me, if this is the theta angle, how much will be this angle? This will be 90 minus theta. This is 90 minus theta. Now see, angle between electric field and area is 90 minus theta. So write over here. So this will be EA cos of, instead of theta, you write 90 minus theta. Because theta is the angle between E and A. Now cos of 90 minus theta is also sine theta. So this will also come out to be EA sine of theta. Tell me, is this question clear? Is this question clear? Please tell me in the chats. Everyone means everyone. Okay. Now, find the flux passing through the area. This is the electric field and this is the area. How much will be the flux in this particular case? In this case, we say flux is simply 0. Why? Because all of these field lines are just touching the surface. They are not crossing. Crossing means something like this. So we say here, no field line is crossing the surface. All the field lines are touching the surface. Tell me, find the outward flux through the cylinder. Guys, see. This is the cylinder. These are the field lines crossing. Okay. Now, here, outward flux. How much is the flux through this portion when it is coming out? We say when it comes to the flux, that is EA cos of theta. Guys, see. What is the area of this portion? Area of this portion. We say area of this portion of the cylinder is simply pi if the radius is given as r. So we say that is pi r square. Okay. And what is the area, direction of area? Direction of area is this. So angle between E and A is 0 degrees over here. So I can simply say flux in this case will be E. Instead of area, I can write pi r square and then I'll write cos of 0. Cos 0 is 1. So flux will come out to be E pi r square. This is the outward flux. This is the outward flux. This is the outward flux. Now take a look at this question. We have got a cube over here. We say these are the field lines going in. We say let's suppose this area surface has got area S. So flux in will be, sir, E into S. Okay. Okay. Why should we write V minus over here? Why? Because area of this will be something like this. This is area. Angle between A and E is 180 degrees. Guys, see flux. Let me write the flux in. Flux in. When field lines are going in, flux will be simply, that is EA cos of theta. Cos is 180 degree. Cos of 180 is minus 1. So that is minus E into A. And when these field lines are coming out, we say here this is the area of this surface. Area of this surface, this face. So here E and A has angle 0 degrees. So flux out will be simply, that is plus, that will be simply EA cos of 0 degrees. Cos 0 is 1, so plus EA. Now, could you please tell me how much is the net flux? Net flux will be minus EA plus EA. That will be 0. So always remember, if flux in is equal to flux out, net flux is 0. Give me the signal. Give me the signal in the chats. Give me the signal in the chats. Please, please. Everyone means everyone. Is this crystalline clear? Is this crystalline clear to each and every single student? Let me know in the chats, guys. Okay. In this particular case, I was asked only to find the outward flux. Outward flux is flux through this portion only because field lines are coming out. So that's why I take this as E into A. A is pi r square. Let's talk about the Gauss law. What does the Gauss law actually say? Guys, see. Now I will have to finish the electrostatics completely, electric charges and fields, then only I'll give you the break. Now see, wait, I will tell you how much time it will take to complete. Hmm. 129. Ho. It will take 1.5 hours. After 1.5 hours, I'll give you the break. Now, see, Gauss law. What does Gauss law actually say? It says that flux through any closed surface is equal to the charge enclosed divided by epsilon naught. What is that? Let's suppose, my dear friends, I'll take over here a cylinder. This is the cylinder that I'm taking. And inside the cylinder, I have placed a charge that is Q. And we know that, sir, because of the charge, field lines will come out. These are the field lines coming out of the surface. Okay. Now, don't you think that these electric field lines are crossing the surface of the cylinder? We say here, field lines are crossing. Your field lines are crossing the surface of the cylinder. Your field lines are crossing the surface of the cylinder. So can I not say flux is created? So flux is created. Now, if I ask you, how much is the flux created through the walls of this closed surface, through the walls of the cylinder? That is given by Gauss law. So we say that flux is given by Gauss law. And I can say that flux will be simply flux is equal to that is flux through any closed surface. I'll write over here flux through any closed surface. Closed surface means cylinder, sphere, all of these are closed, is equal to charge enclosed, whatever is the charge present inside, okay, charge enclosed divided by epsilon naught. This is Gauss law. Gauss says that if you place a charge inside any closed surface, field lines will come out of that charge and it will cross the walls of the closed surface. How much is the flux created through the walls? That is Q by epsilon naught. Next, Q by epsilon naught. Next, let's suppose we have got this cylinder over here and charge is inside the cylinder. How much is the flux through? That is Q by epsilon naught, because flux through any closed surface is Q by epsilon naught. Even if you take a cube, inside this cube you have got a charge. So we say flux through this surface, closed surface, no matter whatever is the closed surface, we say flux will be Q by epsilon naught. Flux will be Q by epsilon naught. Okay. Next, let's suppose you are given over here a cylinder and charge is placed at the mouth of this cylinder. It is not enclosed. We cannot consider this charge as an enclosed charge. Keep that thing in your mind. We cannot consider this charge as an enclosed charge. Keep that thing in your mind. Okay. Now guys, understand one thing. Understand one thing. What is that? What is that? That is in this particular case, what you will do is that, let's suppose you have got this cylinder over here. You have got this cylinder over here. Let me show you how to solve these questions. This is the charge. What you will do is that you will connect one more imaginary cylinder. Imagine you have connected one more cylinder over here. Okay, of the same size. Now, don't you think that this charge comes in between of these two cylinders? Okay. Now, we say for this charge, we say this is now closed surface. Closed surface. Okay. Now, this charge behaves like an enclosed charge. So, we say, guys, if I say in this particular case, flux through a closed surface is equal to, guys, we say here closed surface is made of one cylinder or two cylinder, two. For this charge, if I say this charge is present in the center, then closed surface will be only because of one cylinder. Now it is present over here, that's why I have added one more. So that will be flux through two cylinders. Okay, and that will be Q divided by epsilon naught. Because we know flux through two cylinders will be Q by epsilon naught, or flux through closed surface will be Q by epsilon naught. How much will be the flux through one cylinder? Take this 2 over here. So I can say flux through one cylinder will be Q divided by 2 epsilon naught. Or simply, guys, if flux through two cylinders is this much, flux through one cylinder will be half of this one. So flux through one cylinder will be 1 by 2 of Q by epsilon naught, and that is Q by 2 epsilon naught. Tell me, how much is the flux through one cube? How much is the flux through one cube? How much is the flux through one cube? Generator ka band. Power off. How much is the flux through one cube? See guys, this charge is present at the edge of the cube. Is this charge the enclosed charge? No sir, this is not the enclosed charge. If you have to make this an enclosed charge, how many cubes you are supposed to add? Sir, one cube from this side, another cube from this side, and another cube from this side. So we say here, add 3 more cubes, 3 more cubes to make the charge as enclosed. Okay, enclosed charge. Add 3 more cubes to make the charge as enclosed charge. Now guys, so this cube, one more cube, and one more cube. How many number of cubes in total? 4 cubes. So I can say here closed surface is because of 4 cubes. So I can say flux through a closed surface will be flux through 4 cubes. Okay, and that will be flux through 4 cubes, and that will be Q divided by epsilon naught. Okay, that will be Q by epsilon naught. Now, my dear friends, this is the flux through 4 cubes. This is the flux through closed surface. How much will be the flux through 1 cube? That will be 1 by 4 of Q by epsilon naught. That is Q by 4 epsilon. आवाज करायचं बोल ना तू हँडल हो ठीक आहे जा Next, tell me guys, if the charge is present at the corner, if the charge is present at the corner of this cube, what will be the flux through 1 cube? Guys, is this the enclosed charge? No. You have to make this as an enclosed charge. So how many cubes you will add? 1, 2, 3, 4, 5, 6, 7. Total of 8 cubes. We say add 7 more cubes. 7 more cubes. Add 7 more cubes to make the charge as enclosed charge. Add 7 more cubes to make the charge as enclosed charge. Now guys, I can say flux through closed surface will be flux through 8 cubes. Okay, here closed surface is made up of 8 cubes for this charge. If I say this charge is present at the center, then in that case this cube will behave like a closed surface for this charge. But since the charge is at the corner, so that will be Q divided by epsilon naught. Now, flux through 1 cube will be how much? That will be 1 by 8th of, that is Q by 8 epsilon naught. I hope this is clear. Okay, this is a good question actually. This is a good question. We have got a cylinder over here, and charge is present at the cylinder, inside the cylinder. Find the flux through, if this is given as if flux passing through R means this curved surface, R means this curved surface, R is curved surface, curved surface. If flux passing through the curved surface is phi, let's call it this as phi naught, okay? Then find flux through Q. Guys, see. In this particular case, it says that we have got a cylinder. And we know because of this charge, field lines will come out of this charge, something like this. Something like this. These are the field lines which come out of the charge, something like this. Okay. Now, these field lines are crossing the three surfaces. These field lines are crossing the three surfaces. Which one? This plane surface of the cylinder, if we talk about the cylinder, it has got three surfaces. If this is a cylinder, this is plane surface, this is one more plane surface, and this is the curved surface. Okay? This is the curved surface. So I say, in this particular case, can I say flux through the entire cylinder? Entire cylinder is equal to flux through the curved part, curved surface, plus flux through two plane surfaces. This is one plane surface and this is another plane surface. So flux through two plane surfaces plus flux through curved surface will be equal to the flux through the cylinder. Will be equal to the flux through the cylinder. Okay. Now guys, how much is the flux through the cylinder? That is the flux through the closed surface. So I can say this will be Q divided by epsilon naught plus flux is equal to flux through curved part. Flux through curved part, that is given as R, is given as phi naught. Flux through curved part is given as phi naught. Plus, this is flux through two plane surfaces. This one and this one. That is two plane surfaces. Now guys, take it over there. So flux through two plane surfaces is equal to Q by epsilon naught minus, we say, sir, phi naught. Now flux through one plane surface will be how much? Half of this one. This is the flux through two surfaces, two plane surfaces. Flux through one plane surfaces will be half of this one. So flux through one plane surface will be 1/2 of, we say, Q by epsilon naught minus, we say, phi naught. Is this clear? Is this clear? Is this clear? Great. Great. Now guys, let's talk about this one. Find the flux through the curved part. Guys, if the flux through this part is given as phi naught, what is the flux through the curved part? Guys, see. Let's suppose there's a closed surface over here. There's a hemispherical bowl over here which is closed. So I say in this particular case, flux through closed surface will be flux through this bowl, okay? And this bowl is made of two surfaces, curved and this plane. So that will be flux through, I can say plane surface plus flux through curved surface, okay? So now flux through closed surface is given as how much? Sir, that is, we know, Q divided by epsilon naught is equal to flux through plane surface in this case is phi naught. Okay, plus we say flux through curved surface. Now take it over there. Flux through curved surface will be Q divided by epsilon naught minus, we say, phi naught. Is this clear? Now guys, in this particular case, you guys are supposed to tell me what is the flux through the sphere. What is the flux through the sphere? What is the flux through the sphere? I would want you guys to tell me. Tell me, guys. Now, guys. Now see. You guys are supposed to tell me what is the flux through this sphere. Now, guys, I can simply say flux will be created because of this part, because of this much of charge. Whatever is the charge placed on this part of the wire, we say flux will be produced because of that only. Now, first you have to find the charge. So we say, let's first find the charge. Let's first find the charge enclosed in the sphere. So we have to first find the charge which is present in the sphere. See, guys, let's find the length first. If we find the length, we would be able to find the charge. If this is r by 2, what will be this length? What will be this length? Sir, this is r, because this is radius r, this will be also r. Now, if this is r by 2, this is r, let's call this distance, this length as x. Now, this is a right angular triangle. Can I say from this particular triangle, we say from the triangle. Can I say from this triangle, I can say, sir, this hypotenuse square, that is r square, is equal to base square, that is r square by 4, because r by 2 whole square becomes r square by 4. Then we say plus this perpendicular, that is x square. We have to find x, take it over there. So this will be r square minus r square by 4. Then we say is equal to x square. Now 4r square minus r square by 4, that is 3r square by 4 is equal to x square. Take it over there, it becomes root. So x will be, we say a root 3. This square and this square goes, and this is r upon and root, and if this square comes over here, it becomes root 4, that is 2. So value of x is 2. Now if this is x, don't you think that this is also x? So x plus x is 2x. So I write 2x will be simply, that is 2 root 3r divided by 2. This 2 and 2 will cancel, that is a root 3r. So this is the length of the rod present inside the sphere. Now let's find the charge. Guys, see, we say as lambda is equal to q divided by L. So from here we can find the charge, that will be lambda into L. Now I can say q is equal to lambda. When we have the rod, we take lambda. And what is the length of the rod present inside? That is a root 3. That is root 3, we say r. That is a root 3r. In the question, lambda was given, charge per unit length. Now tell me, now I can say flux through a closed surface will be q inside divided by epsilon naught. How much is the charge enclosed? So that is we say simply lambda root 3r divided by epsilon naught. Guys, is this clear? Is this clear? Please tell me in the chats, is this question clear? This was actually a good question. This question was a previous year question of JEE Mains. Okay. There should be lovebirds also in the chats, huh? Every time I see in my chat some lovebirds hanging over there, huh? And I recently saw a comment saying, "Bhai tu ladka hai ki ladki?" This naam ka. And I'm like, and to all those lovebirds, please do like my session. Huh? At least like this session. That is mandatory. Marking the attendance is mandatory. Last spatyum köşriyasa. Now guys, look at this question we have got on the screen, okay? See, we have placed a charge inside this cube at what distance from this face? A, B, C, D means this face, okay? At what distance? We say, sir, L by 2. Now. We say here, outside this, at L by 2, we have placed another charge. Guys, in this particular case, we say because of this charge, field lines will come out and it will cross this face. These are the field lines which are coming in. Now, because of this charge also, field lines are going something like this. It is crossing, it is going out. So, the number of field lines which are crossing something like this through this face will be equal to the number of field lines something like this. So net flux through ABCD is equal to 0. That will be 0. Because the flux going out is equal to flux going in. So net flux in this case will be 0. Okay. Yes. Now guys, we have the next topic over here. The next topic is electric field due to a hollow sphere. Electric field due to a hollow sphere. Okay. Now guys, I would want you guys to focus over here. See, hollow sphere means which is hollow from the inside. Like you have football. Football is hollow from the inside. We consider that as a hollow sphere. Cricket ball or leather ball, that is filled from the inside. That's a solid sphere. So in case of hollow sphere, I'll just mention this point over here. In case of hollow sphere, we say charge is present on its surface only. Charge is present on its surface only. In case of hollow sphere, charge is present on its surface only. So I can clearly say charge inside will be 0. Okay. Now since this sphere has got a charge on it, so it will create the electric field. Everything which has got charge creates electric field. So it creates electric field. Now we have to find the electric field at 3 different positions. We say outside the sphere at small r distance, on the surface of the sphere at capital R distance, and inside the sphere at small r distance. Inside the sphere at small r distance. Okay. Now guys, if we talk about outside the sphere. Outside the sphere at what small r distance? Now tell me one thing. If I give you a big hollow sphere, okay, you'll place it on your head, and your friend is looking at you from 2 kilometers away. He's 2 kilometers far from you and he's looking at you. Tell me, Do you think that he would be able to see the complete big sphere on your head, or he would be able to see just a point on your head from 2 kilometers away? We say just a point. So from very large distance, we consider this sphere as a point charge. So whatever is the electric field because of the point charge, same will be because of the sphere. So how much is the point charge? We say electric field because of the point charges, that is K. Charge on this is Q divided by, at what distance? We say, sir, R square. I'll write over here, because at very large distance, we consider it a point charge. At very large distance, we consider it a point charge. Now guys, tell me one thing. If you keep on coming closer to the sphere, when you reach onto the surface, don't you think that at surface, value of small r becomes equal to the value of capital R? So we say on the surface, I can say value of small r is equal to capital R. So instead of this small r, you'll put over here capital R. E is equal to K Q divided by capital R square. And when it comes to the inside the sphere, guys, inside I can clearly say Q inside is 0. If there is no charge, if charge is 0, do you think that electric field will be there? We say, sir, no. So electric field inside is 0, because we say electric field is because of the charge only. If charge is 0, electric field is 0. Next. Okay. Let me plot the graph. Guys, see. Let me plot the graph. That is E versus R. Let me plot the graph between E versus R. Okay. E versus R. Guys, understand one thing very, very, very carefully. When it comes to the center means where R is equal to 0. That is inside point. We know, sir, inside electric field is equal to 0. We know, sir, electric field inside at every point is 0. So graph inside will be 0 at center. This is center. Origin, electric field is 0. Now guys. So we say from center to surface, electric field is 0, because all of these are inside points. So I'll make the graph on this line only. Okay, till this. Sir, why not over here? Because if electric field would have some value, then I would have made it something like this. Some value. But it is 0, so I'll make it 0. Till what? Till R is equal to capital R, and that is surface. Okay. And if we check outside the surface, we say electric field is inversely proportional to R square. Okay. Okay. So I can say, we say outside, it will be something like this. Electric field is inversely proportional to R square. And this is the surface, and this is inside. And inside we say electric field is equal to 0. We say outside electric field is equal to inversely proportional to R square. Is this clear? So this is the graph in case of electric field in case of hollow sphere. Now let's talk about a solid sphere. Let's talk about the solid sphere. Guys, see, when it comes to the solid sphere, we say in case of solid sphere, charge is present inside also. Charge is filled inside also. So I say in case of, a solid sphere, charge is filled inside also. In case of a solid sphere, charge is felt inside also. Okay. Now, my dear friends, I would want you to focus exactly over here. I would want you guys to focus exactly over here. What is that? What is that? See, we have to find the electric field because of this outside surface inside. When it comes to the outside, understand one thing very carefully. When it comes to the outside, guys, if I place a big hollow or a solid sphere on your head, again your friend is looking at you from 2 kilometers far distance, don't you think that this also will appear to him as a point? So it looks like it is a point on his head. It looks like it is a point charge on his head, even if it is a hollow sphere or it's a solid sphere. So I can say electric field here also will be kq divided by small r square. Because here also we consider this as a point charge. Okay, yes. Now, if we talk about the surface, don't you think that in case of a surface, value of small r is equal to capital R? In case of a surface, value of small r is equal to capital R. So I'll write over here, electric field is equal to kq divided by capital R square. Okay. Now, when it comes to the inside, guys, right now, inside, see, always remember this R is variable, guys, this R is variable. So we say inside you have to find the electric field at the small r. For outside point, we say this R is greater than capital R. Capital R is the radius. For inside point, R is less than capital R. R is variable. Small r is variable. So we say inside electric field in this particular case will be, that is kq divided by r cube into, we say, sir, this R. Okay. So this is the electric field inside. This is the electric field on the surface. This is the electric field outside of the solid sphere. Now, tell me one thing. When it comes to electric field inside is directly proportional to small r. Electric field outside is inversely proportional to small r square. And if I try to plot the graph, that is E versus small r. Guys, see, I'll say, sir, at the center electric field will be 0, because at center, when r is equal to 0, I can say electric field will be 0. Put r is equal to 0, electric field is 0. So graph is starting. Why r cube? Because there is a long derivation over here. From that derivation only this r cube comes over here. Okay. I ignored that derivation because this is the NEET 2025 series. That's fine. So we say at center, electric field is exactly 0. But as you move away from the center, electric field increases with r. Electric field is directly proportional to r. So then we say it will become something like this. So E is directly proportional to R. We say till what? Till inside. We say till inside. Okay, where R is equal to capital R. And when it comes to the outside, it is a rectangular hyperbola. So E is inversely proportional to R square. This is outside and this is inside. And this will be the surface. Guys, please tell me in the chats if this is crystalline clear. Tell me in the chats if this is crystalline clear. Already I gave you the break at, guys, I gave you the break at 8 o'clock, okay? From 8 to 8:40 we were having break. So now from 8:40 till right now it is 10:40. Only 2 hours. Okay. Wait. What are you guys doing? See, 100 slides I have already finished. So I hope this is crystalline clear to each and every single student. Now take a look over here, guys. Take a look over here. We have got the 3 solid spheres over here. Okay. This solid sphere has got charge Q and its radius is r by 2. You have to find the electric field at point P, which is at r distance. Obviously, r distance will be outside the sphere. Then you have got another sphere which has got charge 2q. And in this case, the radius is r. Here also you have to find the electric field at r distance, but here that point will lie on the surface because it has radius r. And then we have got the bigger sphere. It has got radius 2r. Again we have to find electric field at we say r distance. So here r distance lies inside. Here r distance lies inside. Why? Because it is having the radius 2r. Let's first find the electric field over here. That is, let's suppose E1. So we say E1 is equal to, guys, this point P is outside point or inside or surface point. Obviously it is outside. Point P for this sphere is outside point. So I say we'll use the outside formula, that is KQ divided by small r square. And sure, I'll write, when it comes to the outside the sphere, what is the formula? KQ by small r square. So K and charge over here is Q, and at what distance you are finding? This is R. So this will be capital R, because in this case small r is capital R. Let's find E2. And this is outside point. Let's find E2. E2 is the surface point. How much is the electric field on the surface of the sphere? KQ by its radius square. So we say, sir, KQ divided by R square. So that is K. How much is the charge over here? 2Q divided by radius of this one is capital R square. And I'll write this as the surface point. Now, let's talk about this point. This is the inside point. What is the formula for inside point? We say E3 is equal to KQ small r divided by capital R cube. Now here we say this is KQ. Q is 4Q. 4KQ instead of small r. Small r is the distance where you have to find the electric field inside. Small r is over here, capital R, divided by r cube. R cube is the radius. So that is 2r cube. Okay, and it will be that is 4KQR divided by 2 into 2 into 2 is 8r cube. This and this 4 ones are 4 twos are. So that is KQ divided by 2r square. 2r square, and this is inside formula. Okay, done and dusted. Even this question was asked in JEE Advanced 2014. This question is from the JEE Advanced 2014, and this is complete the NEET based question. Okay, now tell me which electric field is over here more. I can here 2Q is divided with R square. Clearly I can say E2 is greater than, we say E1 is greater than, we say E3. This was the order. This was the order. This was the order. Solve this question, guys. Are you able to see these values over here? Yes. Tell me the answer of this particular question. Find the electric field at P and S. P is this point, S is this point. Find the electric field at P and S. You guys are supposed to tell me what is the value of the electric field at P and S. Okay. What is the value of the electric field at P and S? See. Guys. This is given as 2R from here to here. This is point P. This is point S. This distance is given as 4R. There is plus Q charge over here. This radius is given as R. This is plus 2Q. This is 3R. And this is plus 3Q. I hope now it is visible clearly. Now guys, if we have to find the electric field, let's first find the electric field at S. Okay, we say electric field at S. Guys, understand one thing very carefully. We say electric field at S. Guys, this S is the outside point for this sphere. This S is the outside point for this inner sphere and for this charge also. Don't you think that because of this sphere at S, electric field will be there? So how do we write that? That is K. Q is how much for this sphere? Q is 3Q. That is 3Q divided by, at what distance you are finding? 4R. So it will be 4R whole square. KQ by R square. Outside point we use KQ by R square. Then we say plus. Because of this inner sphere, how much is the electric field at this point? Sir, that is K. Charge on inner sphere is, we say, sir, 2Q. Okay? Because for this inner sphere, this point is outside point. At what distance? 4R. Again, this will be, sir, 4R whole square. Then we say plus. For this charge which is placed exactly at the center, this point is outside point. At what distance? 4R. So it will be KQ divided by 4R whole square. I think you can take common in this particular case as we say KQ divided by 4R square. Okay. Now what remains in the first one? KQ divided by 4R square. In the first one, it remains 3 plus. In the second one, it is 2 plus third one, it is 1. Okay, so 3 plus 2 plus 1 is how much? 6. Okay, I'll tell you this once again. So I can say this is K6KQ divided by 4R square. What I'm trying to say is that, guys, see. I say you have to find the electric field at this point. Electric field at this point will be because of this sphere, because this sphere has got plus 3Q charge. So this is the outside point. Because of this, electric field at this point will be because of this inner sphere also. Electric field at this point will be because of this sphere also. Why? Because of this charge also. Why? Because this is the very far point, away point. And I calculated because of all the three and it came out to be this one. Okay? 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 Yeah, this is 4R whole square. This is 4R whole square. 4R whole square. And this will be, this is 16KQ upon, sorry. This is 6KQ upon 4 square is 16R square. Yes. I corrected. Next we have to find the electric field at P. We say electric field at P. Guys, tell me one thing. If we talk about this point P, at point P, electric field will be because of this charge, because this is at away point. This point P is outside point of this sphere. So because of this sphere, electric field will be at point P. But because of this outer sphere, this point P is the inner point. So don't you think that electric field because of this outer sphere inside is zero? Yes. So let me just write over here. I say electric field at point P is equal to, because of the outer sphere, how much is it? Zero. Why, sir, zero? Because of the outer sphere, this point is the inner point. So electric field inside the hollow sphere, this is the hollow sphere, it is zero. These are the hollow spheres. Okay. And when it comes to electric field because of this sphere, guys, because of this sphere, this point is outside point. Okay. Now it is at what distance from the center? 2r. So it is K. Charge on inner sphere is 2q divided by 2r whole square. Similarly, because of this charge also, it will be plus kq divided by, at what distance? That is 2r whole square. So electric field at point P will be simply, in this particular case, what can you take common? That is kq divided by 2r whole square. Okay, and here it is 2 plus 1, that is 3. That is 3. Is that clear, guys? Is that clear? Okay. Yes. Tell me the answer of this question. Guys, give me the signal in the chats. Is this crystalline clear to each and every single student? Tell me, is this crystalline clear to each and every single student? Now guys, this is the question we have. The electric field at the 20, this is a hollow. It is mentioned over here, uniformly charged non-conducting sphere. Okay. Uniformly charged non-conducting sphere. Now consider this as, you just mentioned it directly over here. Directly mentioned over here, hollow sphere. Hollow sphere. Hollow sphere. Because when it comes to the conducting sphere means hollow sphere. Non-conducting sphere means solid sphere. This is a hollow sphere over here. Okay. The electric field of the sphere at 20 centimeters is, find the electric field at 5 centimeters. How much will be the electric field at 5 centimeters? This is your homework. Okay. Zero. If I am saying this is a hollow sphere, outside electric field is given as E, that is fine. But when it comes to the inside, radius is 10 centimeter, inside is 5 centimeter. So we say inside electric field will be obviously how much? Zero, because in case of hollow sphere, inside electric field will be zero. Inside electric field will be zero. Okay. Okay. Yes, 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 yes. I think we should take a break, huh? Let's take a break. We'll take a break of, we say, what is the time right now? Break is till 11:25. Shall we take a break or we'll continue, guys? Shall we take the break or shall we continue? What do you guys say? Tell me in the chats. Okay, let's take a break of, we say 20. So we say break till 11:25 p.m. check. Okay, guys. Back to business. Come on. Let me know in the chats. Am I perfectly audible? Yes, great. Now guys, in this particular case, let's first discuss over here electric field due to an infinitely long non-conducting sheet. See guys, till now I told you I have got a rod. What is the electric field because of the rod? I told you I have got a ring. What is the electric field because of the ring? Now I'm saying that I have got a sheet over here. This is a big sheet, infinitely long sheet. What is the electric field because of the infinitely long sheet at this point P? Okay. Since this sheet has got a charge, so it will create the electric field. We say since the sheet has charge on it, so it creates electric field. Okay. Now guys, we are supposed to find the electric field at point P. So I can say at point P, guys, when it comes to the sheet, we take basically sigma. We use sigma. Sigma is charge per unit area. In case of the sheet, we take sigma, that is charge per unit area. So I can say electric field at point P will be sigma divided by 2 epsilon naught. So this is the electric field because of a non-conducting sheet. Okay, another one is conducting. Non-conducting sheet, okay, that is sigma by epsilon naught. Now guys, tell me one thing. Can I say as when it comes to sigma means charge per unit area, total charge by total area. Let's suppose area of the sheet is A and charge I am saying over here is Q. So can I say this electric field we can write over here as Q divided by 2A epsilon naught. This comes out to be the electric field. Now, can I say this is the electric field due to a sheet? This is the electric field due to a sheet in terms of charge. And this is the electric field due to a sheet in terms of sigma, that is charge per unit area. Okay. Next, and one more thing. Guys, this electric field does not depend upon the distance from the sheet. Because if we are taking this as infinitely large sheet, if you find the electric field at this point from the sheet, same will be at this point, because all of these, for this infinitely long sheet, all of these points are, we say, same. We can consider these are the similar distance. Now, next, we have got conducting sheet. What is the difference between conducting and non-conducting? Guys, conducting looks something like this. It is basically made up of kind of two sheets over here. From on this surface, it has got charge. On this surface, from the back side, it has got charge. In between this, it doesn't have the charge. In between, it doesn't have the charge. Okay? In between, it doesn't have the charge. So in between, it doesn't have the charge over here. Okay. Now guys say, when it comes to electric field because of the non-conducting sheet at this point P, I would want you guys to focus over here. Is it a lag? I guess it's fine now. I guess it's fine now. I guess it's fine now, huh? Just a second, guys. There is some issue. Okay, now see, we have got a conducting sheet. We have to find the electric field because of the conducting sheet at this point. Guys, see, we say at point P, due to a conducting sheet, guys, understand very carefully. At point P, due to a conducting sheet, I can say electric field will be, we say sigma divided by, we say epsilon naught. Sigma divided by epsilon naught. And when it comes to sigma over here, I can say here, this sigma will be, what does sigma actually mean? Sigma means total charge by total area. How much is the charge over here? Charge, we say that is Q. Q is shared over here. Divided by total area. Area in this case is how much? For this sheet, we take area as A. For this sheet, we take area as A. So in total, I'll take the total area as 2A. In this case, I'm taking the total area as 2A. Keep that thing in your mind because there are two sheets. So electric field will come out to be Q divided by, instead of sigma, that is Q by 2A epsilon naught. Guys, you can see over here, electric field because of the non-conducting sheet in terms of charge, and electric field because of the conducting sheet in terms of charge is exactly same. Why? It is because if you have distributed the 10 Coulomb of charge over here, you are distributing on two sheets. Here, you are distributing the 10 Coulomb charge on one sheet. So here density is different. Density will be different, but charge is same. Okay. So we say density is different, charge is same. So that's why in terms of charge it is same. We say in terms of Q, electric field for both is same. Why? Because both have got the same charge. Here it is distributed on two sheets. Over there it is distributed on one sheet only. Okay. Yes. Now guys, I would want you guys to focus exactly over here. Now we have got the cylinders over here. Let's suppose I have an infinitely long cylinder. Over here. Okay. We are done with the sheets. We are done with everything. Now we have the cylinders. So this is a long cylinder and this is a hollow cylinder. I say this is a hollow cylinder. hollow cylinder. Guys, understand one thing very carefully. When it comes to a hollow cylinder, we say since charge is present on the cylinder, so it creates the electric field. Now guys, don't you think that, understand this point very carefully, don't you think that if you have a long hollow cylinder with you, okay, and your friend is looking at you from very far distance, from 1 kilometer, 2 kilometers away, don't you think that this hollow cylinder will look like to him it is you are holding some sort of rod, you are holding some sort of wire or rod, I can say line charge? Yes. So we say, guys, if I am saying you have to find the electric field at r distance from this hollow cylinder, that is at small r distance, outside, at very far. If I talk about outside the cylinder, guys, see, can I not say whatever is the electric field because of the infinitely long wire? Because from very large distance it looks like an infinitely long wire, infinitely long rod. We say electric field will be same, that is 2k lambda by r. Because of the infinitely long wire, electric field is 2k lambda by r. So I'll write over here, because from very large distance we consider it a infinite rod, infinitely long rod. Like from very large distance you consider a hollow or solid sphere a point, similarly you consider this as an infinitely long rod. Okay? Yes. Now guys, understand one thing very carefully. If I talk about on its surface, don't you think that on the surface, if you keep on decreasing this r, we say this is the center axis, we say this is the radius of the cylinder, we say on its surface, we say the small r becomes equal to capital R, small r becomes equal to capital R. So whatever is the value for this, so same will be over here, but here it is capital R. So electric field on the surface, this is electric field outside. So this will be simply 2k lambda divided by capital R. And guys, when it comes to the inside, in case of hollow cylinder, we say charge is present on its surface. Charge is present on its surface. So inside, we say Q inside is 0 over here. If Q inside is 0, electric field inside will be 0. Electric field inside will be 0. Okay? Electric field inside will be 0. Could you please tell me in the chats if this is crystal and clear? Tell me guys, if this is crystal and clear. Yes. Now, what will be the graph E versus R? Guys, we say from center till surface, electric field is equal to 0. And outside, clearly E outside, you can see over here. We can say E outside is inversely proportional to R. So we say from center, at center R is equal to 0, electric field is equal to 0. From center till surface, electric field is equal to 0. Okay, and this is surface, okay, where R is equal to capital R. And then this is inversely proportional to R. E is inversely proportional to R, and this will be outside. Okay. Okay. So outside this is the graph, inside this is the graph over here. Is that clear? Is that clear? Guys, give me the signal in the chats if everything is crystalline clear. Give me the signal in the chats if everything is crystalline clear. Great. Now guys, let's take a look at this particular question first. Let's take a look at this particular question first. We have two parallel non-conducting plates. This is a non-conducting plate. This is one more non-conducting plate over here. Okay, either you call it the sheet or you call it the plate. Okay, or you call it the plate. You have got 3 points over here. This is A, this point is B, and this point is C. You guys are supposed to tell me, you guys find the electric field at A, B, and C. Okay, you guys are supposed to tell me where, find the electric field at A, B, and C. Guys, the very first thing over here is, when it comes to electric field at this point B, you tell me only where it is non-zero and zero. At B, because of this electric field will be towards the sheet. Okay. And since it is a non-conducting sheet, what is the electric field because of the non-conducting sheet? See, electric field because of the non-conducting sheet is sigma by 2 epsilon naught. So I say it is sigma divided by 2 epsilon naught. This is electric field due to negative sheet. And because of the positively charged sheet, we know electric field will be away from the sheet, and this will be also, that is sigma divided by 2 epsilon naught. Okay, yes. So we say because of the negatively charged sheet, electric field is towards the sheet. Because of the positively charged sheet, electric field is away from the sheet. And what will be the net electric field in this particular case? Net electric field will be this plus this, that is 2 times sigma divided by 2 epsilon naught. This and this will cancel, so it will come out to be sigma by epsilon naught. Sigma by epsilon naught. Now, when it comes to the C point, so at C point, electric field because of the negatively charged sheet is towards the sheet. This is electric field due to negatively charged sheet. Electric field because of this sheet is away from the sheet. Electric field because of the positive charge is away from the sheet. And these two electric fields will cancel each other. Net electric field at C will be 0. Sir, why? Why? We can, sir, this C point is far from this one. So electric field because of C, because of this sheet should be 0. Because of this sheet should be less. No. Guys. This electric field in case of the infinitely long sheet does not depend upon the distance. It does not depend upon the distance. I am saying at point C, because of this sheet, electric field is towards the sheet. At this point, electric field because of this sheet is away from the sheet. Both the electric fields will be equal. Why? Because it does not depend upon the distance from the sheet. So that's why we say both will be equal. Net is 0. Similarly, at point A, electric field because of this sheet will be away. This is electric field due to positive sheet. Electric field because of the negative sheet will be towards. Okay. And here also net electric field will be 0. At A and C, electric field is 0. At B, electric field is non-zero. At B, electric field is non-zero. Let's suppose I ask you the question something like this. Tell me the answer of this question first. Let's suppose I ask you the question something like this. Find the value of sigma. Guys, if the charge Q is in the equilibrium, if the charge Q is in the equilibrium, find the value of sigma if the charge Q is in the equilibrium. See guys, I have got a sheet over here. This is the sheet, and I'm connecting a thread to this sheet. This is the thread connected to this sheet. And this thread has got a sphere attached over here which has got charge Q and its mass is M. And it is in the equilibrium. Equilibrium means it is at rest over here. It is not moving forward, backward. Okay. We are supposed to find what is the value of sigma. What is the value of charge per unit area of this sheet so that this remains in the equilibrium. Okay. Guys, understand one thing very carefully. Is this clear till over here? First give me the signal, guys. Please give me the signal, then only I'll move forward. Let me know in the chats if this is crystalline clear to each and every single student. Okay, great. Now see guys, we say since the charge is in the equilibrium over here, let's draw the forces acting on this charge. We say, sir, this is M into G. And in this one, you have got tension. This is the tension force in the string. If this is given as theta, this component of this will be also theta. So this will be T cos of theta. And this component of force will be T sine of theta. And guys, this sheet is also repelling this charge with a force that is what we call the electrostatic force. And this electrostatic force will be equal to Q times of E. I am supposed to find out if this metal is in the equilibrium. What is the value of sigma? Now balance these forces, okay? Whenever you hear the word equilibrium, remember one thing, you draw the forces and balance the forces. So we say balance the forces. So I can say this T sine theta is equal to, I can say this T sine of theta will be equal to, that is Q times of E. And I can also say this T cos of theta will be equal to, that is M into G. So TT will cancel if you divide these two. So tan of theta will be equal to QE divided by MG. Okay. Now guys, tell me one thing. Can I say this will be, take it over there. So this will be mg tan of theta is equal to q times of E. What is this E? E is the electric field because of this sheet. Guys, if you are saying you have charge over here, how much is the force on the charge? Electric field multiplied by charge. How much is the electric field over here? This is charged conducting sheet. Because of the conducting sheet, we say electric field is, we say sigma divided by epsilon naught. Okay. You have to find the value of sigma. Now take this over there. So sigma will come out to be, that is mg epsilon naught. Then we say tan theta divided by q. This is the value of sigma. Is that clear? Is that crystalline clear to each and every single student? Tell me guys, tell me. Tell me guys, is this crystalline clear? It is not confusing at all. It is simple. It is simple. I am saying that instead of this electric field Q into E, electric field here is only because of this sheet. This sheet is the only thing which is creating the electric field over here. So because of the conducting sheet, electric field is sigma by epsilon naught. That's why. Let's talk about this one. Let's talk about this one. Now guys, see. Motion of a charged particle in uniform electric field. Guys, let's suppose I have got a uniform electric field over here. Okay, I have got a uniform electric field over here. Sir, where does this come from? Maybe you have placed some charge over here. Because of that charge, electric field is produced. And in this electric field, you are placing some charge, another charge, that is Q, and its mass is M. Okay. The very first thing that you guys should understand is that whenever a charge is placed in an electric field, I'll write over here, whenever a charge is placed in an electric field, whenever a charge is placed in an electric field, it experiences force, and that force is equal to Q times of E. That force is equal to Q times of E. Now, as we have studied from Newton's laws of motion, if there is a body on which force is acting, I can say acceleration, it will have acceleration, because we say F is equal to mass into acceleration. So it will have acceleration, and that acceleration is equal to force upon mass, F by M. So can I write this acceleration as acceleration A is equal to, what is force over here? That is Q times of E. And what is mass over here? That is QE divided by M. Okay. Now, since the force is acting on this mass, we say after some time it will, let's suppose, move and it will reach over here. And here it will have some velocity. It will gain some velocity. So I can say velocity of charge after time t. Velocity of charge after time t. So I can say, you can use this particular equation over here. What is that? That is V is equal to U plus A into T. Initially, you have just released it over here, so initial velocity is 0. So V is equal to, acceleration will be, that is QE divided by M into T. Guys, what I'm trying to say is that you have released a particle over here. Force will act. Okay. Force will act. And if force acts, it will move. If it moves, it will gain some velocity. How much is that? That is QE divided by M into T. Okay. And here you can clearly see V is directly proportional to T. Even if somebody asks you to plot the graph between V versus T, that will be the straight line. Okay. Now, let's suppose if I say displacement after time t. Like guys, what I'm trying to say in this particular case is the particle has, let's suppose, reached over here after some time. It has covered some displacement S. We have to find this S. I'll say use S is equal to ut plus 1 by 2 at square. I would say use this particular equation over here. So this S is equal to initial velocity into time. Initial velocity is 0. So I can say 1 by 2. Acceleration is QE divided by M into V say sir T square. QE divided by M into V say sir T square. Okay. Now my dear friends, S is equal to 1 by 2 QE divided by M into T square. Now, here I can say S is proportional to V say sir T square. If somebody asks you to plot the graph between displacement versus time, so it would be something like this. Why? Because S is proportional to T square. In that case, the graph is something like this. Okay, yes. Now guys, let's talk about we say momentum. Momentum of the charge. Guys, tell me one thing. Don't you think that when it comes to the momentum, we say it is mass into velocity. If anybody has mass, it has velocity, it will have momentum, m into v. So we say this charge which is placed in the magnetic electric field, it has mass. It has velocity also. How much? QE T by m. So momentum will be, sir, P is equal to m into QET divided by m. M and m will cancel. P is equal to QE into T. And if I ask you to plot the graph between, we say momentum versus time, it will be straight line because P is directly proportional to T. Okay. Next, if somebody asks you the kinetic energy of charge. Okay, kinetic energy of charge after time t. After time t. Okay, means if the charge is moving, it has gained some velocity. If it gains some velocity, it has mass, so it will have kinetic energy. Okay, so I can say over here, kinetic energy will be simply that is 1 by 2 mv square. So kinetic energy will be simply that is 1 by 2 m. And what is the velocity of the charge after time t? QET by m. So I can say that is q square e square t square by m square. Why, sir? Because we have got v square over here. This and square will cancel over here. So kinetic energy will come out to be that is q square e square t square divided by 2m. And here kinetic energy is proportional to t square. If it makes the graph between kinetic energy versus t, so it will be something like this. Okay. Okay, yes. Now let's talk about one more point. What is that? That is, we say velocity of charge after covering the displacement x. Velocity of the charge after covering the displacement x. What I'm trying to say is that, guys, there are 2 points over here. If this is the electric field, if you place the charge over here, I'm saying that it has covered the displacement x. Okay, it has covered the displacement x. What will be its velocity after this displacement x? The previous question is, what is the velocity of this charge? What is the velocity of this charge after time t? So let's suppose after 10 seconds, how much is the displacement? Second is, after covering 10 meters, how much is the velocity? How much is the velocity? Same is the question over here. Same is the question over here. Okay. Same is the question over here. So I would recommend you guys to use in this particular case, we say use v square minus u square is equal to 2ax, or we say s. after S. To AS. Okay, S. So now V square, initial velocity we consider 0 is equal to acceleration is how much? QE divided by M into S. So V will be under root of 2QE S divided by M. So this is the velocity of the charge. Okay. 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 So we say this is the velocity of the charge after displacement S. After displacement S. Now my dear friends, if I say the kinetic energy, okay, kinetic energy after covering the displacement S. What is the kinetic energy after covering the displacement S? Guys, understand one thing very carefully. See. If I say it has covered the displacement S, how much is its velocity? This is the velocity. After covering this displacement S, how much it has the kinetic energy? That is one more question. So I'll say over here, kinetic energy is simply that is 1 by 2 mv square. 1 by 2 mv square. Okay. Now, I can say kinetic energy is equal to 1 by 2 m. What is the value of velocity? Guys, v square is this much. You are not supposed to take that equation in which time is involved. You are supposed to take that equation in which displacement is involved. So I'll write over here in this particular case, what is the value of V? That is 2QES divided by M. So that is 2QES divided by M, because V square is this much. Okay, M and M will cancel, 2 and 2 will cancel. So kinetic energy will come out to be QES. Kinetic energy will come out to be QS. This is the kinetic energy after covering the displacement S. This is the velocity after covering the displacement S. Guys, tell me in the chats if everything is crystal and clear from this one. Let me know in the chats. Guys, everyone means everyone. Why it is sigma by 2 epsilon naught? Where? Because for conducting plate, we take it sigma by epsilon naught. Na? That's why we have taken it sigma by epsilon naught. For conducting plate, you see, for conducting plate, electric field is sigma by epsilon naught. We don't take it sigma by 2 epsilon naught. This was the question which was asked in NEET 2019. Okay. Now see guys, in this particular case, what does it say that? It says that we have got an electric field over here. This is the electric field. And in this electric field, this is the electron which falls over here. This is the electron which falls over here. You are basically dropping an electron. We say on this electron, force will act in the opposite direction. So whenever you, and one more thing I just tell you, I just want to tell you guys. So you say whenever you place an particle in the external electric field, it experiences force. Guys, see. One more thing. If the charge is positive, okay, this is electric field, force will be in the direction of electric field. If the charge is negative, force will be opposite to the direction of electric field. Remember this always. Okay? 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 Now guys, I am saying in this particular case, you have got the electric field, and in this electric field you have placed an electron. Okay? Now guys, if you release the electron, it will fall down. So it takes time of fall of electron. It will take some time in falling. Now if you reverse this electric field direction, if you reverse the direction of electric field, now if you release the proton over here, this is the proton. Mass of proton is mp. So it will also fall. It will take some time. You have to compare which will take less time and which will take more time. You have to compare which will take less time and which will take more time. Okay? Okay? You have to compare which will take less time and which will take more time. Now guys, understand very carefully. Understand very carefully in this particular case. I'll use the formula. We say S is equal to ut plus 1 by 2 at square. Now initial, we are releasing this one and this one. Whenever we release an object, means initial velocity is 0. We consider its initial velocity as 0. So initial velocity is 0. This term will become 0. So we say S is equal to 1 by 2. Acceleration of the particle in electric field is how much? That is QE divided by M into T square. QE by M into T square. Now multiply it over here. Now see guys, in this case, I can say this is 2ms divided by QE is equal to, we say, sir, T square. Now guys, in both of these situations, we say displacement, both are covering the same, height. This also. Sir, Q, charge on electron is same as the charge on proton, but they are opposite in nature. Okay? They are opposite in nature. This has negative charge, this has positive charge. And electric field, both are in the same electric field. Okay, just the direction is opposite. So I can say here, T square is proportional to, we say, M. T is proportional to, I can simply say, root M. Because the rest of the things are constant. So means time is proportional to root M. So now I can clearly say, guys, the one which has got more mass will take more time in falling. We say as mass of electron is less than mass of proton. So I can say time of fall of electron is less than time of fall of proton. Means electron will fall, okay, more fastly, and this will take more time in falling. Guys, tell me in the chats, is this crystalline clear to each and every single one? Okay. Everyone means everyone. Guys, tell me in the chats. We have got 50 more slides. It's a big chapter, guys. In every single year, we say 4 to 5 questions are asked from this chapter. That's why it's a big chapter. It will take time as compared to other chapters. Capacitor will finish in maximum 5 to 6 hours. Great, 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 great. Now guys, let's take a look at one more question over here. Let's take a look at this question over here. Okay. We have got proton, if proton, deuteron and alpha particle. Okay. Okay. Are placed in a uniform electric field. It is saying that we have got three particles. We have got three particles. We say proton, we say deuteron, and we say alpha particle. So they are placed in the external electric field. We have to find the ratio of their momentum. We have to find the ratio of their momentum. Guys, see. First of all, if we talk about proton, if we talk about deuteron, and if we talk about alpha particle, we say mass of proton is m, charge on a proton is E. We say mass of this is, I would say over here, that is m, okay? And in this, sorry, its mass is 2m, and charge in this particular case is E, okay? It has got one proton, one neutron. So we say charge is E and mass is 2m. And when it comes to the alpha particle, we say it has got mass 4m and charge is 2e. Because alpha particle is made up of 2 protons and 2 neutrons. So it is made up of 2 protons and it is made up of 2 neutrons. So 2 protons will have charge 2e and 2 neutrons does not have charge, neutron does not have charge. And mass it will have 4m, okay? 2 neutrons 2m, 2 neutrons 2m, 2 protons 2m, 2 plus 2 is 4m. Okay. Now guys, when we place these three particles in the external magnetic electric field, we have to find the momentum. Guys, we say as we recently studied. What is the formula for momentum? P is equal to QE into T. In this particular case, I can say all the three particles are placed in the same electric field. So electric field is constant, same. And time is same for all. We say, sir, time is also same, are same. So I can say this P only depends upon the charge. So can I say momentum of proton PP is to momentum of deuteron is to momentum of alpha particle, it is proportional to Q, that is charge of proton, that is E is to, we say 2E, so that is 1 is to 1 is to 2. This is the ratio. Is this clear? Is this clear? Even we can also find the ratio of kinetic energy over here. Also, what is the formula of kinetic energy? Guys, see. If we check the formula of kinetic energy, that is this one. That is this one. That is Q square E square T square divided by 2m. Okay. So I can say formula for kinetic energy is, that is Q square E square T square divided by 2m. Now, in this particular case, can you tell me over here, sir, electric field is same for all the three, time is same for all the three, so we can say E and T are same. So I can say this kinetic energy only depends upon charge and mass. So I say kinetic energy is proportional to Q square divided by m. 2 is also constant. So I can say now kinetic energy of proton is to kinetic energy of deuteron is to kinetic energy of alpha particle. That will be. Now, that is Q square by m. What is Q for proton? That is E. So I say E square divided by m. Is to. Now what is the charge of this deuteron? That is E square divided by 2m. And then we say for alpha particle it is 2e whole square. That is, it has got charge 2e, so q square, that is 2e whole square, that is 4e square divided by we say mass over here is 4m. Okay, and in this particular case we say 4 will cancel, e square by m, so we say 1 is to 1 by 2 is to we say 1. This is the ratio, or you can also say 2 is to 1 is to 2. 2 is to 1 is to 2. Guys, is this clear? Please tell me in the chats. Is this clear? This is a very good question actually. Yes, 2 is to 1 is to 2. Now guys, we say charged particle projected perpendicular to the electric field. As of now, we were discussing the case in which we have the electric field something like this and charge was moving something like this parallel to the electric field. Charge was moving parallel to the electric field. But right now we have the electric field something like this, and charge is entering this electric field perpendicularly. Charge is entering this electric field perpendicularly, something like this, okay, at 90 degrees. Electric field is this and it is entering perpendicularly. Guys, understand one thing. Whenever charge enters the electric field, we say it will apply force on it. And if the charge is positive, we say force will be in the same direction of electric field. If electric field is upward, we say force, direction of force will be, we say, sir, upward. And we say that is Q times of E. That is Q times of E. Now guys, we say this charge wanted to go straight and cross this field. But because of this force, because of this field, it will be deviated and it will follow this parabolic path and will come over here. So because of this force, it will be deviated. It will deviate its path. It is like the projectile motion. It is like the projectile motion. If let's suppose you are throwing something from this building, so we say it will follow this path. It wanted to go straight, but it follows this path. Why? Because mg is acting in the downward direction. Because of that mg, it is going down. It is going down. Similarly, because of this force, it is going up over here. Now, this is what we call the two-dimensional motion. Here, the body is moving forward, the charge is moving forward, as well as it is going up. It is not in the straight line. It is the two-dimensional motion, okay? It is the two-dimensional motion. So, it is also moving, guys, it is moving along x-axis, it is moving forward, as well as it's moving along y-axis, x-axis, y-axis. So we say it performs 2D motion along x-axis and along y-axis. Okay. Now, I would want you guys to understand this particular thing over here. I would want you guys to focus on this particular thing over here. What is that? That is, if I ask you, is there any force acting on this charge in the x direction? We say, sir, force in the x direction is 0. No force. But if there is a force in y direction, yes. Guys, force in y direction means that is this force, that is Q times of E. It is along the y axis. Okay. And What is the initial velocity in x direction, guys? What is the initial velocity in x direction, guys? We say initially all of its velocity is given in x direction. This is ux. No velocity is in the y direction. This is completely in x. So we say initial velocity in this particular case is, we say, sir, u. That is ux. And initial velocity in y direction is initially 0. uy is the initial velocity. So force in x direction is 0. If we say force is 0, means acceleration is 0, because force is equal to mass into acceleration. So acceleration in x direction is 0. But now guys, force in y direction is q into e. Acceleration in y direction is qe by m. That we already studied. qe by m. Okay. Now. Guys. Let's suppose if I ask you, the particle has reached over here. What is the final velocity in x direction? What is the final velocity in x direction? How will you find? Sir, final velocity in x direction, v is equal to u plus a into t. So this is vx. Initial velocity in x direction is how much? That is u plus. Acceleration in x direction is how much? 0. 0 into t. So vx is equal to u. So guys, whatever is the initial velocity in x direction, same will be the velocity finally in x direction. So vx is equal to ux is constant, that is equal to u. Okay. And when it comes to the vy, what is vy over here? Guys, understand this point also. Vy is the final velocity in y direction. How do we find this? Sir, vy is equal to u plus a into t. Vy is equal to, tell me, initial velocity in y direction is how much? That is 0, because you are finding the y velocity, so that is 0. Acceleration in y direction is how much? qe by m. So plus qe by m into t. So that's why it is mentioned over here, velocity in y direction is qe by m into t. Is this clear till over here, guys? Tell me. Everyone, I'll get some water. Give me a second, okay? Just a second, I'll get some water. Okay, so I can simply say, guys, in this particular case, this is the final velocity in x direction. This is the final velocity in y direction. Okay. Forget about this one and this one over here. Don't get confused with these two. Okay. Now, guys, I would want you guys to focus exactly over here. These 3 points I made you clear. These 3 points I made you clear. Here the particle is performing, we say, two-dimensional motion, okay? it is moving along x-axis as well as it is moving along y-axis. Okay. Now, let's suppose when the particle comes out of this, so we say it is making an angle of theta with the horizontal. If somebody asks you what is the value of this theta, this is important. We say this is tan inverse of, that is QED. Q is the charge, E is the electric field, okay, E is this electric field. D is the width of the electric field, upon mu square. M is the mass of this charge, okay, and U is the initial velocity, Guys, directly remember this, okay? This is the angle at which, I'll write over here, tan of theta is equal to QED divided by mu square. We say this is the angle at which the charge comes out of the electric field, Okay. And this y, what is this y? Guys, this particle was supposed to reach over here, but it has gone this much high. So this is the y displacement. And that is QE into x square, okay? X is this horizontal displacement, this is vertical displacement, upon 2mu square, Okay. Now guys, I have told you in this particular case, when the charged particle enters the magnetic field perpendicularly, at what angle it comes out, how much is the vertical displacement, and force in x direction, acceleration in x direction, velocity in x direction. Velocity in y direction, force in y direction, acceleration in y direction, final velocity in y direction. All of these points you will have to remember. Okay. Yes. Now guys, one more important thing I just want to say. If somebody asks you what is this final velocity, okay? Final velocity, also, we say final velocity with which charge comes out. Final velocity with which charge comes out. So I can say that final velocity, guys, it is something like this. This is the velocity v, this is vx, and this is its vy. This angle is theta. You can clearly compare it. This is v, this is vx, this is vy, and this is theta. Now, don't you think that this velocity will be, that is under root of this vector square plus this vector square, that is vx square plus vy square? Yes, sir. So this velocity I can simply write as, what is the value of vx? Vx is ux, and how much is ux? That is u. So I can write over here, that is u square plus, what is the value of vy? Value of vy is QET by m. So that is QET divided by m and its whole square. This is the final velocity. Is this clear, guys? Tell me. Is this clear? Give me the signal in the chats. Everyone means everyone. Now. Let's move on to this topic that we have over here, that is electric dipole. Let's move on to this topic that we have over here, that is electric dipole. Guys, understand very carefully this topic over here. Okay, see, electric dipole. What is this electric dipole all about? We say when two equal and opposite charges, are placed at a very small distance, it forms a dipole. Like, you have got over here a charge that is minus q. You have got over here a charge that is plus q. These are equal charges, like this is q also, this is q also. It is not like this one is q and another one is 2q, no. And they are equal in nature, they are opposite in nature. This is negative and this is positive. When two equal and opposite charges are separated by some distance, we have separated these two charges by some distance, that is d. This combination is what we call the electric dipole. Let's suppose if I ask you, I have got over here, that is, we say, let's suppose minus 2q plus 4q. Sir, is this a dipole? We say, sir, no. Why? The charges are not equal. No doubt the charges are opposite, but the charges are not equal. Okay. So I can say in this particular case, is it lagging, guys? Is it lagging? I don't think it is lagging. So we say it is not a dipole at all. Now, my dear friends, if I say I have got minus 4q over here and I have got plus 4q over here, is it a dipole? Yes. Because here the two equal and opposite charges are present, so it forms a dipole. And we say every dipole has a dipole moment. We say every dipole has a dipole moment. Every dipole has a dipole moment. What is that? Dipole moment kind of tells you the strength of dipole. You can understand it something like that. Dipole moment kind of tells you the strength of the dipole moment. So I say in this particular case, we say this dipole will also have its dipole moment. Okay, and that dipole moment we represent with P. We represent that dipole moment with P. Okay, so we represent that dipole moment with P. And we say, sir, this dipole moment is equal to magnitude of charge multiplied by distance between the charge. It is equal to magnitude of charge multiplied by distance between the charge. How much is the magnitude of charge? If it is minus q plus q, it will be q. Here, how much is the magnitude of charge? 4q. So multiplied by d. And the direction of this dipole moment is always from negative charge to positive charge. It is always from negative to positive charge. Yes, it is always from negative to positive charge. Now guys, so we say whenever two equal and opposite charges are separated by some distance, it forms the dipole. Now, I would want you guys to focus completely over here. In this particular case, we are supposed, see, we have to find the net electric dipole moment. The first thing is we have to find out, is this forming a dipole? Yes or no? We say yes. See guys, I'll redraw this figure over here. I'll redraw this. So this is plus Q over here and this is plus Q over here. Keep it as it is. And here we have got minus 2Q. Minus 2Q means minus Q and minus Q. Now, in this particular case, we say this forms one dipole, okay, equal and opposite charges, and this forms another dipole. This has got the dipole moment from negative to positive. This has got the dipole moment from negative to positive. Now see, here you have got two vectors. First vector is this is P, and another vector is this is P. And angle between these two is given as 120 degrees, 120. If you have got the two vectors and we say angle between the two vectors is 120, we say resultant in that case, net in that case is P only. It is also P. It is also P. And we can also say this is magnitude of charge. How much is that? Q into L. That is Q into L, because distance between the charges is L over here. Let's suppose you are given a question something like this. Find the electric dipole moment, net electric dipole moment from this figure. You can find the net dipole moment in this figure by redrawing the figure. You'll have to redraw this figure. We'll have to redraw this figure. Let me redraw this figure over here. See guys, I say you have got a negative charge over here. Keep this negative as it is. You have got plus 3Q over here. Keep this plus 3Q as it is. You have got plus 2Q as it is. Keep this plus 2Q as it is. And then you have got minus 2Q. Just a second. Let me change it a bit. See guys. Let's check if the dipoles are formed over here or not. This is minus Q. Here minus Q. Keep it as it is. Here you have got plus 3Q. Don't you think that you can write this as plus Q and plus 2Q? It's one and the same thing. Plus Q and plus 2Q becomes plus 3Q once again. And this minus 4Q you can write as minus 2Q and minus 2Q. This minus 4Q, you can break it. Minus 2Q. And this plus 2Q, you can keep this as plus 2Q only. Now, can you tell me in this particular case, guys, do you think that this is forming one dipole? Do you think that this is forming another dipole? Do you think that this is forming another dipole? So I can say, dipole moment of this dipole is from negative to positive. Let's call that as P. Dipole moment of this dipole is from, we say negative to positive. Let's call this as 2P. Sir, why 2P? Because here charge is twice. It is 2Q. So dipole moment is 2P. And dipole moment of this is from negative to positive. Call this also as 2P. Sir, why 2P? Here also charge is twice. Okay, magnitude is doubled. Now let me make these vectors over here. So this P in the upward direction, I'll make it over here, P. This 2P in the forward direction, I'll make it over here, that is 2P. This 2P in the downward direction, I'll make it over here, that is 2P. Now tell me one thing, this one and this one, they are opposite. What is the resultant of this one and this one? It will be something like this. So this 2P as it is, resultant of this one and this one, that is 2P minus P will be P, but in the downward direction. And now you have to find the resultant of this one and this one, that will be this, that is R. So R in this particular case will be R, either you call it the R, either you call it the P net. That will be this vector square, that is 2P whole square, plus this vector square, that is P square. So this R resultant will be, or you call it the better would be P net. 2P whole square is 4P square plus P square, and this is root. So this is 5. So it will come out to be root 5P. Is this clear? Is this clear? Next. Guys, electric field due to a dipole. Electric field due to a dipole. Guys, see, I'll write a statement over here. What is that? That is, when it comes to a dipole, we say dipole has got charge in it. Okay, that is positive charge and negative charge. If dipole has got charge in it, we can clearly say that it creates the electric field. It will create the electric field. Why? Because charge is there, electric field will be there. I'll say over here, dipole has charge in it. So it creates, we say, electric field. Cool? Yes, this is the general statement. Now guys, the very first point is we have to find the electric field at point P. Okay? So we say at point P, we have to find the electric field. Guys, this is the dipole. Dipole moment is from negative to positive. So we say this P is at x distance and this angle over here is theta. So we say at x distance we have to find the electric field. So we say, I'll write over here, this electric field is equal to, this electric field is equal to, that is Kp. What is P? P is the dipole moment divided by x cube. What is x? X is the position, distance where you have to find the electric field. And this is what we call the general point. Yes, general point. Kp by x cube. Then we say under root of. So I'll write over here 3 cos square of theta plus we say 1. This is the electric field because of the dipole at this arbitrary point. We say this is the electric field at general point. General point. Now guys, see. When it comes to, I would want you guys to focus over here. One more thing I'll tell you. And at this point, let's suppose the direction of electric field is this. Okay. We say it is making an angle of alpha. It is making an angle of alpha. And this angle over here is theta. Now, if somebody asks you, what is the value of this alpha? Okay, this angle. We say also, this tan of alpha is equal to, we say tan of theta, divided by 2. This tan of alpha is also equal to tan of theta divided by 2. Keep this thing in your mind. Okay. Now, let's talk about, we say, case 1. We say on its axis. Guys, understand one thing. If I say this is minus q, if I say this is plus q, and I am asking you, previously you told me the electric field at this point, general point. What if I ask you to tell me the electric field at this point, electric field on its axis? Okay, what is the electric field on its axis? Guys, this was theta, okay? If you have to move on to the axis, do you have to decrease the value of theta or increase? You will have to decrease. So we say on its axis, we say dipole moment, this is P, this is P. We say, I'll write over here, on its axis, what should be the value of theta? That is 0 degrees. If you make the angle as 0 degree, then you will reach the axis point. Now, use the same formula, which is which one? This general one. So I can say, electric field will come out to be, that is Kp divided by x cube. Right now, x would be this. From the center till this point, Kp. Check. Guys, am I audible? Tell me. Now see guys, so is this clear? Please tell me in the chats, is this clear? How does this come 2s Kp by x cube? Is this clear? Is this clear? Please tell me in the chats. Is this clear? See, I'll repeat it. I am saying that if we have to find the electric field at x distance, you will have to decrease the value of theta. If you make the theta as 0 degrees, you'll reach on to the axial point. Axial point is that point which lies along the axis of the dipole. Okay. Battery is, guys, I need to recharge this we say mic, so we'll take a break. Guys, we will have to finish this chapter today, okay? So right now we say 175 students are watching. This is the actual competition. How many of you started with me? We say more than, I guess, 600 plus students, 650 were there in the starting. Right now 174. This is the actual competition. Okay, so be ready. Okay, we'll take a break of we say, let's suppose 20 minutes. Okay, so 12:54, I'll start with 1:15. We say break. One 15 a.m. Check. Guys, am I audible? Let me know in the chats. Am I audible? Let me know in the chats, everybody out there. Okay. So now, see. Let me explain this. So we say when it comes to the axial point, okay, when it comes to the axial point, you'll have to decrease the value of theta. Guys, this was, we say, sir, theta over here and this point. Now, axial point means this point. This is the point which lies on the axis of the dipole. So if you have to find the electric field at this axial point, you will have to decrease the value of theta. So you'll have to make the theta is equal to 0 degrees. Now use the general formula. E is equal to Kp divided by x cube. Okay. Then we say under root of 3 cos square of theta. Theta is 0. Because for axial point, theta is 0. Okay. And then we say plus 1. Now cos 0 is 1. So 3 into 1 is 3. So this will be Kp divided by x cube. We say under root of. Guys, 3 into 1 is 3. And 3 plus this 1 is 4. So it is root 4. Okay. Now root 4 is how much? 2. So this will be twice Kp divided by x cube. So we say electric field on the axis of the dipole is simply, that is, twice Kp divided by x cube. As simple as that. Okay. Then we have got the equatorial position. Now guys, see, let's suppose we say this is over here, this is minus q, this is over here, this is plus q. Okay. And distance between these two is something. Let's suppose this is what we call the equatorial position. Okay. In case of equatorial position or perpendicular bisector, this is the point. We say this is the point. Now at this particular point, you guys are supposed to tell me the value of electric field. Guys, understand one thing very clearly. Don't you think that in this case, we say this is the dipole moment, and how much is the angle over here? Here, value of angle is, we say, sir, 90 degrees. At this point, at axis, value of theta is, we say, 0 degrees. We say at equatorial point, we say theta is equal to 90 degrees. If value of theta is equal to 90 degrees at equatorial point, so I can say electric field will be, that is Kp divided by x cube. Then we say under root of Kp by x cube. Then we say under root of 3 cos square theta. 3 cos square of, what is the value of theta? That is 90. Then we say plus 1. Okay. Cos 90 is how much? 0. 0 multiplied by 3 is 0. So it will be 0 plus 1. That is 1 over here. So electric field will come out to be, that is Kp divided by x cube under root of. Instead of this, it will be 0 plus 1. 0 plus 1 is 1. So I can simply say this will be 1 into Kp by x cube will be root 1 is 1. So it will be Kp divided by x cube. It will be Kp divided by x cube. Okay. This is electric field at the equatorial point. And always remember, the direction of this electric field will be something like this. Opposite to the direction of dipole moment. Okay. And when it comes to this case, when it comes to, we say which one? Yeah, when it comes to this case, that is axial case. In case of axis, we say direction of electric field will be something like this, along the direction of this. Now, next thing I would want you guys to understand is this one over here. Guys, understand very carefully. We have got, okay, before this, solve this particular question. Solve this question. We have got a dipole over here. This is the dipole, okay? It has got the dipole moment P. And because of this dipole, you have to find the electric field at A and you have to find the electric field at B. Because of this dipole, you have to find the electric field at A and B. Don't you think that this A point is what we call the general point for this dipole? Okay. So from here to here, if this side is given as L, so this will be clearly that is a root 2L. This will be root 2L. Okay. Now guys, if we say at point A, let's find the dipole moment at point A. Guys, see, we say, I'll use the general formula. E is equal to, that is Kp divided by x cube under root of 3 cos square of theta. How much is the theta for point A? That is 45 degrees. 45 degrees plus 1. Guys, if we have to find the electric field at point A, we use the general formula. Why? Because this is the general point over here. So I'll say, sir, this electric field will come out to be, that is Kp divided by x cube instead of this x. What is the value of x for point A? X is root 2L. So this will be a root 2L and it is whole cube. And then we say under root of cos 45 is 1 by root 2. So it is 3 into 1 by root 2, its whole square, Why? Because it's cos square of 45. Then we say plus 1. And this electric field will come out to be, that is Kp divided by root 2L whole cube. And then we say this square and root will cancel. So it will be 3 divided by 2, we say plus 1. Okay. Now 2 into 1 is 2, 2 plus 3 is 5, so root 5 by 2. So we say it is E is equal to, guys, this is Kp divided by, and this is a root 2 whole cube over here, and this is L cube, because this cube is for both. And over here it will be, this is a root 5 divided by a root 2. Now tell me one thing, guys, this is a root 2 whole cube into root 2. What does it mean? It means a root 2 into root 2 into root 2 into root 2 into root 2. Because this is 4 times root 2 in multiplication. Root 2, root 2, root 2, root 2. Now root 2 into root 2 is 2. Root 2 into root 2 is 2. 2 into 2 is, we say, sir, 4. So instead of all of this, I can write 4. So it will come out to be this root 5 divided by, instead of all of this, I'll write 4. And then we say Kp divided by L cube. This is the electric field at point A because of this dipole. I hope this is clear. Similarly, if I talk about at point B, this is the point B. At point B. Guys, don't you think that this point B is the actual point? Yes, sir. We say at point B, use axial formula. And how much is the electric field because of the dipole on its axis? We say, sir, that is 2Kp divided by x cube. And I say E is equal to 2Kp. What is x? For point B, we say x is equal to this distance, that is L. So that is L cube. This is the electric field at A. This is the electric field at B. Now, solve this. See guys. You have got the two dipoles over here. You have to find the electric field. You have to find the electric field. You have to find the electric field at this point x distance because of these two dipoles. Tell me one thing. Don't you think that, sir, for this dipole, this point is axial point? Yes. So for this dipole, we say electric field at this point will be away from this dipole. That will be away from this dipole. And how much will be that? 2kp divided by x cube. Done. So for this dipole, this is axial point. At axis, electric field is twice kp by x cube. Cool. For this dipole, this point is equatorial point. Guys, you can rotate it also something like this. If you remember, this is minus, this is plus. This is a dipole. This is dipole moment P, okay? I am saying that at equatorial point, electric field is opposite to the direction of dipole moment. Now, if this is the dipole moment, because of this, electric field at this point will be, don't you think that will be opposite? Yes, that is downward. Opposite. If this is upward, this is downward. And that will be kp divided by x cube. Why? Because this will behave like as the perpendicular bisector or equatorial point. Okay? Okay. So I say, I'll mention over here, this is perpendicular bisector point. This is axial point. Now, if you have got the two vectors over here and you have to find their resultant. Okay, you have to find their resultant. So this will be the resultant. And how much is this resultant? That is net dipole moment. That will be under root of, if you have got two vectors, this square plus this square, that is twice kp divided by x cube, its whole square. Then we say plus this square, that is kp divided by x cube and its whole square. Now guys, this is how much? How many times? 2 square is 4. 4 plus 1 is 5 times. So this is 5 kp divided by x cube and its whole square, and this will be root. Okay? Yes. Now this square and root will cancel, so it will come out to be a root 5. We say kp divided by x cube. I think this is the answer. Yes, a lot of students are mentioning in the chats. That is absolutely great. Can you tell me the answer of this question? What is the electric field at this point? You have got this dipole and you have got this dipole. What is the electric field at x distance? What is the net electric field at x distance? Guys, see how you will solve this. We say this dipole and this dipole. Don't you think that they are at 90 degrees? Yes. Don't you think that this dipole and this dipole will have the resultant something like this, and that is root 2p? Because whenever the two vectors are at 90 degrees, the resultant is root 2 of that vector. Okay. Now forget about this vector and this vector. We have got only this dipole. Now for this dipole, this point is the axial point. I'll write the same thing. We say root 2p, this point, let's call this as Q. Point Q is the axial point. Okay. So use the axial formula. So I say electric field will be 2kp divided by x cube. Cool. So I can say 2k. Instead of p, I'll write root 2p. Why? Because I have taken this vector now. So I'll say this is a root 2p divided by, I can say x cube. So this will be 2 root 2 kp divided by x cube. Please tell me in the chats, is this clear? Guys, tell me in the chats, is this clear? Give me the signal in the chats if this is crystalline clear. Great, great. Now take a look. Now take a look. See guys, electric dipole in a uniform electric field. You have got an electric field over here. And in this electric field, you have placed a dipole. Okay. Now see. Dipole means it has got positive charge. Dipole means it has got negative charge. Okay. Whenever you place a positive charge in the external electric field, we say force acts on it, okay, along the direction of electric field. And on this negative charge, force acts opposite to the direction of electric field. Now, don't you think that these two forces will try to rotate the dipole? Guys, these two forces will try to rotate the dipole. We say these two equal and opposite forces. These two equal and opposite forces will try to rotate the dipole. So, when it rotates the dipole, always remember, whenever there is rotation, we say torque is involved. Torque is something which rotates the body. Force is something which accelerates the body. So we say, so torque is created. What I'm trying to say is that, guys, if this is a rod, if you apply the force on the rod and this rod will rotate, we say, here, this rod is rotating because of the torque. Like you have force in the normal motion, linear motion. Similarly, in angular motion, in rotational motion, you have torque. Whatever the role force plays in linear motion, same role torque plays in rotational motion. So if there is rotation, means torque will be there. Torque is what? Torque is the rotating effect or rotational version of force. Okay. Now guys, directly I would want you guys to remember, and this torque is a rotating effect. Now see, I would say, sir, this torque in this particular case will be, we said this will have a dipole moment, that is, sir, P. P is the dipole moment from negative charge to positive charge. And electric field is forward, that is E. Okay. Now see, what is the value of this torque? Value of this torque will be, that is P, E and sine of theta. And we say where theta is the angle between, we say P and E. Theta is the angle between P and E. And so we can say in this particular case, this torque is equal to, we say P and we say cross E. Because A cross B is AB sine theta, PE sine theta is P cross E. So simply I say, guys, whenever you place a dipole in an external electric field, this external electric field will apply force on positive charge, something like this, on negative charge, something like this. Because of that, the dipole will try to rotate. And because of that rotation, we say torque will be produced. Okay, rotation means torque. So torque will be, and what is the value of that torque? PE sine theta. Okay. Now. Let's suppose, guys, if you have the electric field over here, If you have placed the negative charge something like this, positive charge something like this, so this is the dipole moment from negative to positive. What is the angle between dipole moment and electric field? They are parallel. So theta is equal to 0 degrees. And how much will be the torque in this case, guys? How much will be the torque? We say torque is PE sine of theta, and sine 0. Here it is 0. So torque here is 0. So we say torque on this body, torque on this dipole in this case is 0. And net, how much is the net force? Net force is also 0. So this is pulling the body in this direction. This is pulling the body in this direction. So net force is all, this force gets cancelled with this force. Net force is also 0. Net torque is also 0. So we call it the stable equilibrium. Okay. And we call it the translational equilibrium. Translational equilibrium as well as rotational equilibrium. We call it the translational equilibrium as well as the rotational equilibrium. What does that mean? That means the body, this dipole will not rotate, neither will it move forward or backward. It will not do the translational motion, nor it will do the rotational motion. That's why we call it the translational equilibrium, rotational equilibrium, stable equilibrium. Okay. And we say net torque is 0, net force is 0. If theta is equal to 180 degrees, what does that mean? Here you have got negative charge, here you have got positive charge. So dipole moment is from negative to positive. Electric field is forward. Angle between E and P is 180. They are opposite. Okay. In this case also, net force is 0. Why? Because on the negative charge, force acts in the backward direction. On positive charge, force acts along the same direction. This force gets cancelled with this force. So net force is 0. And we say here also net torque is 0. Let me show you how. Tau is equal to PE sine of theta and sine of 180 over here. Sine 180 is 0. So torque also is 0 over here. So torque is 0, this is 0. And this is what we call the unstable equilibrium. Let me give you the example. Let's suppose, guys, this is a bowl over here. Okay, this is a bowl and this is a ball. If you displace this ball something like this, it will come back to its original position. If you displace the ball something like this, it will come back to its original position. This is what we call the stable equilibrium. When you displace the ball, it tries to come back to its initial position. That's called the stable equilibrium. Okay. Like now, if you have got the ball over here, which is at rest, here also it is stable. Here also it is in the equilibrium. If you displace the ball over here, it will fall and it comes down, but it will not go back. So it moves from unstable to stable. Here it is unstable equilibrium. Unstable equilibrium. So here if you displace, it will not come back to its initial position. Same is the case here. See, guys, if you displace, rotate this dipole something like this, again, force on the positive charge will act in the forward direction. I'll show you over here. See, this is the electric field. If this is the dipole, this is negative charge, this is positive charge. If you displace, rotate this dipole, this is positive, this is negative. On this positive, force will again act in the forward direction, force will act in the backward direction. This will again rotate and will bring it to the original position. That's why we call it the stable equilibrium. Like this, like this. Let me talk about unstable. This is the electric field. And this is, we say, positive charge. This is, we say, negative charge. Okay. Now, if you displace it, let's suppose like this. Okay. Now, positive is here, negative is here. Tell me, on positive, force will act in the forward direction. On negative, force will act in the backward direction. These two forces will rotate the dipole something like this. If it rotates the dipole something like this, then finally this negative charge goes over there, positive charge comes over here. Now, it is the case of stable equilibrium. So here, the body moves from unstable to stable, from unstable to stable. That's why we call it the unstable, we call it the stable. This was the best part. Tell me in the chats how many of you understood this. Tell me in the chats how many of you understood this. Please, please, everyone means everyone. Great, 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 great. Now. Similarly, over here, you can see when theta is equal to 90 degrees. How is that? This is negative charge, this is positive charge. Dipole moment is from negative to positive. Now, electric field is forward. How much is the angle between electric field and dipole moment? 90. And how much will be the torque? PE sine 90, that is PE. So maximum torque. Let's talk about at 270. This is negative charge, this is positive charge. Dipole moment is from, we say, positive to negative to positive. And here, this is the angle and that is 270. In this case also, torque will be here, tau is equal to PE sine of 270. Sine 270 is minus 1. That is minus PE. So what does minus say over here? Minus is just the direction. Here it will rotate the torque in anti-clockwise sense. Okay, something like this. Here it will rotate the torque. It will rotate the dipole in clockwise. Here torque is anti-clockwise. Here torque is clockwise. See, on negative charge force is backward. On positive charge forces forward. So torque is anti-clockwise, here torque is clockwise. So we take this as positive, we take this as negative. Okay. Cool. I hope there is no confusion in this one also. There is no confusion in this one also. Okay? Yes. Now guys, let's come on to this one. Electrostatic potential energy stored in a dipole in uniform electric field. Electrostatic potential energy stored in a dipole in uniform electric field. See guys. Before this, I would want you guys to understand one thing. What is that? See, I say, remember this directly. I say, let's suppose I have a block over here which is placed on the earth. Okay? Yes. Now, my dear friends, if this block is placed on the earth, we consider its potential energy as zero. Directly remember. If this block is on the surface, we say its potential energy is zero. Now, if I am taking to the height h, okay, we say here, its potential energy becomes mgh. Now, my question to you is, who has taken this block to the height h from this ground? Sir, me. Who am I? External agent. So, did I do any sort of work? Yes. So, because of my work done in lifting the block from here to here, because of my work done in lifting the block from here to here, we say work has been done. We say work has been done. And we say because of that work done, only potential energy got stored. If I do not lift this block, potential energy will not be stored. So it is because of my energy, when I used energy in lifting the block, that energy is transferred over here. That work done is stored in the form of energy. If I do not do the work done over here, potential energy will not be stored. Can I say, guys, listen, can I say, my work done or the work done by external agent, the work done by external agent in lifting the block, if somebody asks you, is that work done wasted? You say, sir, no. That work done in lifting the block is stored in the form of potential energy. Where is that potential energy? Here, mgh. The work done by external agent in lifting the block is stored in the form of potential energy of the block. Potential energy of the block. Okay? Yes. So what I did is I lifted the block from the ground. Its energy was 0. So I did the work done. I used my energy. So at this height h, its potential energy became mgh. It is because of my energy. It is because of my work done. I'll write the same statement over here. Can I say? So due to the work done, we say potential energy of the block is changed. Potential energy of the block is changed. Sir, how? Here it is 0. Here it is mgh. So it has changed from 0 to mgh. So can I say, guys, can I say work done by external agent is equal to, we say, change in potential energy. So because of the external agent, potential energy of the block has been changed. Yes, we can write it something like this. Work done by external agent is equal to U final minus U initial. Final potential energy is mgh, initially is 0. Is this point clear? Please tell me in the chats. Is this point clear? Please tell me in the chats. Everyone means everyone. Great. Now, come over here. You have the electric field, okay? In this electric field, you have this dipole, okay? I am saying that rotate this dipole. Sir, if I have to rotate this dipole, I'll have to do the work done. Okay? Sir, will that work done go in the waste? Is that wasted? No. That will be stored in the form of potential energy of the dipole. Like over here, that work done was stored in the form of potential energy of the block. Here it is stored in the form of potential energy of the dipole. So we say the work done by the external agent, the work done by the external agent is stored in the form of potential energy of the dipole, is stored in the form of potential energy of the dipole. Okay, yes. So if you rotate this dipole by an angle of how much? We say theta. So we say potential energy is stored in the dipole. So we say, so potential, so due to the external work done, I say potential energy of the dipole is changed. So due to the external work done, potential energy of the dipole is changed. So here I'll write the same statement. Work done by external agent is equal to change in potential energy. And that I can write U final minus U initial. Yes. Now. If you are saying that, here I am lifting the block because of the external work done, potential energy got changed, got stored. How much? That is mgh. In this case, if you rotate the dipole, potential energy of the dipole is stored, potential energy of the dipole is changed. How much? I'll say that potential energy of the dipole at theta angle is guys, see, we say U is equal to minus PE cos of theta. Okay, or we say U is equal to minus P dot E, because P dot E is, we say, PE cos of theta. Okay, like here that potential energy is mgh. Similarly, in this case, that potential energy is how much? We say PE cos of theta. So if you are rotating this by an angle of theta, how much potential energy got stored in the dipole? Minus PE cos of theta. I hope this is crystalline clear. Now, first point. Guys, see. If I say angle is theta is equal to 90, means dipole is placed something like this. With the electric field, it is making 90. The very first thing I recently told you, net force is equal to 0. Sir, why? Because this is negative charge, this is positive charge. On positive force is forward, on negative force is backward. This will cancel with this one, net force is 0. Sir, net torque is how much in case of 90 degree? P is sine 90. Sine 90 is 1, so this will be the net torque. Okay? Yes. Third one. Sir, what is the potential energy at theta is equal to 90 degrees? Minus PE cos 90. Cos 90 is 0. Sir, at 90 degrees, potential energy is 0. So if the dipole is placed perpendicular to the electric field, it is having the 0 potential energy. Oh, yes. Like on the surface, block was having 0 potential energy. Here, dipole at 90 degree, it has 0. Next. If theta is equal to 0 degrees, this is the dipole. Okay, this is electric field. Angle between these two is 0. How much is the net force? 0. That we know. Net force will be always 0. How much is the net torque over here? Sir, PE sine 0 is 0. Net torque is also 0, already discussed. Cool. What is the potential energy at 0 degrees? Minus PE cos 0. Cos 0 is, we say 1. So it will be minus PE. It will be minus PE. Okay, okay. And I have recently told you, when it comes to the 0 degrees, it is stable equilibrium. And in case of stable equilibrium, it has minimum potential energy because this is minus PE. Guys, remember, please do not confuse yourself. All of these points are important. I am saying when it is theta is equal to 0 degrees, I call it stable equilibrium. Translational as well as rotational. And in this stable equilibrium, I am adding one more point now, that is potential energy is minimum. Why are you saying minimum? Why are you saying minimum? Because it is minus PE. Minus PE cos of, we say, sir, 0 degrees, that is minus PE. Okay. Guys, first give me the signal in the chats. Is this clear? Please, 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 please. Is this clear? Great. Let's talk about theta is equal to 180. This is the electric field, okay? And this is the dipole in the backward direction. Angle between this and this is 180. Net torque is 0. Net force is 0. We know that. Why, sir? Because this will be negative charge. This will be positive charge. Force on positive charge is this. Force on negative charge is this. This will cancel with this one. Net force is 0. Torque at 180 is also 0. Already discussed. I'll not repeat. This is unstable equilibrium. Already discussed. At theta is equal to 180 degrees. It is unstable equilibrium. Okay. Rotational as well as translational. That is what we call the mechanical equilibrium. And what is the potential energy at 180 degrees? Minus PE cos of theta, cos 180. Cos 180 is minus 1. So it is minus PE minus 1. That is plus PE. So at theta is equal to 180 degrees, potential energy is, we say, maximum. And you see, compare. At theta is equal to 0 degrees, potential energy is minimum. See, in case of stable equilibrium, potential energy is minimum. In case of unstable equilibrium, potential energy is maximum. At the top, every concept is done and dusted. Every concept is done and dusted. Okay, now guys, let's suppose this is, we have got a question over here. 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 We have this electric field. And in this electric field, you have the dipole initially something like this. This is negative charge. This is positive charge. Dipole is placed like this. Now you rotate it something like this by 180 degrees. Now this is negative charge. This is positive charge. Okay. So you are rotating the dipole by how many degrees? 180. Initially, how much is the angle? This is the dipole moment initially. Initially, angle is 0 degrees. Finally, angle is 180 degrees. How much work has been done in rotating the dipole by 180 degrees? That is what we are supposed to calculate. See, guys. See. We say, as whenever they ask you to find out the work done, you directly say work done is equal to change in potential energy. Whenever they ask you to find the potential energy, work done, whenever they ask you to find the work done, you find change in potential energy. Okay. So because we know work done is equal to change in potential energy. So this is U final minus U initial. Finally, dipole is like this. Initially, dipole is like this. So I can say work done is equal to U final. U final means minus PE cos of final potential energy. How much is the angle finally? 180. Minus PE cos of 180. Minus initial potential energy. We say minus PE cos of 0 degrees. Guys, because formula is minus PE cos theta, then this is formula is minus. Okay, so initial potential energy will be when theta is equal to 0. Final potential energy will be when theta is equal to 180. Here, theta is equal to 0 degrees. Now tell me, how much is this? Minus PE. What is the value of cos 180? That is minus 1. Minus into minus, cos 0 is 1, so it will be plus PE. Because cos 0 is 1, minus into minus is plus, so plus PE. Minus into minus is plus, so this will be PE plus, we say sir, PE, that will be 2 times of PE. So work done is 2 times of PE. Work done is 2 times of PE. Yes. Now, tell me the answer in this case. Find the work done in rotating the dipole from theta 1 to theta 2. This is theta 1 and this is theta 2. Find the work done in rotating the dipole from theta 1 to theta 2. Okay, I don't know which one is theta 1 and theta 2. Yeah, okay, theta 1 and theta 2. Tell me. Find the work done in rotating the dipole from theta 1 to theta 2. Guys, see. Initially, the dipole is something like this. This is the dipole initially. Okay. And it is making how much angle with the electric field? This is electric field. That is 60 degrees. That is 60 degrees. Finally, the dipole is something like this. Okay. You have rotated the dipole something like this. Finally, how much angle it is making? Sir, this angle and total is 180. 180 minus 60, that will be 120 degrees. We say theta initially is equal to, we say 60 degrees. Theta finally is equal to 120 degrees. Because we always measure angle between dipole moment and electric field, something like this. Okay. So here theta 1 is 60, theta 2 is 120. Now let's find the potential work done. Work done is equal to change in potential energy. So work done is equal to minus PE. We say this will be U final. This will be U final minus U initial. So this is minus PE cos of. Finally, how much is the angle? 120 minus PE cos of 120 minus, we say minus PE cos of 60. Cos 60. Now guys, see, this is minus PE. Cos 120 is minus 1 by 2. Then we say minus into minus is plus. We say PE. Cos 60 is 1 by 2. Cos 120 is minus 1 by 2, minus into minus is plus, and PE as it is, this is PE. Cos 60 is 1 by 2. Minus into minus is plus. So it becomes PE divided by 2 plus, we say PE divided by 2. And that is, we say, sir, PE. Yes, answer is PE. Answer is PE. Next. See guys, find the work done in rotating the dipole by 180 degree, which is perpendicular to the field. This is electric field and dipole is placed something like this, which is placed perpendicular to the field, such that it is making how much angle? That is 90 degrees. Find the work done in rotating the dipole by 180 degrees. Now, you have to rotate this by 180 degrees. Rotated by 180 degrees will be something like this. Now, this will be the angle, that is 270. Okay. So, here, find the work done in rotating the dipole by 180 degrees. You have to rotate the dipole by 180 degrees. But the point is mentioned, which is placed perpendicular to the field. The dipole is placed perpendicular to the field. Then you rotate it by 180 degrees. This is 180, completely opposite. Here I can clearly say initially I say theta is how much? We say, sir, 90. Finally, I can say, we say theta is how much? That is 270. Initially, theta is 90. Finally, how much is theta? 270. Let's find the work done. Work done will be minus, we say delta U. That is U final minus U initial. So work done in this case will be U final. That is minus PE cos of. Finally, how much is angle? 270. 270 minus PE cos of 90. Initially angle is 90. Cos 270 is 0. Cos 90 is 0. So work done will be 0. Yes. Work done will be 0. Work done will be 0. Now, let's start this potential energy. Where are you sending this fire? For what? Now guys, we have 3 more hours and we'll finish it. I would want you guys to focus over here. Very important topic personally. When it comes to the NEET 11, 12th, we say, this is what I feel, this is what I felt previously, the difficult topic in the entire physics. Now I'll make you understand. Electrostatic potential energy. Let's suppose, my dear friends, you have got a charge over here that is plus Q1. Okay, it is placed exactly over here. And you have got, we say, one more charge that is over here, which is at infinity, which is at very far distance, that is infinity. Okay. Now, my dear friends, we say at infinity, we consider this potential energy as zero. Like we consider potential energy on the surface of Earth as zero. Similarly, we consider potential energy at infinity zero. Okay. I am saying you the simple thing. I would want you guys to bring this charge. From infinity to this r distance. From infinity till over here. Okay. So I would want you guys to bring this charge from infinity to this distance. At what distance? We say, sir, r distance. Tell me, who is going to bring it from infinity to r distance? Sir, external agent. Okay. External agent will actually bring it. Let's suppose when external agent is bringing it, like when it was over here. Okay. We say this charge plus Q1 is repelling this charge in this direction with electrostatic force. Now, if you have to bring this charge over here, you have to apply the force in the opposite direction. You have to do the work done. So we say this is the external force. Okay. So by applying the external force, you are bringing the charge Q2 from infinity to r distance. Okay. So I say, means the external agent did the work done. Is that work done wasted? No, sir. Where does that work done go? That work done will be stored in the form of potential energy. So we say the work done, by the external agent, in bringing the charge from infinity to that point, or infinity to r distance. By bringing the charge from infinity to r distance is stored in the form of potential energy between the two charges. Is stored in the form of potential energy between the two charges. So can I say over here? So Work done by external agent, work done by external agent. Because of that work done, guys, see, here potential energy is 0, here potential energy is UR. So I can say here also work done by external agent. Because of this external agent, potential energy of the is changed. Potential energy between the charges is changed. When at infinity it is 0, here it is UR, so potential energy is changed. Because of what? When you brought this charge from infinity to this point, then only we say potential energy is changed. Then only we say potential energy is changed. Then only we say potential energy is changed. Cool? Yes. Now guys, I would want you guys to tell me, I would want you guys to understand one thing over here. I would want you guys to understand one thing over here. What is that? That is, see. If I say work done, let me make you understand this concept. What is work done? Let's suppose I have got a block over here. And on this block, I am applying some sort of force. Because of this block, because of this force, this block will move. It will cover some displacement S. Could you please tell me, sir, is the work done over here? Yes. Whenever you apply the force on any body, we say if it displaces, covers some displacement, we say work is being done. And that work is what we call, we say F into S, we say cos of theta. This is how do we find the work done. How much is the force? How much is the displacement? What is the angle between F and S? That is 0. So here work is equal to plus F into S. Now you might have also seen that if you are applying the force on this block, we say frictional force will act on the block in the opposite direction. Now, can you find the work done by this frictional force? Guys, see, this force is in the backward direction. Displacement is in the forward direction. We say force multiplied by displacement and cos of angle between this and this is 180 degrees. They are opposite. So here force is negative of Fs. So here this work is negative. Here this work is negative, this work is positive because of this. Now, one more small thing I just want to say. We say, what is that? Small work done. Can I say due to, I can write small work done. Small work done. Guys, see. If I say work, this is the total work done. Let's suppose you are applying the force on a block, okay? Because of this force, this block got displaced by a little amount. Little displacement. So we say this is ds. So here, small work has been done. So I write that small work done dW is equal to, that is force multiplied by small displacement, then we say cos of that angle, that is 0. So dW in this case is F into ds. This is small work done. Now come over here. Guys, see. I am saying that if you say work done because of this external agent, because of its work done, potential energy has changed, potential energy has stored. Okay. Now here, this electrostatic force is opposite to the external force, and we say here both are equal. Don't you think that if they are opposite to each other, whatever is the value of work done because of this, same will be because of this, but it will be negative. Like here, work done because, see, friction is opposite to this force. So work done because of friction came out to be negative. Same is the case over here. We say whatever is the work done because of this, same will be the work done because of this, because both are equal, but in opposite direction, opposite. So we say we say F external is we say negative of F electrostatic. Both are opposite. Negative sign says they are opposite and equal. So I can say work done by external agent, we say, so work done by gravitation, sorry, not gravitation, work done by electrostatic force is equal to negative of work done by external force. Whatever is the value of work done by external force, same will be for, but this will be negative. Why? Because they are opposite. So I can say in this particular case, sir, work done by electrostatic force, it will be simply, that is work done by external forces, how much? That is delta U. So keep the negative as it is and you write over here, this is delta U. This is what I wanted to make you understand. Is this clear? Work done by this electrostatic force or conservative force is equal to negative of change in potential energy. Tell me, is this clear? Is this clear? Work done by electrostatic force is negative of change in potential energy. Work done by external force is positive of change in potential energy. Yes, yes. Cool, cool. So as of now, I wanted to make you understand this. Now. What is this? The work done by external agent in bringing the charge from infinity to r distance is stored in the form of potential energy between the two charges. And that potential energy will be, if you are saying I am doing work done in bringing this charge over here, that work done is stored as potential energy. How much that potential energy will be? That is U is equal to, that is K Q1, this charge, Q2 divided by R. K Q1 Q2 by R. This much will be the potential energy stored. Okay, this is the potential energy at R distance between the two charges. Okay, this is also clear, this is also clear. So from now onwards, if somebody says that if you have got the two charges, okay, how much is the potential energy between the two charges? K Q1 Q2 by R. What is this actually? Actually, this Q2 charge was at infinity. Somebody took it from infinity and placed at R distance. The amount of work he did in bringing this to R distance, that only is stored in the form of potential energy, and that potential energy is this one. I hope this is clear. I hope this is clear. Now, next. I say, as I recently saw that work done by electrostatic force is equal to negative of change in potential energy. Work done by electrostatic force is negative of change in potential energy. Now, can I say due to the small work done, if I do the small work done, we say small potential energy will be stored, as simple as that. If I do the large work done, large potential energy will be stored. We say if I do to the small work done, small potential energy will be stored. Small potential energy will be stored. So I can say that is dW is equal to, that is minus small, because of small work done, we say small potential energy will be stored. That is minus du. Okay, that is minus du. Now guys, how do we write this work done, dW? Guys, small work done, we write something like this. dW is equal to F dot ds. ds is the small displacement. So I can write over here, this is F dot, either you write ds, dx, dr, it's one and the same thing. So is equal to minus du. So I can say F is equal to minus du divided by dr. We say this is the relation, between force and potential energy. This is the relation between force and potential energy. This is the relation between force and potential energy. Means if potential energy is given, you are supposed to find the force, you will do the differentiation. Du by dr is what? Differentiation. Dy by dx is what? Differentiation. So if potential energy gives, you are supposed to find the force, you will have to do the differentiation. And one more thing. Also, from this equation only, take it over there, from this equation only, I'll say this is equation first. We say also from first, I can say this is minus du is equal to f dr. Take it over there. So du is equal to f dr. Integrate both the sides. Integrate both sides. So that will be integration of du is equal to integration of, and this is negative f dr. Now guys see. In this particular case, integration of du will be delta u. Small change in potential energy will give you the large change in potential energy, delta u. And it is equal to, so we say this is delta u is equal to minus integration of f dot dr. Okay. Now guys, what does it say? It says that if force is given and you are supposed to find the potential energy or change in potential energy, you will have to do the integration. So if force is given, and we integrate to find change in potential energy, and if potential energy is given, you are supposed to find the force, you do the differentiation. Is that clear? Is that clear, guys? Yes. So we say now potential energy between the system of charges. From now onwards, we say if this is, we say Q1 and you have got another charge plus Q2 which is at r distance, potential energy will be simply, that is K, we say Q1, that is Q2 divided by r. In reality, what is this? This charge was at infinity. You brought it from infinity, placed it over here. The amount of work you did will be stored in the form of potential energy, and that is this one. Now, you have got this question over here. Find the net potential energy of the system. Guys, see, in order to find the net potential energy of the system, you have to first check the number of pairs. First, in this case, how many number of, guys, see. This is the first pair. This is the second pair. This is the third pair. Write the potential energy between these two pairs. See, between these two. I'll write net potential energy of this system. Between these two, we'll write K, Q1, Q2. That is Q square divided by L. Okay. Then we say plus. Between these two, it is K, Q square divided by L. Between these two, it is K, Q square divided by L. And I can say this is 3 times K, Q square by L. Okay. Okay. Now, write the potential energy between this. See, how many pairs are formed over here? 1 pair, 2, 3, 4. Then we say diagonal 5 and this diagonal 6. So write the potential energy net over here. That is, sir, K, Q1 into Q2. That is Q square divided by L. Divided by L. Now here also same. Here also same. Here also same. So how many times? 4 times. So I'll write 4 times k cube square divided by L. Then we say plus. Guys, what is the potential energy between this and this? That is k q square upon distance between this and this is root 2 into L. And how many diagonal pairs? 1 and 2. So this is 2kq square divided by root 2 into L. Okay, this is your homework. Find net potential energy of the system. And guys, one more thing, yes, if the charge is negative, you have to take it along with the sign. Like if you have plus q and if you have minus q, this is R. If they ask you to find the potential energy between the two, you will say U is equal to K. This is Q and this is Q. So we say plus Q and this is minus Q by R. Plus into minus is minus. So minus KQ square by R. Okay. There are few topics left. We'll take a little break. We'll take a little break. We'll finish it, guys. We'll finish it, guys. Let's not keep it for the next session. Next session, we'll take the new chapter. Yes, I'll solve 2-3 questions and then we'll take a short break. See. Tell me the answer of this question. Okay, in this particular case, we have got a triangle over here. Okay, this is plus q, plus q, plus q. Till now, everybody was asking for the break. Now I am asking for the break. Now I need a break. Huh? Wait. So we say this is plus q, plus q, plus q placed at the corners of an equilateral triangle. What we are doing is that we will shrink these charges, okay? We'll bring them close to each other. We are shrinking this triangle. Initially, they were at a distance between each other. And finally, they are at a by 2 distance between each other, okay? Now they are at a by 2 distance. Now guys, in this particular case, we are supposed to find what is the external work done. How much is the external work done in shrinking this, in bringing this close to each other. See guys, we say when it comes to the work done, we say work done is equal to change in potential energy. Whenever you have to find the work done, that is change in potential energy. How much is the work done in shrinking this triangle, bringing them close to each other? That will be. We say, sir, W is equal to U final minus U initial. What is the potential energy finally? Potential energy finally of this system. Guys, see. Let's write the potential energy of this system. K, Q into Q is Q square divided by Distance between them is a by 2. Now, how many pairs are over here? We say 1, 2, and 3. So this is 3 times. Now go take this 2 over there. So 2 into 3 is 6k q square divided by a. Now come over here. What is the initial potential energy, sir? That is k, let's write for this pair, q square by a. Now, how many pairs? 1, 2, 3. So it is 3 times. So I'll write over here, work done will be, final potential energy is 6k q square divided by a minus initial potential energy is 3k q square divided by a. So 6 minus 3 is 3k q square divided by a. Okay. So this is the work done in shrinking this triangle. Guys, let's take a break, huh? Break is much needed right now. And I'll check the time. A short break, short break. Break till 2:50 a.m. check. Let's take a look at this particular question. See guys, we have got the 6 similar charges, okay? This is a hexagon over here. This is a hexagon over here. That is plus q, minus q, minus q, plus q, plus q, minus q. Our sides and are at the corners of the hexagon. Side is D as shown in the figure. The work done in bringing the charge q naught to the center from infinity is, okay? Guys, see. Let's suppose it is saying that the charge q naught was initially at infinity. And then we have taken this from infinity to its center. How much amount of work we are supposed to do in order to take this charge from infinity to this point, that is center, okay? Guys, whenever they ask to find the work done, you simply say work done is equal to change in potential energy. Simple method. And you say over here, this work done will be, that is U final minus U initial. Final potential energy minus initial potential energy. Now, initially it is at infinity. I can say initially at infinity. So can I say U initial will be 0? Because initially we consider the potential energy as 0. And we say finally at center. Finally the charge is exactly at center. If finally the charge is at center, what is the final potential energy, guys? Guys, see. Final potential energy will be between these two, okay? So I can say between these two. Let me just write what is the final potential energy. First, we'll write for the negative charges, okay? Or let's write for the positive charges. K Q naught into Q. We say, sir, K Q naught into Q divided by, we say distance between them is D. If this side is D, this will be also D. That is D. This is the potential energy. Now guys, don't you think that between these two same potential energy will be there? Between these two same potential, because this is Q naught Q, Q naught Q, Q naught. So we say this is 3 times. Then we write the potential energy of these negative charges, okay? So then we say minus. We say Q naught, this Q. So minus, we say K Q naught and this Q divided by. What is the distance between the two? That is also, sir, D. And how many negative charges are? 1, 2, 3. So this is 1 pair, 2 pair and 3rd pair. So this will be also 3 times. So this and this will cancel. This will come out to be 0 also. Now work done will be final minus initial. That is also 0. So which option is the correct option? This. And this is the question which was asked in NEET 2022. 0 is the correct option. Yes. Let's move on to the next one. See guys, in the electric field of the charge Q. Okay. Let me show you this similar question over here. Okay, let me show you here only. Guys, it says that we have got a charge Q which is placed at the center. There is another charge Q which we are taking from A point to, we say, sir, B point along this path. Okay. We also have taken this charge along this path, A to C. We have also taken this along A to D, A to E. And we are supposed to say which of the following options is correct. Means in which path work done will be more, work done will be less. Guys, see, If you are taking this charge from this point to this point, means you will have to do the work done. You'll have to do the work done. Okay? You'll have to do the work done. If you are taking along this path, you'll have to do the work done. If you are taking along this path, you will have to do the work done. You will have to check the work done. Let's check the work done along path AB. We say work done along AB. If you take this charge from A to B, how much will be the work done? That is what we need to calculate over here. Guys, how do we find the work done? That is change in potential energy. That is U final minus U initial. Guys, finally the charge is at B. Initially the charge is at A. When charge is at A, what is the potential energy between these two? This is the radius R. Sir, that is initial potential energy. Finally it is at B. Here also this is R. So what is the final potential energy? K, Q into, this Q is finally over here. Q into Q is Q square divided by R. What is the initial potential energy when charge was at A? So that is also K, Q square by R. Guys, I am saying that when this charge is at A, how much is the potential energy between the two? K, Q square by R. When charge is at B, how much is the potential energy between the two? K, Q square by R. This comes out to be 0. So along AB, we say work done is 0. Similarly, if you check along AC, using the same method, we say work done along AB will be equal to the work done along AC, will be equal to the work done along AD, will be equal to the work done along AE, and all of this is 0. All of this is 0. So we say option D is the correct option, 0 along each path. 0 along each path. Even along this also, see guys, when the charge is over here and finally the charge is over here, this is Q. Now tell me, what is the distance between these two? That is R. Here also it is R. So initially potential energy is K, Q square by R. Finally also K, Q square by R. So 0. So next we have this question. Find the work done. This is a good question actually. Find the work done if you move an electron of mass m slowly from A point to B point. Guys, this is the electron. You are moving this electron from A point to B point. Its mass is m slowly in a semicircular path. What is the work done? What is the work done? What is the work done? And let me tell you before itself, 0 is not the answer. See guys, here, let's first talk about work done by electrostatic, F electrostatic. How do we find that? W is equal to negative of work done by change in potential energy. Let's first find work done by conservative force or work done by electrostatic force. So you say, sir, that will be W is equal to negative of U final minus U initial, negative of U final minus U initial. Guys, finally this electron is exactly, it has reached over here. This is E. Initially this electron is over here, minus Q or E, whatever you say. We say final potential energy will be, guys, see, finally, what is the potential energy between this and this? Between this one and this one, sir, that is K, that is Q, and another one is E divided by we say, sir, R. Okay. Then we say minus. What is the potential energy initially when the charge was over here? Sir, between these two, here also distance is R. So I'll write K, Q, E divided by we say R. This and this will cancel. So work done comes out to be 0. Work done comes out to be 0. Now, this is the work done because of electrostatic force. But there is one more thing over here. There is one more thing over here. There is one more thing over here. We say work done by gravitational force. Guys, see, in this particular case, mass is given. And this height, you are taking this mass from this electron from here to here. You are decreasing the height by how much? We say, sir, 2r. So means if mass is involved, means gravitation is involved. So we'll say same formula is used in the gravitation also. We say work done by gravitational force is equal to negative of change in potential energy. Like you have over here, work done by electrostatic force is equal to negative of change in potential energy. Same formula over here. Now, I can say work done by gravitational force is equal to U final minus U initial. Guys, finally, it is at this surface over here. At surface, we consider potential energy as 0. So we say finally it is 0 minus. Okay. Initially, what is the potential energy at when it is at height h? When it is at height h, we say, sir, in this particular case, when it is at height h, how much is the potential energy? We say, sir, that is mgh, and height is how much? R plus R is 2R. So that is mg2R. Now minus into minus becomes plus, so that is 2mgr. So work done here is 2 mgr. This is the answer. Is this clear, guys? Is this clear? Please tell me in the chats. Is this crystalline clear? Okay, great. Now take a look over here. Electric potential. See guys. Let's finish this topic, electric potential. Let's suppose you have got a charge over here, that is Q. Okay. You have got another charge over here, that is Q naught. Okay. Or we say this charge over here is capital Q, and you have got another charge over here that is plus Q. And the value of this plus Q is, let's suppose, 1 Coulomb, and it is present at infinity. Now I want you to bring this close to this charge over here. Okay. And if you bring it close over here, that is this Q. Okay. Now, do you think that you have to do some sort of work? We say, sir, yes. We say yes. Okay. Now, in this particular case, I can say, the amount of work in bringing this charge from infinity to this point will be stored as the potential energy between the two. I'll write over here. The work done here is stored as potential energy between the two. And how much is that potential energy, sir? That is K Q1, sir, Q2 divided by, we say, R. Now, my question to you is, guys, what is the value of this Q? That is 1. So place 1 over here. So we say U is equal to KQ into 1 divided by R. Now, what is this? Sir, this is the potential energy. Can I say this is the potential energy in bringing 1 Coulomb charge from infinity to R distance? This is the potential energy stored in bringing the 1 Coulomb charge from infinity to r distance. Or this is the potential energy. This is the potential energy in bringing the unit positive charge from infinity to that point. And this potential energy is what we call the potential. We gave it the new name, that is the potential. So we say this is the potential energy of 1 Coulomb charge. So basically potential is the potential energy of 1 Coulomb charge. Sir, is potential energy? Yes. For how much charge? 1 Coulomb charge. If I say I am bringing 10 Coulomb charge from infinity to this point, so its potential energy, I call it something else, x. So potential energy of 1 Coulomb charge is what we call potential. That is what we call the potential. Okay. Okay. So we also say, so potential is potential energy per unit charge. Potential is potential energy per unit charge, or potential energy of 1 Coulomb charge. That is what we call the potential. That is what we call the potential. Okay. So from now, so can I say, what is the definition now? What is the definition now? It is the amount of work done in bringing the 1 Coulomb charge from infinity to that point. Simple. That work done will be stored as the potential energy, and that potential energy is called the potential. Because, and what is the formula? We say this formula, V is equal to, we say KQ divided by R. In reality, what is this? This is potential energy. It is actually 1 over here. You have basically taken 1 Coulomb charge from infinity to this point. The amount of work which has been done is this much. Okay. So also we say potential is simply, that is potential energy divided by charge, potential energy per unit charge. Potential energy of 1 Coulomb charge, potential energy per unit charge. So what is the value of potential energy here? Sir, that is K capital Q small q divided by R, and divided by this Q. This and this will cancel. So again, it will come out to be KQ divided by R. Okay. So potential is nothing but potential energy per unit charge. Now, one more thing I just want to say over here. We say as guys, focus, as we say, when it comes to the work done by conservative force, electrostatic force, it is negative of change in potential energy. Okay. Now, can I just do one thing? We say divide both sides by Q. So we say this is W divided by Q is equal to minus delta V divided by Q, minus delta V, and I'll write over here, this is not delta V, this is delta U. This is delta U divided by Q. Okay. So we know work done by conservative force is equal to change in potential energy. So I'll write over here, I'm dividing both sides by Q. Now, can I write this as work done? Work done, I'll write as F dot dr divided by this Q is equal delta U by Q, potential energy per unit charge. We call this as potential delta V. Potential energy per unit charge is delta V. Now guys, can I say, guys, F by Q, we know, sir, electric field. What is the formula of electric field? That is force upon this charge. Okay. How do you find this, guys? We say force is equal to Q times of E. I told you F is equal to Q times of E. Here E is equal to F divided by Q. So can I say instead of F by Q, I'll write E, and this dr is equal to minus, I'll write over here, this is delta V, okay? And when we talk about the small work done, let's take this in terms of small work done. So I'll write over here dW, see, I'll change it, I'll write over here, we say due to small work done, can I say, sir, that is dW is equal to, there will be small change in potential energy, that is du. Now divide both sides by Q, So what is the formula for dW? Sir, that will be F dot dr divided by this Q is equal to dV by this, du by Q, potential energy per unit charge, it will be dV. Now F by Q is electric field, and this is dr is equal to minus dV. So electric field will come out to be minus dV divided by dr. So we say this is the relation between electric field and potential. This is the relation between electric field and potential. This is the relation between electric field and potential. E is equal to minus dV by dr. This is the relation between electric field and potential. Okay, yes. Now guys, I would want you to focus exactly over here. What is dV by dr? Means if potential is given at a point, you are supposed to find the electric field. What will you do? You will do the differentiation. Now, one more thing. Let's suppose if I make the graph over here, between V versus R, okay? And we say, let's suppose I'll take it over here, something like this. Now, if I'm asking you to find the slope of this graph, okay, how do you find the slope of this graph? Slope will be simply, sir, this tan theta, that is perpendicular by base. Slope is tan theta, and that is perpendicular by base. That is, we say simply dV divided by dr. Okay. Now, this is equation first. Guys, I got, this is the relation between electric field and potential difference. Means if potential difference is given, you have to find the electric field, you will do the differentiation. Now, from the graph, V versus R graph, I am finding the slope. Guys, what is slope? See, please wait. If I say this is Y versus X graph, okay? And I am asking you to tell me what is the slope of this graph. You say, sir, slope of Y versus X graph will be simply dy divided by dx. Or you say delta Y by delta X, dy by dx. Or Y by X, whatever you say. And if I say I have got V versus T, what is the slope of this graph? You say, sir, dV by dt. This by this. Similarly, if you have got V versus R graph, slope of this graph is tan theta. Tan theta means perpendicular divided by base, dV divided by dr. Okay. Now from equation first and second, this is second, we say from equation first and second. From this equation and this equation, can I not say here, dV by dr is, take this minus over here, negative of electric field. Here dV by dr is slope. So I can say electric field is equal to this negative of slope. So I can say electric field is equal to negative of slope in case of in case of VR graph. So means from now onwards, if VR graph is given and you are supposed to find electric field, you will find slope and put the negative sign. Like example over here. Like I'll give you the example over here. This. You have V versus R graph. Check from where to where electric field is positive. Guys, see. In this particular case, if you take a look at this graph over here, okay, from A to B, guys, always remember one thing. Always remember one thing. If the graph is something like this, here this angle, this theta is less than 90 degrees. Remember it. So we say its slope is positive. Its slope will be positive. Directly remember it. Directly. And here this angle is theta is greater than 90 degrees, less than 180 degrees. So we say here slope will be negative. Slope is negative. Why? Because tan theta will be negative, slope is negative. Here slope is positive. Now tell me, in this case, if I say slope of AB, can you tell me slope of this AB graph? Is it positive or negative? Sir, theta is less than 90. So we say slope of this graph will be positive. Okay. Now if slope is positive and this is V versus R graph. In case of V versus R graph, you have to find electric field. We say electric field is negative of slope. In which graph? Electric field is negative of slope. In which graph? In V versus R graph. So I can say in this particular case, electric field will be negative of slope. Is slope positive or negative? Sir, positive. Whatever will be the value, it will be positive. So negative into positive will be negative. So electric field is negative. So for this AB, electric field is negative. Okay. Next, we say for BC, we say slope for BC is equal to 0. Whenever this line is parallel to x-axis, we say its slope is 0. Why? Because slope is tan theta, tan 0 is 0. So if slope is 0, we say electric field is negative of slope, so electric field is 0. Similarly, for this BC, CD, we say for CD, theta is greater than 90 and less than 180. So slope will be negative. So we say slope of CD is equal to negative. So electric field will be negative of slope. So electric field is equal to negative of, value of slope is negative. So it will be negative of negative will be positive. So for CD, slope is positive. Guys, is this clear till over here? Please tell me in the chats. Is this clear till over here? So as of now, I have told you one equation over here, that is relation between electric field versus potential difference or potential. Now guys, let's move on to, let me show you this one. Wait. Okay, let me show you this one. See guys. See. We say as electric field is equal to minus dV divided by dr. We studied this relation, dV divided by dr. Now take it over there. So I can say this dV is equal to, take this minus also, minus E dr. Integrate both sides. So it will be integration of dV is equal to minus integration of E dr. Integration of dv will give you the total change in potential difference. Delta V is integration of E dr. Now guys, see. What does this equation tell you? This equation says that if electric field is given and you are supposed to find the potential difference, what you are supposed to do is you will have to integrate. You will have to integrate. Okay. Now. Now, my dear friends, in this particular case, let's suppose I'll make the graph over here. The graph between was, we say, E versus R. Okay. Let's suppose the graph is something like this. You might have studied one single thing, okay? If not, just remember, if you have Y versus X, and if the graph is curve, in case of YX graph, if I ask you to tell me what is the area under this curve, this area under this curve, you simply say it is integration of whatever is mentioned on this axis Y, and this will be dx. This is, if it is integration of, if it is V and T, so it will be integration of V dt. Now sure, if I ask you in case of ER graph, we say in case of, we say ER, in case of E versus R graph, in case of E versus R graph, I say, what is this area under the curve? You say area under the curve will be simply, that is integration of E, and this is a dr. Now, this is the equation first and this is the equation second. Don't you think in this particular case, we say from first and second. From first and second. We say from first and second. Here, integration EdR is equal to negative of change in potential difference. Here, integration EdR is equal to area. So, I can simply say, sir, that will be this delta V will be negative of, we say negative of area. Let me show you the question on this one. That is this. Let me show you the question on this one. That is this one. Okay. So we say in this particular case, you guys are supposed to tell me what is the potential difference between, I say between 2 to 6. Between x is equal to x is equal to 6 meter. What is the potential difference between x is equal to x is equal to 6? Okay. Now guys, when it comes to E versus R graph, see, I recently told you, in case of E versus R graph, where is it? See. Yeah. In case of E versus R graph, if you are supposed to find the potential difference, you find the area. Now, come over here. So we say in this particular case, we say potential difference will be simply, that is area, negative of area. So potential difference will be simply negative of area. Area from x is equal to x is equal to 6 means this area. Now can you tell me how much is this area? This is length is 2, breadth is 10. 2 into 10, that is 20. And how much is this area? We say this is given as 1 by 2 base into altitude, that is 2, altitude is 10. This and this will cancel, 20 plus 10 is 30. So that is minus 30 volts. Okay, that is minus 30 volts. We are supposed to find from x is from 2 to 6, from 2 to 6, 2 to 6. Okay, forget about this. Yes, from 0 to 6 it is minus 40 volts. From 2 to 6 it is minus 30 volts. That is correct. Okay. Yes. Now guys, find the potential difference between A and B. Find the potential difference between A and B. This is point A and this is point B. You have got an infinitely long rod, infinitely long wire. And you are supposed to tell me the potential difference between A and B. Guys, see. I can tell you one thing over here. Let's suppose I'll say at R distance, what is the electric field because of this wire? Sir, that is 2k lambda by R. Because of the infinitely long wire, electric field is 2k lambda by R. Okay. Now, I am asking you one single thing. If you know the electric field, you can find the potential difference. We say as we know. Can I say potential difference will be simply that is integration, we say EdR. Okay. Now guys, you can say, sir, this delta V is equal to integration of what is the electric field at this general R distance? Sir, that is 2k lambda by R, and over here this is dr. Now you have to find the potential difference between A and B. A is at R1 distance, B is at R2 distance, so it is from R1 to we say R2. Simply I am saying you can find easily the potential difference because of this rod. You can find easily the electric field because of this rod. If you know the electric field, you can find the potential difference with this formula. Put the negative sign also over here. Okay. So I can say delta V will come out to be with, see, this 2k lambda will come out, and then it is 1 by R dr. And this is R1 and this is R2. So this will be, I'll say delta V is equal to 2k lambda and then in integration of 1 by R. So it will be ln of R. Okay. It will ln of R. And limits are from R1 to R2. So that will be 2k lambda, okay, ln of we say R2 by R1. This is the potential difference. Is this clear, guys? Is this clear? Please tell me in the chats. Is this clear? Is this clear? Okay. Is this clear? Can you find the potential difference between A and B in this case? Potential difference delta V, simply guys, we say as electric field is equal to dV divided by dr. So we say this dV is equal to EdR. Between A and B, if you are finding out, that is dV, potential difference. Electric field is given as E. dr is the distance between these two, that is E into D. That is E into D, directly. There is one statement, that is potential decreases. That is potential decreases in the direction of electric field. Potential decreases in the direction of electric field. This is the statement that we have. Potential decreases in the direction of electric field. Now guys, if this is the positive charge, remember this. We say at point A and at point B, if you move along the direction of electric field, potential will decrease. It is obvious. As you go close to the charge, we say you'll have to do more work done. Previously, what did I say? This is the charge if I say plus Q1. If you are bringing another charge plus Q2 close to this charge, you have to do more work done. So potential energy will increase. So potential will increase. Directly you can remember over here, if this is a charge, okay, we say as you move away from the charge, potential will decrease, potential energy will decrease. So can I say potential at A is greater than potential at B? Yes. And electric field at A is greater than electric field at B. Why? Because it is near to the charge. If the point is near to the charge, electric field is more. Now when it comes to the negative charge, as you move towards this negative charge, okay, as you move towards this negative charge, we say potential will decrease. So here potential at A is less than potential at B, and electric field at A is greater than electric field at B. Why? Because if you are close to the charge, electric field will be large. Now let's take a look at the question which was asked. This is the direction of electric field. You guys are supposed to tell me A, B, C are the 3 points in the uniform electric field. The electric potential is maximum at B. We say maximum at A, maximum at C, same at all. I guess maximum at B. Because if you move along the direction of electric field, potential difference, this potential will decrease. So option A is the correct option. Okay. Now guys, I would want you guys to remember one thing. And that is, see guys. Yes. Guys, let's suppose I have got a charge over here. We say, sir, at r distance, what is the value of potential? You say simply that is K, this Q divided by R. Sir, in reality, what is this? In reality, this is the potential energy. Sir, what kind of potential energy? You took 1 Coulomb charge from infinity, you placed it over here, and the amount of work done I did in bringing that charge over here, this is that work done. That work done is stored in the form of potential energy, and that is this one. So if there is a charge, we say it will have potential, kq by r. Now let's take a look at this question. You guys are supposed to tell me find the net electric field and net potential at the center. See guys, if this is side A, always I have told you this will be L by root 2. Okay. Let's first find the net potential at the center. What is the net potential? Am I audible now? Yes, mic battery is down. Now see, so we say because of this also it will be kq upon L by root 2. Because of this also it is kq upon L by root 2. Because of this also it is kq upon L by root 2. So it will be 4 times. So it will be 4 times. So it is, take this root 2 over there, 4 root 2 kq divided by L. 4 root 2 kq divided by L. Okay. Guys, please wait for 5 minutes. Check. Now see guys, so when it comes to the electric field, so this is the net potential. Potential does not have the direction. You simply say potential does not have the direction. You simply say you are adding this potential. When it comes to the electric field, guys, see, because of this at center, electric field will be away from the charge. Because this is a positive charge, that is E. Because of this, electric field at this point will be away from the charge. Because of this, electric field at this point will be away from the charge. Because of this, electric field at this point will be away from the charge. So all of these will cancel out. So net electric field in this case will come out to be 0. So here net electric field is 0, but net potential is not 0. Okay. Like we have got this. We say find V net and E net at center. You guys are supposed to tell me what is the net potential and net electric field at the center. See. When it comes to the net potential, guys, understand very carefully. We say if this is A, obviously this will be A divided by a root 2. Because of this minus Q charge, we say it is minus KQ divided by, we say A by a root 2. Because in case of the potential and potential energy, you have to take charges along with the sign. Then we say potential energy, potential because of this, we say plus KQ upon A by root 2. Then we say because of this minus, we say KQ upon, we say A by root 2. Then we say plus, because of this, KQ upon A divided by root 2. This and this will cancel, this and this will cancel, so net potential will be 0. Let's talk about net electric field. Guys, see. Because of this positive charge, electric field is away from the charge. Because of this positive charge, electric field is away from the charge. Because of this negative charge, electric field is towards the charge. Because of this negative charge, electric field is towards the charge. This angle over here is 90 degrees. Now tell me, if you have got E and E in the same direction, so we say this is 2E. If you have got E and E in the same direction, we say this is 2E. Angle between these two is 90 degrees. We say resultant in this case will be how much? That is a root 2 of, we say, sir, 2E. And we say this is 2 root 2 and E will be how much? E is the electric field due to any of the charges over here. So that will be K. Let's suppose because of this it is Q divided by this distance, that is A by a root 2 whole square. So now this will be A by a root 2, that is A square by 2. 2 into 2 is 4. 4 root 2 KQ upon A square. This will be the net electric field. Okay. Now this question I'll give you as homework. Why? Because I have already shown you the question of this for, see. We are supposed to find the net potential at this point because of all of these charges. It is going till infinity. Okay, see. How will we write the net potential, sir? Net potential will be, that is, first it is because of this. This is at 1 meters, 2 meters, 4 meters, 8 meters, and so on. So because of the first charge, we say it is KQ divided by 1. Because it is KQ by R. Then potential because of the second charge at origin, it is minus KQ divided by 2. Because of the third charge, it is plus kq divided by 4. Because of the fourth charge, it is plus and it is minus kq divided by 8 and so on. Now in this, what can you take common? This is kq. Then we say 1 minus 1 by 2 plus 1 by 4 minus 1 by 8 plus so on. Okay. Now you know how to add. Okay. You know how to add. This is a GP series. How to find the sum over here? We say sum is equal to a upon 1 minus r. Guys, you can do this now. You can do this now. Okay, it is easy because I have already shown you 2 questions on this one, which were in the electric field. Let's talk about this one. See guys, electric potential due to a ring on its axis. Electric potential due to a ring on its axis. Electric potential due to a ring on its axis. Guys, because of see, if there is a charge, it creates the potential. If there is a charge, it creates potential. As simple as that. Okay. And if you place that charge onto something, that will also create potential. We say because of this ring. See guys, ring has charge on it, so it will create potential. Ring has charge on it, so it will create potential. We are supposed to find the potential at point P. We say this is V is equal to, we say KQ upon under root of, we say R square plus, we say sir, X square. R square plus X square. So this is the potential because of the ring at what distance? X distance. Where R is the radius, X is the distance at which you have to find the potential. Okay. Now guys, if I talk about in this particular case, at center, we say at center, I can say X is equal to 0. If you put X is equal to 0 over here, so potential will come out to be, that is KQ upon, this is under root of R square. This and this will cancel. So it will come out to be KQ divided by R. This is the potential at the center. Okay. Then we say case 1. What is that? Very close to the ring. If you have got this ring over here and its radius is R. Okay. And you guys are supposed to find out the potential at very close to the ring. Can I say in this particular case, we say X is much less than R? Yes, sir. This is a ring. Very close to the ring, I am finding out potential. At center, I am saying potential is this much. Now, very close to the ring. You can neglect X over here because you are adding a very small quantity to the very large quantity. So neglect this X. So V will come out to be KQ upon, we say under root of R square. This and this will cancel. So this is KQ upon, we say sir, R. KQ upon R. And next we say case 2, that is very far from the ring. So in that is, we say R is much less than X. R is much less than X. Okay. Now, in this particular case, guys, I am saying this is the ring. Okay, this is the radius of the ring. And I am saying this is X. Sure, R is much less than X. Now ignore this r over here, v will come out to be kq upon, we say under root of x square, under root of x square. This and this will cancel. So this is kq by x. So potential at very far from the ring is kq by x. Close to the ring is kq by r. At center it is kq by r. Okay. 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 Yes. 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 This is done. Okay. Now, this is a question we have got over here. Okay. Now guys, in this particular case, what I am trying to say is that, see. I have got a ring over here and charge on this ring is positive. I have got another ring over here, charge on this ring is negative. You have to tell me the potential difference between A and B. You have to tell me the potential difference between A and B. Okay. What is that? That is, find the potential at point A, then find the potential at point B, then find the difference VA minus VB. See guys. Let's first find the potential at A, at point A. Let's find the potential. Guys, see, this point is the center of this ring, and this point is very far from this ring. So potential at this point A will be because of this charge plus Q, because of this ring also, that is minus Q. See guys, if I talk about at point A, now, because of its own ring, what is the potential? Guys, potential due to a ring at its center will be how much? Potential due to a ring at its center is KQ divided by capital R. Okay. KQ by capital R. So because of the own ring, I can say potential at A will be, first we'll find because of its own ring, that is KQ divided by capital R. Now, because of this ring, which is at very far distance, here it is mentioned, X is much greater than R. So it will be, guys, it is negative charge minus KQ divided by, at what distance you are finding, that is X. Okay. Let's find out at point B. So you say VB will be potential at B. It will be here potential because of the own ring, that is minus KQ divided by R. Because at the center, it will be KQ by R. And because of this ring, so this point is very far from the ring. So it will be plus KQ divided by X. So we got VA, we got VB. Now we have to find VA minus VB. So VA minus VB, I can write VA is KQ divided by R minus KQ divided by X. Then we say minus. This is minus KQ divided by R plus KQ divided by X. So it will be KQ divided by R minus KQ divided by X. Minus into minus is plus. KQ divided by R minus into plus is minus KQ divided by X. Now KQ by R, this is twice, so 2 times. So this will be 2 times KQ by R. This is also 2 times minus 2 times KQ divided by X. I guess this is the answer. Now guys, potential due to a hollow sphere, okay, and solid sphere. Hollow conducting, solid non-conducting. Remember always, hollow sphere we also call it the, we say conducting sphere, and solid we call the non-conducting sphere. Remember this. Guys, see. We have to, this is a hollow sphere. We know in case of hollow sphere, charge is present on its surface. We have to find the potential at this outside point, r distance. Okay. Then we will find the potential on its surface. Then we will find the potential inside. Guys, directly remember, at very far distance, we consider it a point charge. Okay. So whatever is the formula for point charge, same will be for this. I say outside. So we say potential will be, that is KQ divided by R. So because of this, at outside point, it is KQ by R. Same whatever is for point charge. Okay. So we say because at very far distance, we consider it a point. Okay. Now we say on the surface. On the surface. Can I say on the surface value of small r becomes equal to capital R? If you keep on reducing this r, value of small r is equal to capital R. So we say V surface will be, that is KQ divided by capital R. Yes. And when it comes to inside, guys, you say, sir, there is no charge inside, so potential inside will be 0. No. Potential inside will be same as potential on the surface. KQ by R. Don't ask me why as of now, because time is very less. Okay, because stream will end at, stream has a maximum time of 12 hours. Okay. So we said the reason is basically, if you take any other charge and if you bring it to inside, you don't have to do any sort of work because no charge is present inside. It will not, you don't have to do the work. If no work is done in bringing the charge inside, so means no potential energy will be stored, increased, I would say. So it will remain same, KQ. Directly say, whatever is on the surface, same will be inside. Okay. Now, let's plot the graph. Guys, see, this is V versus R. K constant, Q constant. Okay, no, not this one. K constant, Q constant, R constant. So this is constant. Sir, K constant, Q constant, capital R constant. This is constant. So means potential inside from center to surface is constant. From center to surface is constant. Okay. And then potential outside is inversely proportional to small r. Then it will be something like this. Okay. Okay. So V is equal to constant, and I say this is inside, and V is inversely proportional to small r, and this is outside. This is outside. It is outside. Okay. Guys, is this graph clear? Let's talk about in case of a solid sphere. Potential due to a solid sphere. We are almost done. Potential due to a solid sphere. Now guys see. When it comes to the potential due to a solid sphere, I would want you guys to focus over here. Solid sphere, in case of a solid sphere, we say V outside will be same as whatever is for the hollow sphere. That is KQ divided by small r. And even on the surface, because at very far distance we consider hollow as well as solid, both we say point charges. Hollow means in which charge is filled inside also. So we say V surface is KQ divided by capital R. But when it comes to the V inside, guys, V inside is something different. Right now, charge is present inside. So inside potential will be different, because if you take any other charge inside, so we say you'll have to do the work done, potential will increase. So V inside is, we say KQ upon, guys, directly see, kq upon, we say 2r cube, okay, and then we say 3r square minus, we say, sir, r square. 3r square minus, we say, sir, r square. So this is the value of potential inside. Let's suppose I am saying, sir, inside you are supposed to find the potential at this r distance. This r is variable. For outside point, r is large, small r is large. For inside point, small r is small. Okay. Now, my dear friends, this is the potential inside. If somebody asks you what is the potential at the center, we say at center. Can you tell me what is the value of small r at center? That is 0. Small r is 0. Put small r 0 over here. So V naught will come out to be, that is kq upon 2r cube. Then we say 3r square minus 0. Okay. So this r square and cube will cancel. So V naught will come out to be 3 by 2 kq divided by r. So this is the potential at the center. This is the, by means of this you can find the potential anywhere inside. This is the potential on the surface, okay, and this is the potential outside. This is the potential outside. This is the potential outside. Now guys, in this particular case, if we try to make the graph, this graph is very important. If we try to make the graph, guys, this is, can you tell me where the potential is large in case of solid sphere? Center or surface? Here it is 3 by 2 kq by r. 3 by 2 means 1.5 kq by r. And kq by r, it is 1 times of kq by r. 1 kq by r, 3 by 2, 5 kq by r. So 1.5 is greater. So here r is equal to 0. This is the center, origin. So at origin, potential is maximum. Then see. At origin, potential is maximum. Okay. And this is, we say, sir, V naught. And then this becomes V surface. Okay. And then when you move outside, it decreases. So V is inversely proportional to R, because V is inversely proportional to R outside. So till over here, it is inside. This is surface. And this is outside. Guys, tell me in the chats, how many of you understood this properly, each and every single thing? How many of you understood this properly, each and every single thing? Let me know, guys. Everyone means everyone. Guys, please tell me everybody right now. Okay, now see. Find the electric field and potential at A, B, C. At A, B and C. You have to find the electric field and potential at A, B and C. Now guys, when it comes to understand you would be able to, you can now easily solve this question. See, when it comes to the point A, we say, sir, at point A, let's first find the electric field at point A. Okay. So we say electric field at point A. Guys, this point A lies outside of the bigger sphere. This point A lies outside of this smaller sphere. Okay. So because of this sphere, At point A, we say electric field will be, sir, outside electric field is kq by small r square. I have told you. That is K. Here, charge on this one is Q1 divided by, at what distance you are finding the potential? RA. So, that is RA square. Okay. Okay. Yes. Then we say plus. Electric field because of this sphere outside at this point A. That is K. Charge on this sphere, that is Q2 divided by, at what distance you are finding? That is RA square. We say RA square. Done. Let's find the electric field at point B. Electric field at point B. Guys, see. This point B lies inside of the bigger sphere. These are the hollow spheres. These are hollow spheres. Hollow spheres. So can I say, because of this bigger sphere, electric field inside will be 0? Yes. So I say this is 0 plus. We say electric field because of the inner sphere, because this point B is outside of this inner sphere. So electric field because of this will be K. Charge on this is 2Q2 divided by, at what distance you are finding? That is RB square. Then if we talk about the point C, electric field at C will be simply 0. 0 plus 0. Why? Because C point lies inside of the inner sphere, inside of the outer sphere. So we say because of this one and this one, electric field inside is 0. Now, let's talk about potential. Let's talk about potential at A. Let's talk about potential at A. Guys, see, because of this sphere, this point lies outside. So for outside, potential is kq by small r. That is K. Charge on this one is Q1 divided by small r. Because recently I told you, potential because of hollow sphere is kq by small r. Outside. This is outside. Okay. So kq by small r. And because of this inner sphere, so this is the outside point. So we say this is kq2 divided by, just a second, you are finding it RA. It is RA. kq2 by, we say RA. Then we say, now let's find the potential at B. So potential at B will be, guys, tell me, this point B lies inside the bigger sphere. As I told you, when it comes to the potential, whatever is the potential on the surface of this hollow sphere, same will be inside. On its surface, how much will be the potential? kq1 divided by r1. On the surface, it is kq1 by r1. And same will be inside. Now plus potential at point B because of the inner sphere. This point is the outside point for inner sphere. That is kq2 divided by this distance is, we say, RB. This distance is RB. And then if we talk about the point C, VC. Guys, see, this point C lies inside this sphere. This point C lies inside bigger sphere. Whatever is the potential on the surface of bigger sphere, same will be inside at every point. So that is kq1 divided by r1 plus whatever is the potential on the surface of this inner sphere, same will be inside at every point. Okay, so potential on this inner sphere will be, on its surface will be kq2. Its charge is q2. Its radius is r2. This will be the potential at C. Guys, tell me in the chats, is this question crystal and clear? Everyone means everyone. I need to know. Is this crystalline clear? I don't have the access to block somebody. Okay? I don't have the Unacademy NEET English channel's access. So I cannot block him. A small topic. Electric potential due to a dipole. See guys, you have got negative charge, you have got positive charge. This is a dipole. Two positions. When it comes to the axial position, on the axial position we say potential is, on the axial position we say potential is Kp divided by x square. P is the dipole moment, x is the distance from the center. And when it comes to this equatorial point, we say here potential is equal to 0, net potential is 0. Due to the dipole at equatorial position, potential is 0. At this point, it is Kp by x square. As simple as that. Directly you guys remember this. There is nothing much. Next, just a second, let me check. Okay, let's take a look at this. Find the potential difference between A and B. Very simple. You have to tell me potential difference between A and B. First, you find the potential at A. Then you find the potential at B. Then find the difference. See, let's find the potential at A. Guys, see. When it comes to the potential at A potential will be because of this sphere. Okay. Since this is on the surface of this sphere. So we say potential will be K. Because of this sphere, it is KQ divided by radius of this is R. Okay. Then because of this bigger sphere, whatever is the potential on the surface of bigger sphere, same will be inside also at every point. Because we have studied this. So it will be plus K, charge on this is capital Q, and radius of this is, we say, sir, R. So if this is the potential over here, same will be at inside point. Now, when it comes to the potential at point B, see guys, B point is the outside of the smaller sphere. So because of the smaller sphere, potential at point B will be, that is K, this charge Q, at what distance? Sir, this distance is this capital R. You are finding the potential at capital R. So this is KQ by capital R. Because outside point we say KQ by small r. So small r over here is basically capital R. Okay, variable. Then we say plus. We say potential because of the bigger sphere on the surface. It will be K. Charge on the bigger sphere is Q divided by, we say radius is R. Capital R. Now VA minus VB. VA minus, we say VB. So it is KQ divided by R plus KQ divided by R minus this KQ divided by R minus KQ divided by R. I guess this one and this one will cancel. So here remains this KQ divided by R minus KQ divided by R. Now take this KQ common. So KQ will be common. 1 by R minus 1 by capital R. This is the answer. Is this clear, guys? Is this clear? Please tell me in the chats. Is this clear? One more question is given over here. Two concentric hollow conducting spheres. Two concentric hollow conducting spheres. With what charge should I give to inner sphere so that the potential outside becomes 0? Okay. We are supposed to find the charge on this sphere over here. What is the charge on this sphere? What charge should I give to the inner sphere so that the potential on outside of the sphere is 0? Okay. Guys, let me give you this as homework. Next, let's talk about this one. Equipotential surfaces. Equipotential surfaces. Let's talk about the equipotential surfaces. Guys, see, understand very carefully. Let's suppose if I say I have a charge over here. I have a charge over here. Okay. And I'm saying, sir, at r distance, what is the potential over here? You say, sir, that is kq divided by r. At this r distance, what is the potential over here? That is kq by r. At r distance, what is potential over here? That is kq divided by r. At r distance, what is potential over here? kq by r. Now, if you join all of these points, like this is the charge. At r distance, kq by r, kq by r, kq by r, kq by r, kq by r. It's in 3D. You join all of these points, it becomes a spherical ball. It becomes a spherical ball. Now, don't you say that at every point of this spherical ball, of this sphere, of this surface, potential is same. That is kq by r, kq by r, kq by r, kq by r. Yes. If potential is same at every point of this surface, then this becomes the equipotential surface. That surface upon which potential is same everywhere will be the equipotential surface. Okay? Okay? Like for a point charge, I say the equipotential surface is spherical. For a point charge, I say equipotential surface is spherical. Okay, because at this it is kq by r, 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 kq by r. Okay. Okay. Now guys, see. Am I audible? Am I audible? So in this particular case, I am saying that for a point charge, we say equipotential surface is spherical. Why? Because clearly we can see that, sir, if we join all of these points, it becomes a sphere. So at sphere only we say potential is same. Now if I say this is an equipotential surface over here, so means potential at A will be equal to the potential at B. Okay, so we say potential at A will be equal to the potential at B, then only we can say this is the equipotential surface. Okay, next, the potential difference between any 2 points on the equipotential surface is zero. Obviously, we say if this is an equipotential surface, okay, let me show you. Let's suppose this is a charge Q. Around this charge Q, we are drawing an equipotential surface. And we say at this r distance, what is the potential? KQ by R. Now at this r distance, what is the potential? KQ by R. Let's suppose this is point A. Let's suppose this is point B. Now, could you please tell me what is VA minus VB? VA is KQ by R minus VB is also KQ by R. This and this will cancel, so it is 0. So, potential difference in case of equipotential surface will be 0. It will be 0. Next, no work is done in moving the charge on an equipotential surface. Guys, see. If this is an equipotential surface. Okay, like if we say this is charge and this is an equipotential surface, I am saying that I am taking one more charge from this point and I am placing it over here. So how much is the work done over here? How much is the work done over here? Guys, understand one thing very carefully. We say as. When it comes to the work done, we say that is change in potential energy. We say work done is equal to change in potential energy. I say divide over here with Q, divide over here with Q. So we say work done divided by charge Q is equal to delta U by Q. Potential energy per unit charge will be delta V. So this work done will be simply that is Q delta V. So this is how do we find the work done actually. That is Q delta V. This is one more way to find the work done. Now, if you are taking this charge from this point to this point, how much is the work done? The first thing is potential difference is 0 on equipotential surface. So Q multiplied by 0 is equal to 0. So work done will be 0. Okay. Yes. Next point. Electric field is perpendicular to the equipotential surface at all the points. True. If this is a charge, around this is the equipotential surface. Tell me, because of this positive charge, don't you think that electric field is away from the charge? This is the electric field. Electric field is away from the charge. This is the electric field. Now, this electric field is making how much angle with this surface over here? That is 90 degrees. This electric field is making how much angle over here? That is 90 degrees. That is what it is saying. Even this was the question asked in NEET 2022. Electric field is perpendicular making 90 degree to equipotential surfaces at all the points, here, every point it will be this. There is a question over here. You have got different equipotential surfaces, 10 volt, 20 volt, 30 volt, 40 volt. You are taking a charge from A to B. Here also you are taking the charge from A to B. Here also A to B. Here also A to B. You have to check in which work done is maximum and minimum. Guys, see. Let's find the work done in first case. We say work done is simply that is Q delta V. Recently I I have shown you this formula. Okay. Now, we say in this particular case, W is equal to Q. Q is the charge. You are taking the charge Q. Okay. And delta V is the potential difference. Guys, what is the potential of the first surface? First one, that is 10. What is the potential of the last one? That is 40. So that is 40 minus, we say, sir, 10. So work done is equal to 30Q in this particular case. Let's find the work done in the second case. So that is W is equal to Q delta V. Here also, guys, delta V means final potential minus initial. Final is 40, initial is 10. Here also, W is equal to Q into, we say, sir, 30. So we say in all the cases, work done is same. In all the cases, work done is same. In all the cases, work done is same. Next. This one. See, guys, in this particular case, you guys are supposed to tell me which of the following options are correct. Option A, option B, option C. See, I'll tell you over here. In this particular case, if you check between these two equipotential surfaces, how much is the potential difference? 50 minus 40, that is 10. How much is the potential difference between these two? 10. How much is the potential difference between these two? That is also 10. Okay. Now guys, tell me one thing. As this is the charge present over here, this is the electric field. We say, as we know the formula, we say electric field is equal to delta V divided by delta R, or you say dV divided by dr, or delta V divided by delta R. It's one and the same thing. Now see, guys, in this particular case, I'm saying that delta V between this and this, potential difference, that is same. So delta V is constant. Okay. And when it comes to the electric field, we say as you move away from the charge, electric field will increase. So electric field will decrease. We say electric field decreases, because as you move away from the charge, electric field decreases. Now guys, I say delta V is constant, so electric field is inversely proportional to delta R. Now here, I am saying that electric field is decreasing. Why? Because as you move away from the charge, electric field is decreasing. If electric field is decreasing, so can I not say this delta R will be increasing? Because it is inversely proportional to delta R. Now, what is delta R? Delta R is the distance between these. This is D1, here it is D2, here it is D3. So we say as you move away, electric field decreases, but delta R increases. So D3 is greater than D2, is greater than D1. So which option? D1 is less than D2, less than D3. Guys, how many of you understood this question? Please tell me in the chats. Tell me, guys, how many of you understood this question? See guys. We are done. Okay, now few questions are there. few questions that I'll show you in the capacitors, chapter. Chill. We are done with this complete chapter. Now guys, take a look over here. Electrostatics of a conductor. Let's suppose guys, I have a charge over here that is plus Q. And we say at this small r distance, we have got this sphere over here. Okay. Now, my dear friends, we say because of this charge, electric field will be present over here. Electric field will be created over here at r distance. And how much is that? We say that is electric field, that is what we call the external electric field. That is, we say, sir, simply that is K, because of that is Q divided by at what distance? That is R square at R square. Now guys, what happens over here is that we say due to that electric field, negative charge of this sphere, this is a neutral sphere, neutral conductor. Negative charge of this sphere will get occupied onto this side, okay? Because it is kind of, this positive charge is attracting its negative charge and repelling its positive charge that gets occupied onto the another side. This is what we call the induction. We say induction takes place on the conductor. So we say because of this positive charge, it will attract its negative charge and it will repel its positive charge. So its positive charge gets occupied onto this side, negative gets occupied onto this side, Okay. Now, in this particular case, my dear friends, we say internal electric field is induced, which is from positive to negative charge. Okay. So we say here E induced is set up from we say positive to negative charge. What I'm trying to say is that I'm simply taking a conductor over here, neutral conductor, and I'm taking a charge over here. We say because of this charge, guys, see, we say because of this charge, we say electric field will be created. Due to that electric field, negative charge gets occupied onto this side, positive charge gets occupied onto this side. Electric field is set up over here. That is called the induced electric field. Okay, this is external electric field. And we say after some time, this induced electric field, this becomes exactly equal to the external electric field, but in opposite direction, that is minus KQ divided by R square. Whatever is the external electric field, same will be the induced, but in the opposite direction. And when it comes to the net electric field, net will be zero. Let me show you over here. Find E net, E induced, E external. Guys, see, because of this positive charge, we say external electric field will be set up, and that external electric field will be simply, that is KQ divided by this distance is R square. KQ by R square. Okay. Now, due to this external electric field, charge separation will take place. Okay. So we say positive charge of this gets occupied over here. Okay. And negative charge gets occupied over here. So we say electric field induced is set up from positive to negative. And value of this E induced will be exactly equal to this, but in opposite direction, KQ by R square. And we say net electric field is equal to 0. Why? Because they are equal and opposite. Okay. Because they are equal and opposite. Okay. Now guys, let's suppose 4 5 questions are there. 5 to 7 questions are there. I will be basically talking about these questions in the next session. Okay. And guys, once I end the live stream, I would want you guys to let me know in the comments how was the session. Okay. Do let me know in the comments how was the session afterwards. So I guess with this we'll end the session. Okay. There are some questions. I'll show you these in the capacitors. Chill. Okay. Topics, we have covered every single topic. Okay. Now there are some questions which I personally feel I need to show you. We'll show you in the capacitors. Guys, do let me know in the comments later on how was the session. Do let me know in the comments later on how was the session. Okay. Okay. Open your heart in the comments. Write. Okay. From the bottom of your heart. So that's all for today, ladies and gentlemen. I am done with this. I am extremely tired. Okay. Now I need to go to sleep. I'll eat something first and then I'll go to sleep. And we'll have the next session very soon. Okay. That's all for today. Take care and bye-bye. And I would want you guys to let me know in the comments how was the session. And if you have not liked the session yet, hit the like button as soon as possible. Take care and bye-bye. Take care and bye-bye.